we can kind of visualize it like this. When you run /swap, or any program for that matter, main is the first function to get called with a C program. And so I'm just going to label this bottom row of memory as main. And what were the two variables I had in main called in this code? Yeah. X and Y. And each of those was an int, so that's 4 bytes. So it's kind of deliberate that I reserved a chunk of wood here that's 4 bytes. So let me just call this X, and I'm just going to write the number 1 in this box here. And then I had my other variable Y, and I'm going to put the number 2 there. What happens when main calls swap like it does in this code here? Well, it has two variables of its own, A and B. And A initially is 1, and B is initially 2. But it has a third variable, temp, which is a local variable in addition to the arguments A and B that are passed in. So I'm going to call this temp, TMP, over here. And what is the value of temp? Well, we have to look back at the code. Temp initially gets the value of A. All right, the value of A was 1. So temp initially gets 1. That's step 1 in my 3-line program. OK, A equals B. So that is assigned from the right to the left of the B into the A. So B is 2. A is this. So let me go ahead and erase this and just overwrite that. So at this moment in the story, you have 2 copies of 2. So that's OK, though, because the third line of code says temp gets copied into B. So what's temp? 1 gets copied into B. So let me overwrite this 2 with a 1. And now what happens? Now, unfortunately, the code ends. Swap doesn't actually do anything with the result. And the problem in C is that I could have had a return value. I could go in there and change void to int. But which one am I going to return? The A or the B? The whole goal is to swap 2 values. And it seems kind of lame if you can't write a function to do something as common per last week's sorting algorithms as swapping 2 values. But what really happens? Well, even though when this program starts running, main is using this chunk of memory at the bottom in the so-called stack. And the stack is just like a cafeteria, a stack of trays. It grows up like this. Here's main's memory on the stack. Here's the swap function's memory on the stack. It's using 3 ints instead of only 2. What happens when the function returns, whether it's void or not? The sort of recollection that this is swap's memory goes away, and garbage values are left. So adorably, we get rid of these values here. And there's still data there. Technically, the numbers 1, 1, and 2 are still there in the computer's memory, but they no longer belong to us because the function has now returned. So they're still in there. And this is kind of an example visually of why there's other stuff in memory, even though you didn't put it there necessarily. Sometimes you did put it there. But now, once swap returns, you only should be touching memory inside of main. But we've never actually copied one value into main. We haven't returned anything, and we haven't solved this fundamentally. So how could we do this? Well, what if we instead passed into swap not copies of X and Y, calling them A and B? What if they passed in breadcrumbs to X and Y, sort of a treasures map that will lead swap to the actual X and to the actual Y? Today, we have that capability using pointers. So suppose that we use this code instead. There's a lot of stars going on here, which is a bit annoying, but let's consider what it is we're trying to achieve. What if we pass in not X and Y, but the address of X and the address of Y, respectively? Breadcrumbs, if you will, that will lead swap to the original values. Then what we do is we still give ourselves a temp variable, like an empty glass. It's still a glass, so we still call it an int. But what do we want to put into that temporary variable? We don't want to put A into it, because that's an address now. We want to go to that address, per the star, and put whatever's at that address. What do we then want to do? Well, we want to then copy into whatever's at location A. We want to copy over to location A's contents, whatever is at locations B's contents. And then lastly, we want to copy temp into whatever's at location B. So again, we're very deliberately introducing all of these stars because we don't want to change any of these addresses. We want to go to these addresses per the dereference operator and put values there or get values from. So what does this actually mean? Well, if I kind of rewind in this story and I go back here, I still have temp, although I'm going to delete its value to begin with. I still have B, and I still have A. But what's going to be different this time is how I use A and B. So let me finish erasing those. That's A on the left. This is B on the right. At this point in the story, we're rerunning swap with this new and improved version. And let's see what happens. Well, X is presumably at some address. Maybe it's like 0x123, as always. What then does A get when I'm using this code? The value of A is 0x123. What is the value of B? Maybe Y is at 0x456. What goes in B? Well, I'm going to put 0x456. And then what am I going to do? Based on these 3 lines of code, I'm going to store in temp whatever is at the address in A. What is the address in A? That's this thing here. So I'm going to put 1 in temp. Line 2, I'm going to go to B. All right, B is 456. So I'm going to B. And I'm going to store 2 at whatever is at location A. And at location A is 1, 2, 3. So that's this. So what am I going to do? I'm going to change this one to a 2. Last line of code. Get the value of temp, which is 1. And then put it at whatever the location B is. So B, 456, go there. And change it to be the value of temp, TMP, which puts 1 here. That's it for the code. There's still no return value. Swap returns, which means these 3 temporary variables are sort of garbage values now. They can be reused by subsequent function calls. But now I've actually swapped the values of x and y, which is to say what came as naturally as the real world here for Mariana is not quite as simply done in C, because, again, functions are sort of isolated from each other. You can pass in values, but you get copies of those values. If you want one function to affect the value of a variable somewhere else, you have to, 1, understand what's going on, but 2, pass things in as by a pointer here. So if I go back to my code here, I need to make a few changes now. Let me get rid of these extra printfs. Let me go in and add all these stars. So I'm dereferencing these actual addresses here and here. And I've got to make one more change. How do I now call swap if swap is expecting an int star and an int star? That is the address of an int and the address of another int. What do I change on line 11? Here, yeah. Sorry, a little louder. Sorry, the address of operator. So up here on line 11, we do ampersand x and ampersand y. So that, yes, we're technically passing in a copy of a value, but this time the copy we're passing in is technically an address. And as soon as we have an address, just like when I held up the fuzzy finger, or the foamy finger, I can point at that address. I can go to that address and actually get a value from the mailbox or put a value into the mailbox if I even want. So let's cross our fingers now and do make swap, enter. Oh my God, so many mistakes. Oh, I didn't remember to change my prototype. So let me go way up here and add 2 more stars, because I made that change already. Make swap, /swap, and voila, now I have actually swapped. Thank you. Thank you, the 2 values. All right, so what more can we do here? Well, let me consider that all this time we've been deliberately using getString and getInt and getFloat and so forth, but for a reason. These aren't just training wheels for the sake of like making things easier. They're actually in place to make your code safer. And to illustrate this, let me go ahead and open up one other file here. How about a file called code scanf.c? It turns out that the old school way, the way in C really, of getting user input is via functions like scanf. And let me go ahead and include standard.io.h, int main void, and without using the CS50 library at all for strings or for any of those get functions, let me give myself an int called x. Let me just print out what the value of x is, even though it's going to be, or rather ask the user for the value by asking them for x. And I'm going to use a function called scanf that's going to scan in an integer using %i. And I'm going to store whatever the human types in at this location. And then I'm going to go ahead and, just so we can see what happened, I'm going to print out with %i whatever the human typed in as follows. All right, so line 8 is week 1 style code. Line 5 and 6 is week 1 style code. So the curiosity today is this new line. Scanf is another function in standard.io.h. And notice what I'm doing. I'm using the same syntax that I use for printf, which is kind of a little clue, a format code to tell scanf what it is I want to scan in, that is, read from the human's keyboard. And I'm telling it where to put whatever the human typed in. I can't just say x, because we run into the same darn problem as with swap. I have to give a little breadcrumb to the variable where I want scanf to put the human's integer. And so this just tells the computer to get an int. This is what you would have had to type essentially in week 1 just to get an int from the user. And there's a whole bunch of things that can go wrong still, but that's the cryptic syntax we would have had to show you in week 1. Let me go ahead and make scanf here. Oops. User error. Put the semicolon in the wrong place. Make scanf. Enter. Oh, my God. Non-void doesn't return a value. Oh, thank you. Strike 2. OK. Make scanf. There we go. OK, so scanf, I'm going to type in a number like 50, and it just prints it back out. So that is the sort of traditional way of implementing something like getInt. The problem, though, is when you start to get into strings, things get dangerous quickly. Let me delete all of this and give myself a string s, although wait a minute, we don't call it strings anymore, char star to store a string. Then let me go ahead and just prompt the user for a string using just printf. Then let me go ahead and use scanf, ask them for a string this time with %s, and store it at that address. Then let me go ahead and print out whatever the human typed in just by using the same notation. So here, line 5 is the same thing as string s, but we've taken back that layer today, so it's char star s. This is just week 1. This is just week 1. Line 7 is new. Scanf will also read from the human's keyboard a string and store it at s. But that's OK, because s is an address. It's correct not to do the ampersand. It's not necessary. A string is and has always been a char star, aka string. The problem, though, arises as follows. If I do make scanf, oh my God, what did I do? Oh, I can't. OK, we have certain defenses in place with make. Let me do clang of scanf.c and output a program called scanf. All right, so I'm overriding some of our pedagogical defenses that we have in place with make. Let me now run scanf of this version, enter, and let me type in something like, how about hi again? Huh. So it didn't even store something, and it weirdly printed out null. This time it's in lowercase, but that is somewhat related. What did I fundamentally do wrong, though, here? Why is this getting more and more dangerous? And let me illustrate the point even more. What if I type in not just something like hello, which also doesn't work. What if I do like hello and make a really long string, enter? That still works. Can I do this again? Let's try again. All right, a really long, unexpectedly long string. This is the non-determinism kicking it. Enter. All right, damn it. I was trying to trigger a segmentation fault, but it wouldn't. But the point still remains. It's still not working. But what's the essence of why this isn't working and it's not storing my actual input? Yeah. We have to make space for it. So what we're missing here is malloc or something like that. So I could do that. I could do something like this. Well, let me let the human type in at least a 3-letter word. So I could do malloc of 3 plus 1 for the null character. So like, let me give them 4 characters. And let me go ahead and do make scanf. Whoops. Nope, sorry. Clang. I have to search. Nope. Damn it. Oh. Include standard lib.h. There we go. That gives me malloc. Now I'm going to recompile this with clang. Now I'm going to rerun it. And now I'm going to type in my first thing, hi. That now works. And let me get a little aggressive now and type in hello, which is too long. Still works, but I'm getting lucky. Let me try a hello. Damn it. That still works, too. Sort of. But it actually, not quite. There's some weirdness going on there already. It turns out I could also do this. I could actually just say char star 4 and give myself an array of 4 characters. Let me try this one more time. So let me rerun clang /scanf. Hello, clearly exceeding the 4 characters. There we go. Thank you. All right, so the point here, though, is if we hadn't given you getInt, you would have had to use the scanf thing. Not a huge deal because it seemed to work. But if we hadn't given you getString, you would have had to do stuff like this, knowing about malloc already, or knowing about strings being arrays. And even now, there's a danger. If the human types in 5 letters, 6 letters, 100 letters, this code, like with the hello input, will probably just crash, which is bad. So getString also has this functionality built in where we have a fancy loop inside such that we allocate, using malloc, as many bytes as you physically type in. And we use malloc essentially every keystroke. The moment you type in H-E-L-L-O, we're sort of like laying the tracks as we go, and we keep allocating more and more memory so that we, theoretically, will never crash with getString, even though it's this easy easy to crash your code using scanf if you again did it without the help of a library. So where are we all going with this? Well, let me show you a few final examples that'll pave the way for what will be problem set 4. Let me go ahead and open up from today's code, which is available on the course's website. For instance, a program like this called phonebook.c. And I'm just going to give you a quick tour of it that you'll see more details on in the context of pset 4 itself. We're going to introduce a few new functions you're going to see. You're going to see a function called fopen, which stands for file open. And it takes 2 arguments: the name of a file to open, like a CSV that you might manipulate in Excel or Google Spreadsheets or the like, comma, separated values. And then something like A for append, R for read, W for write, depending on whether you want to add to the file, just open it up, or change it. We're going to introduce you to a file pointer. You'll see that capital file, which is a little non-conventional, capital file is a pointer to an actual file on the computer's hard drive so that you can actually access something like a CSV file or, heck, even images. And we're going to see down below that you're also going to have the ability to write files as well, or print to files. You'll see functions like fprintf for file printf, or fwrite, file write, which now that you will begin to understand pointers, you'll have the ability to actually not only read files, text files, images, other things, but also write them out. In fact, for instance, just as a teaser here, JPEGs will be one of the things we focus on this week, where we give you a forensic image, and your goal is to recover as many photographs from this forensic image of like a digital camera as you possibly can. And the way you're going to do that is by knowing in advance that every JPEG in the world starts with these 3 bytes, written in hexadecimal, but these 3 numbers. And so in fact, just as a teaser, let me open up an example you'll see on the course's website for today. If I scroll through here, you'll see a program that does a little something like this. And again, more on this in if we could, hit the button. Oh, there we go. So here we have the notion of a byte. We're going to create for ourselves, we'll see, a data type called byte, which is a common convention. This gives me 3 bytes. And you're going to learn about a function called fread, which reads from a file some number of bytes, for instance, 3 bytes. We might then use code like this. If bytes bracket 0 equals OXFF, and bytes bracket 1 equals 0xD8, and bytes bracket 2 equals 0xFF, all 3 of those bytes I just claimed represent a JPEG, you'll see an output like this. Let me go ahead and run this program as follows. Let me copy jpeg.c into my directory from today's distribution. Let me do make JPEG. And let me run JPEG on a file, which is available online, called lecture.jpg. And I claim, yes, it's possibly a JPEG. Well, what is that file? Let me open it up for us, called lecture.jpg. And here, for instance, is that same photo with which we began class, namely implemented as a JPEG. But what we're also going to do this week is start to implement our own sort of filters a la Instagram, whereby we might take images and actually run them through a program that creates different versions thereof. For instance, using a different file format called BMP, which essentially lays out all of its pixels from left to right, top to bottom in a grid, you're going to see a struct, a data struct in C that's way more complicated than like the candidate structure from the past or the person structure from the past that looks like this, which is just a whole bunch more values in it. But we'll walk you through these in the pset. And we might take a photograph like this and ask you to run a few different filters on it, a la Instagram, like a black and white filter or grayscale, a sepia filter to give it some old school feel, or a reflection like this to invert it, or blur it, even in this way. And just to end on a note here, I have a version of this code ready to go that doesn't implement all of those filters. It just implements one filter initially. Let me go ahead and just ready this on my computer here. I'm going to go into my own version of filter. And you'll see a few files that we'll give you a tour of this coming week. In bitmap.h, for instance, is a version of this structure that I claimed existed a moment ago. And let me show you this file here, helpers.c, in which there is a function called filter that I've already implemented in advance today. But the ones we give you for the pset won't already be implemented. This function called filter takes the height of an image, the width of an image, and a 2-dimensional array. So rows and columns of pixels. And then I have a loop like this that iterates over all of the pixels in an image from top to bottom, left to right. And then notice what I'm going to do here. I'm going to change the blue value to be 0 in this case, and the green value to be 0 in this case. But why? Well, the image I have here in mind is this one, whereby we have this hidden image that simply has sort of old school style, a secret message embedded in it. And if you don't happen to have in your dorm, like one of these sort of secret decoder glasses that essentially make everything red, getting rid of the green in the world and the blue in the world, you can actually, I'm actually probably the only one who can read this right now, see what message is hidden behind all of this red noise. But if using my code written here in helpers.c, I get rid of all the blue in the picture, and I get rid of all the green in the picture, essentially implementing the idea of this filter, this red filter where you only see red, well, let's go ahead and compile this program, make filter, run /filter on this hidden message.bmp. I'm going to save it in a new file called message.bmp. And with one final flourish, we're going to open up message.bmp, which is the result of having put on these glasses. And hopefully now you too will see what I see. All right. All right. All right, that's it for CS50. We'll see you next time. All right. This is CS50, and this is already week 5, which means this is actually our last week in C together. In fact, in just a few days' time, what has looked like this, and much more cryptic than this perhaps, is going to be distilled into something much simpler next week when we transition to a language called Python. And with Python, we'll still have our conditionals and loops and functions and so forth, but a lot of the low-level plumbing that you might have been wrestling with, struggling with, frustrated by over the past couple of weeks, especially now that we've introduced pointers and it feels like you probably have to do everything yourself, in Python and in a lot of higher level languages, so to speak, more modern, more recent languages, you'll be able to do so much more with just single lines of code. And indeed, we're going to start leveraging libraries all the more, code that other people wrote, frameworks, which is collections of libraries that other people wrote. And on top of all that, will you be able to make even better, grander, more impressive projects that actually solve problems of particular interest to you, particularly by way of your own final project. So last week, though, in week 4, recall that we focused on memory, and we've been treating this memory inside of your computer as kind of like a canvas, right? At the end of the day, it's just zeros and ones, or bytes, really. And it's really up to you what you do with those bytes and how you interconnect them, how you represent information on them. And arrays were like one of the simplest ways we started playing around with that memory, just contiguous chunks of memory, back to back to back. But let's consider for a moment some of the problems that pretty quickly arise with arrays, and then today focus on what more generally are called data structures, using your computer's memory as a much more versatile canvas to create even two-dimensional structures to represent information and ultimately to solve more interesting problems. So here's an array of size 3, maybe the size of 3 integers. And suppose that this is inside of a program, and at this point in the story, you've got 3 numbers in it already, 1, 2, and 3. And suppose, whatever the context, you need to now add a 4th number to this array, like the number 4. Well, instinctively, where should the number 4 go? If this is your computer's memory, and we currently have this array, 1, 2, 3, from left to right, where should the number 4 just perhaps naively go? Yeah, what do you think? Sorry? Oh, OK. So you could replace number 1. I don't really like that, though, because I'd like to keep number 1 around. But that's an option. But I'm losing, of course, information. So what else could I do if I want to add the number 4? Over there. Yeah, so I mean, it feels like if there's some ordering to these, which seems kind of a reasonable inference, that it probably belongs somewhere over here. But recall last week, as we started poking around a computer's memory, there's other stuff potentially going on. And if we sort of fill that in, ideally, we'd want to just plop the number 4 here, if we're maintaining this kind of order. But recall, in the context of your computer's memory, there might be other stuff there. Some of these garbage values that might be usable, but we don't really know or care what they are, as represented by Oscar here. But there might actually be useful data in use. Like if your program has not just a few integers in this array, but also a string that says like hello world, it could be that your computer has plopped the HELLOWORLD right after this array. Why? Well, maybe you created the array in one line of code and filled it with 1, 2, 3. Maybe the next line of code used getString, or maybe just hard-coded a string in your code for hello world. And so you kind of painted yourself into a corner, so to speak. Now, I think you might claim, well, let's just overwrite the H, but that's kind of problematic for the same reasons. We don't want to do that. So where else could the 4 go? Or how do we solve this problem if we want to add a number, and there's clearly memory available because those garbage values are junk that we don't care about anymore, so we could certainly reuse those. Where could the 4 and perhaps this whole array go? OK, so I'm hearing we could move it somewhere, maybe replace some of those garbage values. And honestly, we kind of have a lot of options. We could use any of these garbage values up here. We could use any of these down here or even further down. The point is there is plenty of memory available, as indicated by these Oscars, where we could put 4, maybe even 5, 6, or more integers. The catch is that we sort of chose poorly early on, or we just got unlucky, and 1, 2, 3 ended up back to back with some other data that we care about. All right, so that's fine. Let's go ahead and assume that we'll abstract away everything else, and we'll plop the new array in this location here. So I'm going to go ahead and copy the 1 over, the 2 over, the 3 over, and then ultimately, once I'm ready to fill the 4, I can throw away essentially the old array at this point, because I have it now entirely in duplicate, and I can populate it with the number 4. All right, so problem solved. That is a correct potential solution to this problem. But what's the trade-off? And this is something we're going to start thinking about all the more. What's the downside of having solved this problem in this way? Yeah, I'm adding a lot of running time. It took me a lot of effort to copy those additional numbers. Now, granted, it's a small array, 3 numbers, who cares? It's going to be over in the blink of an eye. But if we start talking about interesting data sets, sort of web application data sets, mobile app data sets, where you have not just a few, but maybe a few hundred, a few thousand, a few million pieces of data, this is probably kind of a suboptimal solution to just, move all your data from one place to another. Because who's to say that we're not going to paint ourselves into a new corner? And it would feel like you're wasting all of this time moving stuff around and ultimately just costing yourself a huge amount of time. In fact, if we put this now into the context of our big O notation from a few weeks back, what might the running time now of search be for an array? Let's start simple. I'll throw back a couple of weeks ago. If you're using an array, to recap, what was the running time of a search algorithm in big O notation? So maybe in the worst case. If you've got n numbers, 3 in this case, or 4, but n more generally, big O of what for search? Yeah, what do you think? Big O of n, and what's your intuition for that? OK, yeah. So if we go through each element, for instance, from left to right, then search is going to take us big O notation, big O running time. If, though, we're talking about these numbers specifically, and now I'll explicitly stipulate that, yeah, they're sorted, does that buy us anything? What would the big O notation be for searching an array in this case, be it of size 3 or 4 or n more generally? Big O of, not n, but rather? Log n, right? Because we could use, per week 0, binary search on an array like this. We'd have to deal with some rounding because there's not a perfect number of elements at the moment. But you could use binary search. Go to the middle, roughly, and then go left or right, until you find the element you care about. So search remains in big O of log n when using arrays. But what about insertion now? If we start to think about other operations, like adding a number to this array, or adding a friend to your contacts app, or Google finding another page on the internet. So insertion happens all the time. What's the running time of insert when it comes to inserting into an existing array of size n? How many steps might that take? Big O of n. It would be indeed n. Why? Because in the worst case, where you're sort of out of space, you have to allocate, it would seem, a new array, maybe taking over some of the previous garbage values. But the catch is, even though you're only inserting one new number, like the number 4, you have to copy over all the darn existing numbers into the new one. So if your original array is size n, the copying of that is going to take big O of n plus 1. But we can throw away the plus 1 because of the math we did in the past. So insert now becomes big O of n. And that might not be ideal, because if you're in the habit of inserting things frequently, that could start to add up and add up and add up. And this is why computer programs and websites and mobile apps could be slow if you're not being mindful of these kinds of trade-offs. So what about, just for good measure, omega notation? In maybe the best case, well, just to recap here, we could get lucky. And search could just take one step, because you might just get lucky and boom, the number you're looking for is right there in the middle if using binary search, or even linear search for that matter. And insert 2, if there's enough room and we didn't have to move all of those numbers 1, 2, and 3 to a new location, you could get lucky. And we could have, as someone suggested, just put the number 4 right there at the end. And if we don't get lucky, it might take n steps. If we do get lucky, it might just take the 1 or constant number of steps. In fact, let me go ahead and do this. How about we do something like this? Let me switch over to some code here. Let me start to make a program called list.c. And in list.c, let's start with the old way. So we kind of follow the breadcrumbs we've laid for ourselves as follows. So in this list.c, I'm going to include standard io.h, int main void as usual. Then inside of my code here, I'm going to go ahead and give myself the first version of memory. So int list3 is now implemented at the moment in an array. So we're rewinding for now to week 2 style code. And then let me just initialize this thing. At the first location will be 1. At the next location will be 2. And at the last location will be 3. So the array is 0 indexed always. I, for just the sake of discussion, though, am putting in the numbers 1, 2, 3 like a normal person might. All right, so now let's just print these out. 4, int I gets 0, I less than 3, I plus plus. Let's go ahead now and print out using printf, %i\n. List bracket I. So very simple program, kind of inspired by what we did in week 2, just to create and then print out the contents of an array. So let's make list. So far, so good. /list. And voila, we see 1, 2, 3. Now let's start to practice some of what we're preaching with this new syntax. So let me go in now and get rid of the array version. And let me zoom out a little bit to give ourselves some more space. And now let's begin to create a list of size 3. So if I'm going to do this now dynamically, so that I'm allocating these things again and again, let me go ahead and do this. So let me give myself a list that's of type int star equal the return value of malloc of 3 times the size of an int. So what this is going to do for me is give me enough memory for that very first picture we drew on the board, which was the array containing 1, 2, and 3, but laying the foundation to be able to resize it, which was ultimately the goal. So my syntax is a little different here. I'm going to use malloc and get memory from the so-called heap, as we called it last week, instead of using the stack by just doing the previous version where I said int list3. That is to say, this line of code from the first version is in some sense identical to this line of code in the second version, but the first line of code puts the memory on the stack automatically for me. The second line of code that I've left here now is creating an array of size 3, but it's putting it on the heap. And that's important because it was only on the heap and via this new function last week, malloc, that you can actually ask for more memory and even give it back. When you just use the first notation, int list3, you have permanently given yourself an array of size 3. You cannot add to that in code. So let me go ahead and do this. If list equals null, something went wrong, the computer's out of memory, so let's just return 1 and quit out of this program. There's nothing to see here. So just a good error check there. Now let me go ahead and initialize this list. So list bracket 0 will be 1 again. List bracket 1 will be 2. And list bracket 2 will be 3. So that's the same kind of syntax as before. And notice this equivalence. Recall that there's this relationship between chunks of memory and arrays are really just doing pointer arithmetic for you, where the square bracket notation is. So if I've asked myself here in line 5 for enough memory for 3 integers, it is perfectly OK to treat it now like an array using square bracket notation, because the computer will do the arithmetic for me and find the first location, the second, and the third. If you really want to be kind of cool and hacker-like, well, you could say list equals 1, list plus 1 equals 2, list plus 2 equals 3. That's the same thing using very explicit pointer arithmetic, which we looked at briefly last week. But this is atrocious to look at for most people. It's just not very user-friendly. It's longer to type. So most people, even when allocating memory dynamically, as I did a second ago, would just use the more familiar notation of an array. All right. So let's go on. Now suppose time passes and I realize, oh, shoot, I really wanted this array to be of size 4 instead of size 3. Now, obviously, I could just rewind and like fix the program. But suppose that this is a much larger program. And I've realized at this point that I need to be able to dynamically add more things to this array for whatever reason. Well, let me go ahead and do this. Let me just say, all right, list should actually be the result of asking for 4 chunks of memory from malloc. And then I could do something like this. List bracket 3 equals 4. Now, this is buggy potentially in a couple of ways. But let me ask first, what's really wrong first with this code? The goal at hand is to start with the array of size 3, with the 1, 2, 3, and I want to add a number 4 to it. So at the moment, in line 17, I've asked the computer for a chunk of 4 integers, just like the picture, and then I'm adding the number 4 to it. But I kind of have skipped a few steps and broken this somehow. Yeah? Yeah, I don't necessarily know where this is going to end up in memory. It's probably not going to be immediately adjacent to the previous chunk. And so, yes, even though I'm putting the number 4 there, I haven't copied the 1, the 2, or the 3 over to this chunk of memory. So, well, let me fix, well, that's actually, indeed, really the essence of the problem. I am orphaning the original chunk of memory. If you think of the picture that I drew earlier, the line of code up here on line 5 that allocates space for the initial 3 integers, this code is fine, this code is fine. But as soon as I do this, I'm clobbering the value of list and saying, no, 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 don't point at this chunk of memory. Point at this chunk of memory, at which point I've forgotten, if you will, where the original chunk of memory is. So the right way to do something like this would be a little more involved. Let me go ahead and give myself a temporary variable, and I'll literally call it temp, TMP, kind of like I did last week, so that I can now ask the computer for a completely different chunk of memory of size 4. I'm going to again say if temp equals null, I'm going to say, oh, bad things happened here, so let me just return 1. And you know what? Just to be tidy, let me free the original list before I quit. Because remember from last week, anytime you use malloc, you eventually have to use free. But this chunk of code here is just a safety check. If there's no more memory, there's nothing to see here, I'm just going to clean up my state and quit. But now, if I have asked for this chunk of memory, now I can do this. For int I get, for int I gets 0, I is less than 3, I plus plus. What if I do something like this? Temp bracket I equals list bracket I. That would seem to have the effect of copying all of the memory from one to the other. And then I think I need to do one last thing. Temp bracket 3 gets the number 4, for instance. Again, I'm kind of just hard coding the numbers for the sake of discussion. After I've done this, what could I now do? I could now set list equals to temp. And now I have updated my linked list properly. So let me go ahead and do this. For int I gets 0, I is less than 4, I plus plus. Let me go ahead and print each of these elements out with %i using list bracket I. And then I'm going to return 0 just to signify that all is successful now. So to recap, we initialize the original array of size 3 and plug in the values 1, 2, 3. Time passes. And then I realize, wait a minute, I need more space. And so I ask the computer for a second chunk of memory, this one of size 4. Just as a safety check, I make sure that temp doesn't equal null, because if it does, I'm out of memory, so I should just quit altogether. But once I'm sure that it's not null, I'm going to copy all the values from the old list into the new list. And then I'm going to add my new number at the end of that list. And then, now that I'm done playing around with this temporary variable, I'm going to remember in my list variable what the address is of this new chunk of memory. And then I'm going to print all of those values out. So at least aesthetically, when I make this new version of my list, except for my missing semicolon, let me try this again. When I make list, OK, what did I do this time? implicitly declaring a library function malloc ... What's my mistake anytime you see that kind of error? Yeah, library. So up here, I forgot to do include standard lib.h, which is where malloc lives. Let me go ahead and again do make list. There we go. So I fixed that, /list, and I should see 1, 2, 3, 4. But there's still a bug here. Does anyone see the bug or question? Oh, sorry, say again? I forgot to free the original list. And we could see this, even if not just with our own eyes or intuition, if I do something like valgrind of /list. Remember our tool from this past week. Let me increase the size of my terminal window temporarily. The output is crazy cryptic at first, but notice that I have definitely lost some number of bytes here. And indeed, it's even pointing at the line number in which some of those bytes were lost. So let me go ahead and back to my code. And indeed, I think what I need to do is before I clobber the value of list, pointing it at this new chunk of memory instead of the old, I think I now need to first proactively say free the old list of memory and then change its value. So if I now do make list and do /list, the output is still the same. And if I cross my fingers and run valgrind again after increasing my window size, hopefully here, still a bug. So better. It seems like less memory is lost. What have I now forgotten to do? I forgot to free it at the very end, too, because I still have a chunk of memory that I got from malloc. So let me go to the very bottom of the program now. And after I'm done sort of senselessly just printing this thing out, let me free the new list. And now let me do make list, /list. It still works visually. Now let's do valgrind of /list, enter. And now hopefully all heap blocks were freed. No leaks are possible. So this is perhaps the best kind of output you can see from a tool like valgrind. I used the heap, but I freed all the memory as well. So there were 2 fixes needed there. All right, any questions then on this array-based approach, the first of which is statically allocating an array, so to speak, by just hard coding the number 3. This second version now is dynamically allocating the array using not the stack but the heap. But it, too, suffers from the slowness we described earlier of having to copy all those values from one to the other. OK, hand was over here.
Why did you not have to free the temp?
Good question. Why did I not have to free the temp? I essentially did eventually, because temp was pointing at the chunk of 4 integers. But on line 33 here, I assigned list to be identical to what temp was pointing at. And so when I finally freed list, that was the same thing as freeing temp. In fact, if I wanted to, I could say free temp here, and it would be the same. But conceptually, it's sort of wrong, because at this point in the story, I should be freeing the actual list, not that temporary variable. But they were the same at that point in the story. Yeah? Good question. And long story short, everything we're doing thus far is still in the world of arrays. The only distinction we're making is that in version 1, when I said int list bracket 3 close bracket, that was an array of fixed size, so-called statically allocated on the stack as per last week. This version now is still dealing with arrays, but I'm kind of flexing my muscles and using dynamic memory allocation so that I can still use an array per the first pictures we started talking about, but I can at least grow the array if I want. So we haven't even now solved this even better, in a sense, with linked list. That's going to come next. Yeah? How am I able to free list? I freed the original address of list. I then changed what list is storing. I'm moving its arrow to a new chunk of memory. And that is perfectly reasonable for me to now manipulate, because now list is pointing at the same value of temp. And temp is what was given the return value of malloc the second time. So that chunk of memory is valid. So these are just squares on the board, right? There's just pointers inside of them. So what I'm technically saying is I'm not freeing list per se. I am freeing the chunk of memory that begins at the address currently in list. Therefore, if a few lines later I change what the address is in list, totally reasonable to then touch that memory and eventually free it later, because you're not freeing the variable per se. You're freeing the address in the variable. Good distinction. All right, so let me back up here and just now make one final edit. So let's finish this with one final improvement here, because it turns out there's a somewhat better way to actually resize an array as we've been doing here. And there's another function in standard lib that's called realloc, for reallocate. And I'm just going to go in and make a little bit of a change here so that I can do the following. Let me go ahead and first comment this now, just so we can keep track of what's been going on this whole time. So dynamically allocate an array of size 3. Assign 3 numbers to that array. Time passes. Allocate new array of size 4. Copy numbers from old array into new array. And add 4th number to new array. Free old array. Remember, if you will, new array using my same list variable. And now print new array. Free new array. Hopefully that helps. And we'll post this code online after too, which tells a more explicit story. So it turns out that we can reduce some of the labor involved with this. Not so much with the printing here, but with this copying. Turns out C does have a function called realloc that can actually handle the resizing of an array for you as follows. I'm going to scroll up to where I previously allocated a new array of size 4. And I'm instead going to say this: resize old array to be of size 4. Now, previously, this wasn't necessarily possible, because recall that we had painted ourselves into a corner with the example on the screen where hello world happened to be right after the original array. But let me do this. Let me use realloc for reallocate and pass in not just the size of memory we want this time, but also the address that we want to resize, which again is this array called list. All right, the code thereafter is pretty much the same. But what I don't need to do is this. So realloc is a pretty handy function that will do the following. If at the very beginning of class, when we had 1, 2, 3 on the board, and someone's instinct was to just plop the 4 right at the end of the list, if there's available memory, realloc will just do that. And boom, it will just grow the array for you in the computer's memory. If, though, it realizes, sorry, there's already a string like hello world or something else there, realloc will handle the trouble of moving that whole array from one chunk of memory originally to a new chunk of memory. And then realloc will return to you the address of that new chunk of memory. And it will handle the process of freeing the old chunk for you, so you do not need to do this yourself. So in fact, let me go ahead and get rid of this as well. So realloc just condenses a lot of what we just did into a single function, whereby realloc handles it for you. All right, so that's the final improvement on this array-based approach. So what now, knowing what your memory is, what can we now do with it that solves that kind of problem? Because the world is going to get really slow, and our apps and our phones and our computers are going to get really slow if we're just constantly wasting time moving things around in memory. What could we perhaps do instead? Well, there's just one new piece of syntax today that builds on these 3 pieces of syntax from the past. Recall that we've looked at struct, which is a keyword in C that just lets you invent your own structure, your own variable, if you will, in conjunction with typedef, which lets you say a person has a name and a number or something like that. Or a candidate has a name and some number of votes. You can encapsulate multiple pieces of data inside of just one using struct. What did we use the dot notation for now a couple times? What does the dot operator do in C? Perfect, to access the field inside of a structure. So if you've got a person with a name and a number, you could say something like person.name or person.number if person is the name of one such variable. Star, of course, we've seen now in a few ways. Like way back in week 1, we saw it as like multiplication. Last week, we began to see it in the context of pointers, whereby you use it to declare a pointer, like int star p or something like that. But we also saw it in one other context, which was like the opposite, which was the dereference operator, which says if this is an address, that is, if this is a variable like a pointer, and you put a star in front of it then with no int or no char, no data type in front of it, that means go to that address. And it dereferences the pointer and goes to that location. So it turns out that using these 3 building blocks, you can actually start to now use your computer's memory almost any way you want. And even next week when we transition to Python and you start to get a lot of features for free, like a single line of code will just do so much more in Python than it does in C. It boils down to those basic primitives. And just so you've seen it already, it turns out that it's so common in C to use this operator to go inside of a structure and this operator to go to an address that there's shorthand notation for it, aka syntactic sugar, that literally looks like an arrow. So recall last week I was in the habit of pointing, even with the big foam finger. This arrow notation, a hyphen and an angled bracket, denotes going to an address and looking at a field inside of it. But we'll see this in practice in just a bit. So what might be the solution now to this problem we saw a moment ago, whereby we had painted ourselves into a corner and our memory a few moments ago looked like this? We could just copy the whole existing array to a new location, add the 4, and go about our business. What would another, perhaps better solution longer term be that doesn't require constantly moving stuff around? Maybe hang in there for your instincts. If you know the sort of buzz phrase we're looking for from past experience, hang in there. But if we want to avoid moving the 1, 2, and the 3, but we still want to be able to add endless amounts of data, what could we do? Yeah, so maybe create some kind of list using pointers that just kind of point at a new location, right? In an ideal world, even though this piece of memory is being used by this h in the string hello world, maybe we could somehow use a pointer from last week, like an arrow, that says after the 3, oh, I don't know, go down over here to this location in memory. And you just kind of stitch together these integers in memory so that each one leads to the next. It's not necessarily the case that it's literally back to back. That would have the downside, it would seem, of costing us a little bit of space. Like a pointer, which recall takes up some amount of space, typically 8 bytes or 64 bits. But I don't have to copy potentially a huge amount of data just to add one more number. And so these things do have a name. And indeed, these things are what generally would be called a linked list. A linked list captures exactly that kind of intuition of linking together things in memory. So let's take a look at an example. Here's computer's memory in the abstract. Suppose that I'm trying to create an array. No, let's generalize it as a list now of numbers. An array has a very specific meaning. It's memory that's contiguous, back to back to back. At the end of the day, I, as the programmer, just care about the data, 1, 2, 3, 4, and so forth. I don't really care how it's stored until I don't care how it's stored when I'm writing the code. I just want it to work at the end of the day. So suppose that I first insert my number 1, and who knows, it ends up there at location 0x123 for the sake of discussion. All right, maybe there's something already here, and heck, maybe there's something already here, but there's plenty of other options for where this thing can go. And suppose that for the sake of discussion, the first available spot for the next number happens to be over here at location 0x456 for the sake of discussion. So that's where I'm going to plop the number 2. And where might the number 3 end up? Oh, I don't know, maybe down over there at 0x789. The point being, I don't know what is or really care about everything else that's in the computer's memory. I just care that there are at least 3 locations available where I can put my 1, my 2, and my 3. But the catch is, now that we're not using an array, we can't just naively assume that you just add 1 to an index and boom, you're at the next number. Add 2 to an index and boom, you're at the next number. Now you kind of have to leave these little breadcrumbs or use the arrow notation to kind of lead from one to the other. And sometimes it might be close, a few bytes away. Maybe it's a whole gigabyte away in an even bigger computer's memory. So how might I do this? Like, where do these pointers go as you proposed? Right? All I have access to here are bytes. I've already stored the 1, the 2, and the 3. So what more should I do? OK, yeah, so you put the pointers right next to these numbers. So let me at least plan ahead so that when I ask the computer, like malloc, recall from last week, for some memory, I don't just ask it now for space for just the number. Let me start getting into the habit of asking malloc for enough space for the number and a pointer to another such number. So it's a little more aggressive of me to ask for more memory, but I'm kind of planning ahead. And here's an example of a trade-off. Almost any time in CS, when you start using more space, you can save time. Or if you try to conserve space, you might have to lose time. It's being that kind of trade-off there. So how might I solve this? Well, let me abstract this away, and either next to or below, I'm just drawing it vertically just for the sake of discussion, so the arrows are a bit prettier. I've asked malloc for now twice as much space, it would seem, than I previously needed. But I'm going to use this second chunk of memory to refer to the next number. And I'm going to use this chunk of memory to refer to the next, essentially stitching this thing together. So what should go in this first box? Well, I claim the number, 0x456. And it's written in hex because it represents a memory address. But this is the equivalent of sort of drawing an arrow from one to the other. As a little check here, what should go in this second box if the goal is to stitch these together in order, 1, 2, 3? Feel free to just shout this out. OK, OK, that worked well. So 0x789, indeed. And you can't do that with hands because I can't count that fast. So 0x789 should go here because that's like a little breadcrumb to the next. And then we don't really have terribly many possibilities here. This has to have a value, right? Because at the end of the day, it's got to use its 64 bits in some way. So what value should go here if this is the end of this list? So it could be 0x123, the implication being that it would kind of be a cyclical list, which is OK, but potentially problematic. If any of you have accidentally sort of lost control over your code space because you had an infinite loop, this would seem a very easy way to give yourself the accidental probability of an infinite loop. What might be simpler than that and ward that off? Say again? So just the null character, not NUL confusingly, which is at the end of strings, but NULL as we introduced it last week, which is the same as OX0. So this is just a special value that programmers decades ago decided that if you store the address 0, that's not a valid address. There's never going to be anything useful at OX0. Therefore, it's a sentinel value, just a special value that indicates that's it. There's nowhere further to go. It's OK to come back to your suggestion of making a cyclical list, but we'd better be smart enough to maybe remember where did the list start so that you can detect cycles if you start looping around in this structure otherwise. All right, but these addresses, who really cares at the end of the day? If we abstract this away, it really just now looks like this. And indeed, this is how most anyone would draw this on a whiteboard if having a discussion at work talking about what data structure we should use to solve some problem in the real world. We don't care generally about the addresses. We care that in code we can access them. But in terms of the concept alone, this would be perhaps the right way to think about this. All right, let me pause here to see if there's any questions on this idea of creating a linked list in memory by just storing not just the numbers like 1, 2, 3, but twice as much data so that you have little breadcrumbs in the form of pointers that can lead you from one to the next. Any questions on these linked lists? Any questions? No? All right. Oh, yeah, over here. This does take more memory than an array because I now need space for these pointers. And to be clear, I technically didn't really draw this to scale. Thus far in the class, we've generally thought about integers like 1, 2, and 3 as being 4 bytes or 32 bits. I made the claim last week that on modern computers, pointers tend to be 8 bytes or 64 bits. So technically, this box should actually be a little bigger. It was just going to look a little stupid in the picture. So I abstracted it away. But indeed, you're using more space as a result. Oh, how does the computer identify useful data from used data? So for instance, garbage values or non-garbage values. For now, think of that as the job of malloc. So when you ask malloc for memory, as we started to last week, malloc keeps track of the addresses of the memory it has handed to you as valid values. The other type of memory you use, not just from the heap, because recall we briefly discussed that malloc uses space from the heap, which was drawn at the top of the picture pointing down. There's also stack memory, which is where all of your local variables go and where all of the memory used by individual functions go. And that was drawn in the picture as working its way up. That's just an artist's rendition of direction. The compiler essentially will also help keep track of which values are valid or not inside of the stack, or really the underlying code that you've written will keep track of that for you. So it's managed for you at that point. All right, good question. Sorry, it took me a bit to catch on. So let's now translate this to actual code. How could we implement this idea of, let's call these things nodes. And that's a term of art in CS. Whenever you have some kind of data structure that encapsulates information, node, N-O-D-E is the generic term for that. So each of these might be said to be a node. Well, how can we do this? Well, a couple of weeks ago, we saw how we could represent something like a student or a candidate. And a student, or rather a person, we said, has a name and a number. And we used a few pieces of syntax here. One, we used the struct keyword, which gives us a data structure. We used typedef, which defines the name person to be our new data type, representing that whole structure. So we probably have the right ingredients here to build up this thing called a node. And just to be clear, what should go inside of one of these nodes, do we think? It's not going to be a name or a number, obviously, but what should a node have in terms of those fields, perhaps? Yeah. So a number, like a number and a pointer in some form. So let's translate this to actual code. So let's rename person to node to capture this notion here. And the number is easy. If it's just going to be an int, that's fine. We can just say int number or int n or whatever you want to call that particular field. The next one's a little non-obvious, and this is where things get a little weird at first. But in retrospect, it should all kind of fit together. Let me propose that ideally, we would say something like node star next. And I could call the word next anything I want. Next just means what comes after me is the notion I'm using it at. So a lot of CS people would just use next to represent the name of this pointer. But there's a catch here. C and C compilers are pretty naive, recall. They only look at code top to bottom, left to right. And anytime they encounter a word they have never seen before, bad things happen. Like you can't compile your code, you get some cryptic error message or the like. And that seems to be about to happen here. Because if the compiler is reading this code from top to bottom, it's going to say, oh, inside of this struct should be a variable called next, which is of type node star. What the heck is a node? Because it literally does not find out until 2 lines later after that semicolon. So the way to avoid this, which we haven't quite seen before, is that you can temporarily name this whole thing up here struct node. And then down here inside of the data structure, you say struct node star. And then you leave the rest alone. This is kind of a workaround. This is possible because now you're teaching the compiler from the first line that here comes a data structure called struct node. Down here, you're shortening the name of this whole thing to just node. Why? It's just a little more convenient than having to write struct everywhere. But you do have to write struct node star inside of the data structure. But that's OK because it's already come into existence now as of that first line of code. So that's the only fundamental difference between what we did last week with a person or a candidate. We just now have to use this struct workaround syntactically. All right, yeah, question? Why is the next variable a struct node star pointer and not an int star pointer, for instance? So think about the picture we are trying to draw. Technically, yes. Each of these arrows I deliberately drew is pointing at the number. But that's not alone. They need to point at the whole data structure in memory because the computer ultimately and the compiler in turn needs to know that this chunk of memory is not just an int. It is a whole node. Inside of a node is a number and also another pointer. So when you draw these arrows, it would be incorrect to point at just the number because that throws away information. That would leave the compiler wondering, OK, I'm at a number. Where the heck is the pointer? You have to tell it that it's pointing at a whole node so it knows a few bytes away is that corresponding pointer. Good question. Yeah? Really good question. It would seem that just as copying the array earlier required twice as much memory because we copied from old to new, so technically twice as much plus 1 for the new number. Here, too, it looks like we're using twice as much memory also. And to my comment earlier, it's even more than twice as much memory because these pointers are 8 bytes and not just 4 bytes like a typical integer is. The differences are these. In the context of the array, you were using that memory temporarily. So yes, you needed twice as much memory, but then you were quickly freeing the original array. So you weren't consuming long-term more memory than you might need. The difference here, too, is that, as we'll see in a moment, it turns out it's going to be relatively quick for me, potentially, to insert new numbers in here because I'm not going to have to do a huge amount of copying. And even though I might still have to follow all of these arrows, which is going to take some amount of time, I'm not going to have to be asking for more memory, freeing more memory. And certain operations in a computer, anything involving asking for or giving back memory tends to be slower. So we get to avoid that situation as well. There's going to be some downsides, though. This is not all upside, but we'll see in a bit just what some of those trade-offs actually are. All right, so from here, if we go back to the structure in code as we left it, let's start to now build up a linked list with some actual code. How do you go about in C representing a linked list in code? Well, at the moment, it would actually be as simple as this. You declare a variable called list, for instance, that itself stores the address of a node. That's what node star means, the address of a node. So if you want to store a linked list in memory, you just create a variable called list or whatever else, and you just say that this variable is going to be pointing at the first node in a list, wherever it happens to end up. Because malloc is ultimately going to be the tool that we use just to go get at any one particular node in memory. All right, so let's actually do this in pictorial form. When you write a line of code, like I just did here, and I do not initialize it to anything with the assignment operator, an equal sign, it does exist in memory as a box, as I'll draw it here, called list. But I've deliberately drawn Oscar inside of it. Why? To connote what exactly? It's a garbage value. I have been allocated the variable in memory called list, which is going to give me 64 bits or 8 bytes somewhere drawn here with this box. But if I myself have not used the assignment operator, it's not going to get magically initialized to any particular address for me. It's not going to even give me a node. This is literally just going to be an address of a future node that exists. So what would be a solution here? Suppose that I'm beginning to create my linked list, but I don't have any nodes yet. What would be a sensible thing to initialize list to, perhaps? Yeah, again? So just null, right? When in doubt with pointers, generally it's a good thing to initialize things to null. So at least it's not a garbage value. It's a known value. Invalid, yes, but it's a special value you can then check for with a conditional or the like. So this might be a better way to create a linked list even before you've inserted any numbers into the thing itself. All right, so after that, how can we go about adding something to this linked list? So now the story looks like this. Oscar is gone because inside of this box is all 0 bits, just because it's nice and clean. And this represents an empty linked list. Well, if I want to add the number 1 to this linked list, what could I do? Well, perhaps I could start with code like this, borrowing inspiration from last week. Let's ask malloc for enough space for the size of a node. And this kind of gets to your question earlier, like what is it I'm manipulating here? I don't just need space for an int, and I don't just need space for a pointer. I need space for both, and I gave that thing a name, node. So size of node figures out and does the arithmetic for me and gives me back the right number of bytes. This then stores the address of that chunk of memory in what I'll temporarily call n, just to represent a generic new node. And it's of type node star, because just like last week when I asked malloc for enough space for an int, and I stored it in an int star pointer, this week, if I'm asking for memory for a node, I'm storing it in a node star pointer. So technically nothing new there, except for this new term of art and data structure called node. All right, so what does that do for me? It essentially draws a picture like this in memory. I still have my list variable from my previous line of code initialized to null, and that's why I've drawn it blank. I also now have a temporary variable called n, which I initialized to the return value of malloc, which gave me one of these nodes in memory. But I've drawn it having garbage values too, because I don't know what int is there. I don't know what pointer is there. It's garbage values because malloc does not magically initialize memory for me. There is another function for that. But malloc alone just says, sure, use this chunk of memory, deal with whatever's there. So how could I go about initializing this to known values? Well, suppose I want to insert the number 1 and then leave it at that, a list of size 1. I could do something like this. And this is where you have to think back to some of these basics. My conditional here is asking the question if n does not equal null. So that is, if malloc gave me valid memory, and I don't have to quit altogether because my computer's out of memory, if n does not equal null, that is, it equals a valid address, I'm going to go ahead and do this. And this is cryptic looking syntax now. But does someone want to take a stab at translating this inside line of code to English in some sense? How might you explain what that inner line of code is doing? Star n dot number equals 1. Let me go further back. No? OK, over here. Yeah. Perfect. The place that n is pointing to, set it equal to 1. Or using the vernacular of going there, go to the address in n and set its number field to 1. However you want to think about it, that's fine. But the star, again, is the dereference operator here. And we're doing the parentheses, which we haven't needed to do before because we haven't dealt with pointers and data structures together until today. This just means go there first. And then once you're there, go access number. You don't want to do one thing before the other. So this is just enforcing order of operations. The parentheses, just like in grade school math. All right, so this line of code is cryptic. It's ugly. It's not something most people easily remember. Thankfully, there's that syntactic sugar that simplifies this line of code to just this. And this, even though it's new to you today, should eventually feel a little more familiar because this now is shorthand notation for saying start at n, go there as by following the arrow. And when you get there, change the number field, in this case, to 1. So most people would not write code like this. It's just ugly. It's a couple extra keystrokes. This just looks more like the artist's renditions we've been talking about and how most CS people would think about pointers as really just being arrows in some form. All right, so what have we just done? The picture now, after setting number to 1, looks a little something like this. So there's still one step missing. And that's, of course, to initialize, it would seem, the pointer in this new node to something known, like null. So I bet we could do this like this. With a different line of code, I'm just going to say if n does not equal null, then set n's next field to null. Or more pedantically, go to n, follow the arrow, and then update the next field that you find there to equal null. And again, this is just doing some nice bookkeeping. Technically speaking, we might not need to set this to null if we're going to keep adding more and more numbers to it. But I'm doing it step by step so that I have a very clean picture and there's no bugs in my code at this point. But I'm still not done. There's one last thing I'm going to have to do here. If the goal ultimately was to insert the number 1 into my linked list, what's the last step I should perhaps do here? Just in English is fine. Yeah. Yes, I now need to update the actual variable that represents my linked list to point at this brand new node that is now perfectly initialized as having an integer and a null pointer. Yeah, technically this is already pointing there, but I described this deliberately earlier as being temporary. I just needed this to get it back from malloc and sort of clean things up initially. This is the long-term variable I care about, so I'm going to want to do something simple like this. List equals n. And this seems a little weird that list equals n, but again, think about what's inside this box. At the moment, this is null, because there is no linked list at the beginning of our story. N is the address of the beginning, and it turns out end of our linked list. So it stands to reason that if you set list equal to n, that has the effect of copying this address up here, or really just copying the arrow into that same location so that now the picture looks like this. And heck, if this was a temporary variable, it will eventually go away, and now this is the picture. So kind of an annoying number of steps, certainly to walk through verbally like this. But it's just malloc to give yourself a node, initialize the 1, the 2 fields inside of it, update the linked list, and boom, you're on your way. I didn't have to copy anything. I just had to insert something in this case. All right, let me pause here to see if there's any questions on those steps. And we'll see before long it all in context with some larger code. Yes, I drew them separately just for the sake of the voiceover of doing each thing very methodically. In real code, as we'll transition to now, I could have and should have just done it all inside of one conditional after checking if n is not equal to null. I could set number to a value like 1, and I could set the pointer itself to something like null. All right, well, let's translate then this into some similar code that allows us to build up a linked list now using code similar in spirit to before, but now using this new primitive. So I'm going to go back into VS Code here. I'm going to go ahead and now and delete the entirety of this old version that was entirely array-based. And now inside of my main function, I'm going to go ahead and first do this. I'm going to first give myself a list of size 0, and I'm going to call that node star list. And I'm going to initialize that to null as we proposed earlier. But I'm also now going to have to take the additional step of defining what this node is. So recall that I might do something like typedef struct node. Inside of this struct node, I'm going to have a number, which I'll call number of type int. And I'm going to have a structure called node with a star that says the next pointer is called next. And I'm going to call this whole thing more succinctly node. instead of struct node. Now, as an aside, for those of you wondering what the difference really is between struct and node, technically, I could do something like this, not use typedef, and not use the word node alone. This syntax here would actually create for me a new data type called verbosely struct node. And I could use this throughout my code saying struct node, struct node. It just gets a little tedious, and it would be nicer just to refer to this thing more simplistically as a node. So what typedef has been doing for us is it, again, lets us invent our own word that's even more succinct. And this just has the effect now of calling this whole thing node without the need subsequently to keep saying struct all over the place, just FYI. All right, so now that this thing exists in main, let's go ahead and do this. Let's add a number to list. And to do this, I'm going to give myself a temporary variable. I'll call it n for consistency. I'm going to use malloc to give myself the size of a node, just like in our slides. And then I'm going to do a little safety check. If n equals null, I'm going to do the opposite of the slides. I'm just going to quit out of this program because there's nothing useful to be done at this point. But most likely my computer's not going to run out of memory, so I'm going to assume we can keep going with some of the logic here. If n does not equal null, and that is it's a valid memory address, I'm going to say n bracket, and I'm going to build this up backwards. Well, that's OK. Let's go ahead and do this. N bracket number equals 1, and then n bracket or arrow next equals null. And now update list to point to new node. List equals n. So at this point in the story, we've essentially constructed what was that first picture, which looks like this. This is the corresponding code via which we built up this node in memory. Suppose now we want to add the number 2 to the list. So let's do this again. Add a number to list. How might I do this? Well, I don't need to redeclare n because I can use the same temporary variables before. So this time I'm just going to say n equals malloc and the size of a node. I'm again going to have my safety check. So if n equals null, then let's just quit out of this altogether. But I have to be a little more careful now. Technically speaking, what do I still need to do before I quit out of my program to be really proper? Free the memory that did succeed a little higher up. So I think it suffices to free what is now called list way at the top. All right, now if all was well, though, let's go ahead and say n bracket number equals 2. And now n arrow next equals null. And now let's go ahead and add it to the list. If I go ahead and do list arrow next equals n, I think what we've just done is build up the equivalent now of this in the computer's memory by going to the list field's next field, which is synonymous with the 1 node's bottommost box, and store the address of what was n, which a moment ago looked like this. And I'm just throwing away in the picture the temporary variable. All right, one last thing to do. Let me go down here and say add a number to list, n equals malloc. Let's do it one more time, size of node. And clearly, in a real program, we might want to start using a loop and do this dynamically or a function, because it's a lot of repetition now. But just to go through the syntax here, this is fine. If n equals null, out of memory for some reason, let's return 1. But we should free the list itself and even the second node, list bracket next, but I've deliberately done this poorly. All right, this is a little more subtle now. And let me get rid of the highlighting just so it's a little more visible. If n happens to equal null, and something really just went wrong there out of memory, why am I freeing 2 addresses now? And again, it's not that I'm freeing those variables per se. I'm freeing the addresses in those variables. But there's also a bug with my code here, and it's subtle. Let me ask more pointedly. This line here, 43, what is that freeing specifically? Can I go to you? I'm freeing, not so. That's OK. I'm not freeing list 2 times. Technically, I'm freeing list once and list next once. But let me just ask the more explicit question. What am I freeing with line 43 at the moment? Which node? I think node number 1. Why? Because if 1 is at the beginning of the list contains the address of that number 1 node. And so this frees that node. This line of code, you might think now intuitively, OK, it's probably freeing the node number 2. But this is bad. And this is subtle. Valgrind might help you catch this. But by eyeing it, it's not necessarily obvious. You should never touch memory that you have already freed. And so the fact that I did this in this order, very bad. Because I'm telling the operating system, I don't need the list address anymore. Do with it what you want. And then literally one line later, you're saying, wait a minute, let me actually go to that address for a moment and look at the next field of that first node. It's too late. You've already sort of given up control over the node. So it's an easy fix in this case, logically. But we should be freeing the second node first and then the first one so that we're doing it in essentially reverse order. And again, Valgrind would help you catch that. But that's the kind of thing one needs to be careful about when touching memory at all. You cannot touch memory after you've freed it. But here is my last step. Let me go ahead and update the number field of number field of n to be 3, the next node of n to be null, and then just like in the slide earlier, I think I can do list next equals n, and that has the effect now of building up in the computer's memory essentially this data structure. Very manually, very pedantically, like in a better world, we'd have a loop and some functions that are automating this process. But for now, we're doing it just to play around with the syntax. So at this point, unfortunately, suppose I want to print the numbers. It's no longer as easy as int I equals 0, I less than 3, I plus plus, because you cannot just do something like this. Because pointer arithmetic no longer comes into play when it's you who are stitching together the data structure in memory. In all of our past examples with arrays, you've been trusting that all of the bytes in the array are back to back to back. So it's perfectly reasonable for the compiler and the computer to just figure out, oh, well, if you want bracket 0, that's at the beginning. Bracket 1, it's one location over. Bracket 2, it's one location over. This is way less obvious now, because even though you might want to go to the first element in the linked list or the second or the third, you can't just jump to those arithmetically by doing a bit of math. Instead, you have to follow all of those arrows. So with linked lists, you can't use this square bracket notation anymore because one node might be here, over here, over here, over here. You can't just use some simple offset. So I think our code's going to have to be a little fancier. And this might look scary at first, but it's just an application of some of the basic definitions here. Let me do a for loop that actually uses a node star variable initialized to the list itself. I'm going to keep doing this so long as temp does not equal null. And on each iteration of this loop, I'm going to update temp to be whatever temp arrow next is. And I'll rewind in a moment and explain in more detail. But when I print something here with printf, I can still use %i because it's still a number at the end of the day. But what I want to print out is the number in this temporary variable. So maybe the ugliest for loop we've ever seen, because it's mixing not just the idea of a for loop, which itself was a bit cryptic weeks ago, but now I'm using pointers instead of integers. But I'm not violating the definition of a for loop. Recall that a for loop has 3 main things in parentheses. What do you want to initialize first? What condition do you want to keep checking again and again? And what update do you want to make on every iteration of the loop? So with that basic definition in mind, this is giving me a temporary variable called temp that is initialized to the beginning of the loop. So it's like pointing my finger at the number 1 node. Then I'm asking the question, does temp not equal null? Well, hopefully not, because I'm pointing at a valid node, that is the number 1 node. So of course it doesn't equal null yet. Null won't be until we get to the end of the list. So what do? I start at this temp variable. I follow the arrow and go to the number field therein. What do I then do? The for loop says change temp to be whatever is at temp by following the arrow and grabbing the next field. That then has the result of being checked against this conditional. Nope, of course it doesn't equal null because the second node is the number 2 node. Null is still at the very end, so I print out the number 2. Next step, I update temp one more time to be whatever is next. That then does not yet equal null, so I go ahead and print out the number 3 node. Then one last time, I update temp to be whatever temp is in the next field. But after 1, 2, 3, that last next field is null. And so I break out of this for loop altogether. So if I do this in pictorial form, All we're doing, if I now use my finger to represent the temp variable, I initialize temp to be whatever list is, so it points here. That's obviously not null, so I print out whatever is at temp, follow the arrow in number, and I print that out. Then I update temp to point here. Then I update temp to point here. Then I update temp to point here. Wait, that's null. The for loop ends. So again, admittedly much more cryptic than our familiar int I equals 0 and so forth, but it's just a different utilization of the for loop syntax. Yes?
How does it happen that you're always printing out the numbers? It seems to me that you have to.
Good question. How is it that I'm actually printing numbers and not printing out addresses instead? The compiler is helping me here. Because I taught it in the very beginning of my program what a node is, which looks like this here, the compiler knows that a node has a number field and an x field. Down here in the for loop, because I'm iterating using a node star pointer and not an int star pointer, the compiler knows that anytime I'm pointing at something, I'm pointing at the whole node. It doesn't matter where specifically in the rectangle I'm pointing per se. It's ultimately pointing at the whole node itself. And the fact that I then use temp arrow number means, OK, adjust your finger slightly so you're literally pointing at the number field and not the next field. So that's sufficient information for the computer to distinguish the two. Good question. Other questions then on this approach here? Yeah, in back. How would I use a for loop to add elements to a linked list? You will do something like this, if I may, in problem set 5. We will give you some of the scaffolding for doing this. But in this coming week's materials, will we guide you to that? But let me not spoil it just yet. Fair question, though. Yeah?
So I had a question about line 49.
OK. Good question. Is line 49 acceptable even if we freed it earlier? We didn't free it in line 43 in this case, right? You can only reach line 49 if n does not equal null and you do not return on line 45. So that's safe. I was only doing those freeing if I knew on line 45 that I'm out of here anyway at that point. Good question. And yeah. Correct. You're asking about temp because it's in a for loop. Does that mean you don't have to free it? You never have to free pointers per se. You should only free addresses that were returned to you by malloc. So I haven't finished the program, to be fair. But you're not freeing variables. You're not freeing like fields. You are freeing specific addresses, whatever they may be. So the last thing, and I was kind of stalling on showing this just because it too is a little cryptic. Here is how you can free now a whole linked list. In the world of arrays, recall, it was so easy. You just say free list, you return 0, and you're done. Not with a linked list, because again, the computer doesn't know what you have stitched together using all of these pointers all over the computer's memory. You need to follow those arrows. So one way to do this would be as follows. While the list itself is not null, so while there's a list to be freed, what do I want to do? I'm going to give myself a temporary variable called temp again. And it's a different temp because it's in a different scope. It's inside of the while loop instead of the for loop a few lines earlier. I am going to initialize temp to be the address of the next node, just so I can get one step ahead of things. Why am I doing this? Because now I can boldly free the list itself, which does not mean the whole list. Again, I'm freeing the address in list, which is the address of the number 1 node. That's what list is. It's just the address of the number 1 node. So if I first use temp to point at the number 2, slightly in the middle of the picture, then it is safe for me on line 61 at the moment to free list. That is the address of the first node. Now I'm going to say, all right, once I've freed the first node in the list, I can update the list itself to be literally temp. And now the loop repeats. So what's happening here, if you think about this picture, temp is initially pointing at not the list, but list arrow next. So temp, represented by my right hand here, is pointing at the number 2. Totally safe and reasonable to free now the list itself, aka the address of the number 1 node. That has the effect of just throwing away the number 1 node, telling the computer you can reuse that memory for you. The last line of code I wrote updated list to point at the number 2, at which point my loop proceeded to do the exact same thing again. And only once my finger is literally pointing at nowhere, the null symbol, will the loop, by nature of a while loop, as I'll toggle back to, break out, and there's nothing more to be freed. So again, what you'll see ultimately in problem set 5, more on that later, is an opportunity to play around with just this syntax, but also these ideas. But again, even though the syntax is admittedly pretty cryptic, we're still using basics like these for loops or while loops. We're just starting to now follow explicit addresses rather than letting the computer do all of the arithmetic for us, as we previously benefited from. At the very end of this thing, I'm going to return 0 as though all is well. And I think then we're good to go. All right, questions on this linked list code now? And again, we'll walk through this again in the coming week's spec. Yeah? Sure. Can we explain this while loop here for freeing the list? So notice that first I'm just asking the obvious question, is the list null? Because if it is, there's no work to be done. However, while the list is not null, according to line 58, what do we want to do? I want to create a temporary variable that points at the same thing that list arrow next is pointing at. So what does that mean? Here's list. List arrow next is whatever this thing is here. So if my right hand represents the temporary variable, I'm literally pointing at the same thing as the list is itself. The next line of code, recall, was free the list. And unlike in our world of arrays, like half an hour ago, where that just meant free the whole darn list, you now have taken over control over the computer's memory with a linked list in ways that you didn't with the array. The computer knew how to free the whole array because you malloc the whole thing at once. You are now mallocing the linked list one node at a time. And the operating system does not keep track of for you where all these nodes are. So when you free list, you are literally freeing the value of the list variable, which is just this first node here. Then my last line of code, which I'll flip back to in a second, updates list to now ignore the freed memory and point at 2. And the story then repeats. So again, it's just a very pedantic way of using this new syntax of star notation and the arrow notation and the like to sort of do the equivalent of walking down all of these arrows, following all of these breadcrumbs. But it does take, admittedly, some getting used to. Syntax you only have to do 1 week. But again, next week in Python, will we begin to abstract a lot of this complexity away. But none of this complexity is going away. It's just that someone else, the authors of Python, for instance, will have automated this kind of stuff for us. The goal this week is to understand what it is we're going to get for free, so to speak, next week. All right, questions on these linked lists? All right, oh yeah, in back. Fair question. Let me summarize as, could we have freed this with a for loop? Absolutely. It just is a matter of style. It's a little more elegant to do it in a while loop, according to me, but other people will reasonably disagree. Anything you can do with a while loop, you can do with a for loop, and vice versa. Do while loops, recall, are a little different, but they will always do at least one thing. But for loops and while loops behave the same in this case. Sure. Other questions? All right, well, let's just vary things a little bit here just to see what some of the pitfalls might now be without getting into the weeds of code. Indeed, we'll try to save some of that for problem set 5's exploration. But instead, let's imagine that we want to create a list here of our own. I can offer in exchange for a few volunteers some foam fingers to bring to the next game, perhaps. Could we get maybe just one volunteer first? Come on up. You will be our linked list from the get-go. What's your name? Pedro. Pedro, come on up. All right, thank you to Pedro. And if you want to just stand roughly over here, but you are a null pointer, so just point sort of at the ground as though you're pointing at 0. All right, so Pedro is our linked list of size 0, which pictorially might look a little something like this for consistency with our past pictures. Now suppose that we want to go ahead and malloc, how about the number 2? Can we get a volunteer to be on camera here? OK, you kind of jumped out of your seat. Do you want to come up? OK, you really want the foam finger, I see. All right, round of applause, sure. OK, and what's your name?
Caleb.
Say again?
Caleb.
Haywen?
Caleb.
Caleb. Yeah. Caleb, sorry. All right, so here is your number 2 for your number field, and here is your pointer. And come on, let's say that there was room for Caleb, like right there. That's perfect. So Caleb got malloced, if you will, over here. So now if we want to insert Caleb and the number 2 into this linked list, well, what do we need to do? I already initialized you to 2, and pointing as you are to the ground means you're initialized to null for your next field. Pedro, what should you? Perfect. What should Pedro do? Point. That's fine too. So Pedro's now pointing at the list, so now our list looks a little something like this. So far, so good, all is well. So the first couple of these will be pretty straightforward. Let's insert one more. If anyone really wants another foam finger here, how about right in the middle? Come on down. And just in anticipation, how about let's malloc someone else? OK, your friends are pointing at you. Do you want to come down too preemptively? This is a pool of memory, if you will. What's your name? Hannah. All right, Hannah. You are number 4. And hang there for just a moment. All right, so we've just malloced Hannah. And Hannah, how about Hannah, suppose you ended up over there in just some random location. All right, so what should we now do if the goal is to keep these things sorted? How about? So Pedro, do you have to update yourself? No? All right, Caleb, what do you have to do? OK, and Hannah, what should you be doing? I would just, it's just you for now, so point at the ground representing null. OK, so again, demonstrating the fact that unlike in past weeks where we had our nice clean array back to back to back contiguously, these guys are deliberately all over the stage. So let's malloc another. How about number 5? What's your name? Jonathan. All right, Jonathan, you are our number 5. And pick your favorite place in memory. OK. All right, so Jonathan's now over there, and Hannah's over there. So 5. We want to point Hannah at number 5. So you, of course, are going to point there. And where should you be pointing? Down to represent null as well. OK, so pretty straightforward. But now things get a little interesting. And here we'll use a chance to, without the weeds of code, point out how order of operations is really going to matter. Suppose that I next want to allocate, say, the number 1. And I want to insert the number 1 into this list. Yes, this is what the code would look like. But if we sort of act this out, could we get one more volunteer? How about on the end there in the sweater? Yeah, come on down. We have, what's your name? Lauren. OK, Lauren, come on down. And how about, Lauren, why don't you go right in here in front, if you don't mind. Here is your number. Here is your pointer. So I've initialized Lauren to the number 1, and your pointer will be null, pointing at the ground. Where do you belong if we're maintaining sorted order? Looks like right at the beginning. What should happen here? OK, so Pedro has presumed to point now at Lauren. But how do you know where to point? Pedro's undoing what he did a moment ago. So this was deliberate, and that was perfect that Pedro presumed to point immediately at Lauren. Why? You literally just orphaned all of these folks, all of these chunks of memory. Why? Because if Pedro was our only variable pointing at that chunk of memory, this is the danger of using pointers and dynamic memory allocation and building your own data structures. The moment you point temporarily, if you could, to Lauren, I have no idea where he's pointing to. I have no idea how to get back to Caleb or Hannah or anyone else on stage. So that was bad. So you did undo it. So that's good. I think we need Lauren to make a decision first. Who should you point at? So pointing at Caleb. Why? Because you're pointing at literally who Pedro is pointing at. Pedro, now what are you safe to do? Good. So order of operations there matters. And if we had just done this line of code in red here, list equals in, that was like Pedro's first instinct. Bad things happen, and we orphaned the rest of the list. But if we think through it logically and do this, as Lauren did for us instead, we've now updated the list to look a little something more like this. Let's do one last one. We got one more foam finger here for the number 3. How about on the end? Yeah? You want to come down? All right. One final volunteer. All right. What's your name?
Miriam.
Sorry?
Miriam.
Miriam. All right. So here is your number 3. Here is your pointer. If you want to go maybe in the middle of the stage in a random memory location. So here, too, the goal is to maintain sorted order. So let's ask the audience, who or what number should point at whom first here so we don't screw up and orphan some of the memory. And this is, if we do orphan memory, this is what's called, again, per last week, a memory leak. Your Mac, your PC, your phone can start to slow down if you keep asking for memory but never give it back or lose track of it. So we want to get this right. Who should point at whom? Or what number? Say again?
3 to 4.
3 should point at 4. So 3, do you want to point at 4? And not, so OK, good. And how did you know, Miriam, whom to point at? Perfect. OK, so copying Caleb. Why? Because if you look at where this list is currently constructed, and you can cheat on the board here, 2 is pointing to 4. If you point at whoever Caleb, number 2, is pointing at, that indeed leads you to Hannah for number 4. So now what's the next step to stitch this together? Our voice in the crowd. 2 to 3. So 2 to 3. So Caleb, I think it's now safe for you to decouple because someone is already pointing at Hannah. We haven't orphaned anyone. So now if we follow the breadcrumbs, we've got Pedro leading to 1, to 2, to 3, to 4, to 5. We need the numbers back, but you can keep the foam fingers. Thank you to our volunteers here. Thank you. You can just put the numbers here. Thank you to all. So this is only to say that when you start looking at the code this week and in the problem set, it's going to be very easy to sort of lose sight of the forest for the trees because the code does get really dense. But the ideas, again, really do bubble up to these higher level descriptions. And if you think about data structures at this level, if you go off and program after a class like CS50 and you're whiteboarding something with a friend or a colleague, most people think at and talk at this level. And they just assume that, yeah, if we went back and look at our textbooks or class notes, we could figure out how to implement this. But the important stuff is the conversation and the ideas up here, even though via this week, will we get some practice with the actual code. So when it comes to analyzing an algorithm like this, let's consider the following. What might be now the running time of operations like searching and inserting into a linked list? We talked about arrays earlier, and we had some binary search possibilities still as soon as it's an array. But as soon as we have a linked list, these arrows, like our volunteers, could be anywhere on stage. And so you can't just assume that you can jump arithmetically to the middle element, to the middle element, to the middle one. You pretty much have to follow all of these breadcrumbs again and again. So how might that inform what we see? Well, consider this too. Even though I keep drawing all of these pictures with all of the numbers exposed, and all of us humans in the room can easily spot where the 1 is, where the 2 is, where the 3 is, the computer, again, just like with our lockers and arrays, can only see one location at a time. And the key thing with a linked list is that the only address we've fundamentally been remembering is what Pedro represented a moment ago. He was the link to all of the other nodes. And in turn, each person led to the next. But without Pedro, we would have lost some of or all of the linked list. So when you start with a linked list, if you want to find an element, as via search, you have to do it linearly, following all of the arrows, following all of the pointers on the stage in order to get to the node in question. And only once you hit null can you conclude, yep, it was there, or no, it was not. So given that, if a computer essentially can only see the number 1 or the number 2 or the number 3 or the number 4 or the number 5 one at a time, how might we think about the running time of search? It is indeed big O of n. But why is that? Well, in the worst case, the number you might be looking for is all the way at the end. And so obviously, you're going to have to search all of the n elements. And I drew these things with boxes on top of them because, again, even though you and I can immediately see where the 5 is, for instance, the computer can only figure that out by starting at the beginning and going there. So there, too, is another trade-off. It would seem that overnight, we have lost the ability to do a very powerful algorithm from week 0 known as binary search, right? It's gone because there's no way in this picture to jump mathematically to the middle node unless you remember where it is and then remember where every other node is. And at that point, you're back to an array. Linked lists by design only remember the next node in the list. All right, how about something like insert? In the worst case, perhaps, how many steps might it take to insert something into a linked list? Someone else? Someone else, yeah. Say again? N squared. Fortunately, it's not that bad. It's not as bad as n squared. That typically means doing n things n times. And I think we can stay under that. But not a bad thought. Yeah? Why would it be n? OK, so to summarize, you're proposing n because to find where the thing goes, you have to traverse potentially the whole list. Because if I'm inserting the number 6 or the number 99 that numerically belongs at the very end, I can only find its location by looking for all of them. At this point, though, in the term, and really this point in the story, you should start to question these kinds of very simplistic questions, to be honest, because the answer is almost always going to depend. right? If I've just got a linked list that looks like this, the first question back to someone asking this question would be, well, does the list need to be sorted? Right? I've drawn it as sorted, and it might imply as much, so that's a reasonable assumption to have made. But if I don't care about maintaining sorted order, I could actually insert into a linked list in constant time. Why? I could just keep inserting into the beginning, into the beginning, into the beginning. And even though the list is getting longer, the number of steps required to insert something between the first element is not growing at all. You just keep kind of inserting. If you want to keep it sorted, though, yes, it's going to be indeed big O of n. But again, these kinds of now assumptions are going to start to matter. So let's, for the sake of discussion, say it's big O of n if we do want to maintain sorted order. But what about in the case of not caring, it might indeed be big O of 1. And now these are the kinds of decisions that we'll start to leave to you. What about in the best case here? If we're thinking about big omega notation, then frankly, we could just get lucky in the best case. And the element we're looking for happens to be at the beginning. Or heck, we just blindly insert to the beginning, irrespective of the order that we want to keep things in. All right, so besides that, how can we improve further on this design? We don't need to stop at linked list because honestly, it's not been a clear win. Like linked lists allow us to use more of our memory because we don't need massive growing chunks of contiguous memory. So that's a win. But they still require big O of n time to find the end of it. If we care about order, we're using at least twice as much memory for the darn pointer. So that seems like, a sidestep. It's not really a step forward. So can we do better? Here's where we can now accelerate the story by just stipulating that, hey, even if you haven't used this technique yet, we would seem to have an ability to stitch together pieces of memory just using pointers. And anything you could imagine drawing with arrows, you can implement, it would seem, in code. So what if we leverage a second dimension? Instead of just stringing together things laterally, left to right, essentially, even though they were bouncing around on the screen, what if we start to leverage a second dimension here, so to speak, and build more interesting structures in the computer's memory? Well, it turns out that in a computer's memory, we could create a tree, similar to a family tree. If you've ever seen or drawn a family tree with grandparents and parents and siblings and so forth, it's kind of this so inverted branch of a tree that grows, typically when it's drawn, downward instead of upward like a typical tree. But that's something we could translate into code as well. Specifically, let's do something called a binary search tree, which is a type of tree. And what I mean by this is the following. Notice this. This is an example of an array from like week 2 when we first talked about those and we had the lockers on stage. And recall that what was nice about an array, if 1, it's sorted, and 2, all of its numbers are indeed contiguous, which is by definition of an array, we can just do some simple math. For instance, if there's 7 elements in this array, and we do 7 divided by 2, that's what, 3.5, round down through truncation, that's 3, 0, 1, 2, 3. That gives me the middle element arithmetically in this thing. And even though I have to be careful about rounding, using simple arithmetic, I can very quickly, with a single line of code or math, find for you the middle of the left half of the left half of the right half or whatever. That's the power of arrays, and that's what gave us binary search. And how did binary search work? Well, we looked at the middle, and then we went left or right, and then we went left or right again, sort of as implied by this color scheme here. Wouldn't it be nice if we somehow preserved the new upsides today of dynamic memory allocation, giving ourselves the ability to just add another element, add another element, add another element, but retain the power of binary search? Because log of n was much better than n, certainly for large data sets. Right? Even the phone book demonstrated as much weeks ago. So what if I kind of draw this same picture in 2 dimensions, and I preserve the color scheme just so it's obvious what came where? What do these things kind of look like now? Maybe like things we might now call nodes, right? A node is just a generic term for like storing some data. What if the data these nodes are storing are numbers, so still integers? But what if we kind of connected these cleverly like an old family tree, whereby every node has not 1 pointer now, but as many as 2. Maybe 0, like in the leaves at the bottom there in green. But other nodes on the interior might have as many as 2, like having 2 children, so to speak. And indeed, the vernacular here is exactly that. This would be called the root of the tree, or this would be a parent with respect to these children. The green ones would be grandchildren with respect to these. The green ones would be siblings with these green ones would be siblings with respect to each other, and over there too. So all the same jargon you might use in the real world applies in the world of data structures and CS trees. But this is interesting because I think we could build this now, this kind of data structure, in the computer's memory. How? Well, suppose that we defined a node to be no longer just this, a number in a next field. What if we sort of give ourselves a bit more room here and give ourselves a pointer called left and another one called right, both of which is a pointer to a struct node, so same idea as before. But now we just make sure we think of these things as pointing this way and this way, not just this way, not just a single direction, but two. So you could imagine in code building something up like this with a node that creates, in essence, this diagram here. But why is this compelling? Suppose I want to find the number 3. I want to search for the number 3 in this tree. It would seem, just like Pedro was the beginning of our linked list, in the world of trees, the root, so to speak, is the beginning of your data structure. You can retain and remember this entire tree just by pointing at the root node, ultimately. One variable can hang on to this whole tree. So how can I find the number 3? Well, if I look at the root node and the number I'm looking for is less than, notice I can go this way. Or if it's greater than, I can go this way. So I've preserved that property of the phone book or just a sorted array in general. What's true over here? If I'm looking for 3, I can go to the right of the 2 because that number is going to be greater. If I go left, it's going to be smaller instead. And here's an example of actually recursion. Recursion in a physical sense, much like the Mario's pyramid, which was kind of recursively defined. Notice this. I claim this whole thing is a tree, specifically a binary search tree, which means every node has 2 or maybe 1 or maybe 0 children, but no more than 2, hence the bi in binary. And it's the case that every left child is smaller than the root, and every right child is larger than the root. That definition certainly works for 2, 4, and 6. But it also works recursively for every subtree or branch of this tree. Notice, if you think of this as the root, it is indeed bigger than this left child, and it's smaller than this right child. And if you look even at the leaves, so to speak, the grandchildren here, this root node is bigger than its left child, if it existed. So it's sort of a meaningless statement. And it's less than its right child. Or it's not greater than, certainly. So that's meaningless too. So we haven't violated the definition even for these leaves as well. And so now, how many steps does it take to find, in the worst case, any number in a binary search tree, it would seem? So it seems 2 literally. And the height of this thing is actually 3. And so long story short, especially if you're a little less comfy with your logarithms from yesteryear, log base 2 is just like the number of times you can divide something in half and half and half until you get down to 1. This is kind of like a logarithm in the reverse direction. Here's a whole lot of elements, and we're having until we get down to 1. So the height of this tree, that is to say, is log base 2 of n, which means that even in the worst case, the number you're looking for maybe is all the way at the bottom in the leaves. Doesn't matter. It's going to take log base 2 of n steps, or log of n steps, to find maximally any one of those numbers. So again, binary search is back, but we've paid a price. Right? This isn't a linked list anymore. It's a tree. But we've gained back binary search, which is pretty compelling. Right? That's where the whole class began, on making that distinction. But what price have we paid to retain binary search in this new world? Yeah. It's no longer sorted left to right, but this is, I claim, sorted according to the binary search tree definition, where again, left child is smaller than root, and right child is greater than root. So it is sorted, but it's sorted in a 2-dimensional sense, if you will, not just one. But another price paid? Exactly. Every node now needs not one number, but 3 pieces of data, a number and now 2 pointers. So again, there's that kind of trade-off again, where, well, if you want to save time, you've got to give something. If you start giving space and you start using more space, you can speed up time. Like you've got it. There's always a price paid, and it's very often in space or time or complexity or developer time, the number of bugs you have to solve. I mean, all of these are sort of finite resources that you have to juggle among. So if we consider now the code with which we can implement this, here might be the node. And how might we actually use something like this? Well, let's take a look at maybe one final program in C here before we transition to higher level concepts ultimately. Let me go ahead here and let me just open a program I wrote here in advance. So let me, in a moment, copy over a file called tree.c, which we'll have on the course's website. And I'll walk you through some of the logic here that I've written for tree.c. All right, so what do we have here first? So here is a implementation of a binary search tree for numbers. And as before, I've just kind of played around and I've inserted the numbers manually. So what's going on first? Here is my definition of a node for a binary search tree, copied and pasted from what I proposed on the board a moment ago. Here are two prototypes for two functions that I'll show you in a moment that allow me to free an entire tree, one node at a time, and that also allow me to print the tree in order. So it's, even though they're not sorted left to right, I bet if I'm clever about what child I print first, I can reconstruct the idea of printing this tree properly. So how might I implement a binary search tree? Here's my main function. Here is how I might represent a tree of size 0. It's just a null pointer called tree. Here's how I might add a number to that list. So here, for instance, is me mallocing space for a node, storing it in a temporary variable called n. Here is me just doing a safety check, make sure n does not equal null. And then here is me initializing this node to contain the number 2 first, then initializing the left child of that node to be null and the right child of that node to be null, and then initializing the tree itself to be equal to that particular node. So at this point in the story, there's just one rectangle on the screen containing the number 2 with no children. All right, let's just add manually to this a little further. Let's add another number to the list by mallocing another node. I don't need to redeclare n as a node star because it already exists at this point. Here's a little safety check. I'm going to not bother with my, let me do this, free memory here just to be safe. Do I want to do this? We're going to free memory 2, which I've not done here, but I'll save that for another time. Here I'm going to initialize the number to 1. I'm going to initialize the children of this no node to null and null. And now I'm going to do this. Initialize the tree's left child to be n. So what that's essentially doing here is, if this is my root node, the single rectangle I described a moment ago that currently has no children, neither left nor right, here's my new node with the number 1. I want it to become the new left child. So that line of code on the screen there, tree left equals n, is like stitching these two together with a pointer from 2 to the 1. All right, the next lines of code you can probably guess are me adding another number to the list, just the number 3. So this is a simpler tree with 2, 1, and 3, respectively. And this code, let me wave my hands, is almost the same, except for the fact that I'm updating the tree's right child to be this new and third node. Let's now run the code before looking at those two functions. Let me do make tree, /tree, and voila, 1, 2, 3. So it sounds like the data structure is sorted, to your concern earlier. But how did I actually print this and then eventually free the whole thing? Well, let's look at the definition of first print tree. And this is where things get kind of interesting. Print tree returns nothing, so it's a void function. But it takes a pointer to a root element as its sole argument, node star root. Here's my safety check. If root equals null, there's obviously nothing to print, just return. That sort of goes without saying. But here's where things get a little magical. Otherwise, print your left child, then print your own number, then print your right child. What is this an example of, even though it's not mentioned by name here? What programming technique here? Yeah, so this is actually perhaps the most compelling use of recursion yet. It wasn't really that compelling with the Mario thing because we had such an easy implementation with a for loop weeks ago. But here is kind of a perfect application of recursion where your data structure itself is recursive, right? If you take any snip of any branch, it all still looks like a tree, just a smaller one. That lends itself to recursion. So here is this leap of faith where I say, print my left tree, or my left subtree, if you will, via my child at the left. Then I'll print my own root node here in the middle. Then go ahead and print my right subtree. And because we have this base case that just makes sure that if the root is null, there's nothing to do, you're not going to recurse infinitely. You're not going to call yourself again and again and again infinitely many times. So it just kind of works out and prints the 1, the 2, and the 3. And notice what we could do, too. If you wanted to print the tree in reverse order, you could do that. Print your right tree first, the greater element, then yourself, then your smaller subtree. And if I do make tree here in /tree, voila, now I've reversed the order of the list. And that's pretty cool. You could do it with a for loop and an array, but you can also do it even with this two-dimensional structure. Let's lastly look just at this free tree function. And this one's almost the same. Order doesn't matter in quite the same way, but it does still matter. Here's what I did with free tree. Well, if the root of the tree is null, there's obviously nothing to do. Just return. Otherwise, go ahead and free your left child and all of its descendants. Then free your right child and all of its descendants. And then free yourself. And again, free literally just frees the address in that variable. It doesn't free the whole darn thing. It just frees literally what's at that address. Why was it important that I did line 72 last, though? Why did I free the left child and the right child before I freed myself, so to speak? Exactly. If you free yourself first, if I had done incorrectly this line higher up, you're not allowed to touch the left child subtree or the right child subtree because the memory address is no longer valid at that point. You would get some kind of memory error, perhaps. The program would crash. Valgrind definitely wouldn't like it. Bad things would otherwise happen. But here then is an example of recursion, and again, just a recursive use of an actual data structure. And what's even cooler here is, relatively speaking, suppose we wanted to search something like this. Binary search actually gets pretty straightforward to implement too. For instance, here might be the prototype for a search function for a binary search tree. You give me the root of a tree, and you give me a number I'm looking for, and I can pretty easily now return true if it's in there or false if it's not. How? Well, let's first ask a question. If tree equals null, then you just return false. Because if there's no tree, there's no number, so it's obviously not there. Return false. Else if the number you're looking for is less than the tree's own number, which direction should we go? OK, left. How do we express that? Well, let's just return the answer to this question. Search the left subtree by way of my left child looking for the same number. And you just assume through the beauty of recursion that you're kicking the can and let yourself figure it out with a smaller problem, just that snipped left tree instead. Else, if the number you're looking for is greater than the tree's own number, go to the right, as you might infer. So I can just return the answer to this question. Search my right subtree for that same number. And there's a fourth and final condition. What's the fourth scenario we have to consider explicitly? Yeah. If the number itself is right there. So else if the number I'm looking for equals the tree's own number, then and only then should you return true. And if you're thinking quickly here, there's an optimization possible, better design opportunity. Think back to even our Scratch days. What could we do a little better here? You're pointing at it? Exactly. And else suffices, because if there's logically only 4 things that could happen, you're wasting your time by asking a 4th gratuitous question, and else here suffices. So here, too, more so than the Mario example a few weeks ago, there's just this elegance, arguably, to recursion. And that's it. This is not pseudocode. This is the code for binary search on a binary search tree. And so recursion tends to work in lockstep with these kinds of data structures that have this kind of structure to them, as we're seeing here. Are any questions then on binary search as implemented here with a tree? Yeah? Good question. So when returning a Boolean value, true and false are values that are defined in a library called standard bool, stdbool.h, with the header file that you can use. It is the case that true is it's not well defined what they are, but they would map indeed, yes, to 0 and 1 essentially. But you should not compare them explicitly to 0 and 1. When you're using true and false, you should compare them to each other. Sorry. So if I am in my own code from earlier, in a void function, it is totally fine to return. You just can't return something explicitly. So return just means that's it. Quit out of this function. You're not actually handing back a value. So it's a way of short-circuiting the execution. If you don't like that, and some people do frown upon having code return from functions prematurely, you could invert the logic and do something like this. If the root does not equal null, do all of these things, and then indent all 3 of these lines underneath. That's perfectly fine, too. I happen to write it the other way just so that there was explicitly a base case that I could point to on the screen, whereas now it's kind of implicitly there for us only. But a good observation, too. All right, so let's ask the question as before about like running time of this. It would look like binary search is back, and we can now do things in logarithmic time, but we should be careful. Is this A binary search tree, just to be clear. And again, a binary search tree is a tree where the root is greater than its left child and smaller than its right child. That's the essence. So you're nodding your head. You agree? Okay, I agree. So this is a binary search tree. Is this a binary search tree? OK, I'm hearing yeses, or I'm hearing just my delay changing the vote, it would seem. So this is kind of one of those trick questions. This is a binary search tree because I've not violated the definition of what I gave you. Right? Is there any example of a left child that is greater than its parent? Or is there any example of a right child that's smaller than its parent? That's just the opposite way of describing the same thing. No, this is a binary search tree. Unfortunately, it also looks like, albeit at a different axis, what? A linked list. But you could imagine this happening, right? Suppose that I hadn't been as thoughtful as I was earlier by inserting 2 and then 1 and then 3, which kind of nicely balanced everything out. Suppose that instead, because of what the user's typing in or whatever you contrive in your own code, suppose you insert a 1 and then a 2 and then a 3. Like, you've kind of created a problem for yourself, because if we follow the same logic as before, going left or going right, this is how you might implement a binary search tree accidentally if you just blindly keep following that definition. I mean, this would be better designed as what? If we kind of like rotated the whole thing around, and that's totally fine. And those kinds of trees actually have names. There's trees called AVL trees in computer science. There are red-black trees in computer science. There are other types of trees that additionally add some logic that tell you when you got to pivot the thing and rotate it and kind of snip off the root and fix things in this way. But a binary search tree in and of itself does not guarantee that it will be balanced, so to speak. And so if you consider the worst case scenario of even using a binary search tree, if you're not smart about the code you're writing, and you just blindly follow this definition, you might accidentally create a crazy long and stringy binary search tree that essentially looks like a linked list, because you're not even using any of the left children. So unfortunately, the literal answer to the question here is, what's the running time of search? Well, hopefully log n, but not if you don't maintain the balance of the tree. Both insert and search could actually devolve into, instead of big O of log n, literally big O of n, if you don't somehow take into account, and we're not going to do the code for that here, sort of a higher level thing you might explore beyond, down the road, it can devolve into something that you might not have intended. And so now that we're talking about 2 dimensions, it's really the onus is on the programmer to consider what kinds of perverse situations might happen where the thing devolves into a structure that you don't actually want it to devolve into. All right, we've got just a few structures to go. Let's go ahead and take one more 5-minute break here. When we come back, we'll talk at this level about some final applications of this. See you in 5. All right. So we are back. And as promised, we'll sort of operate now at this higher level, where if we take for granted that even though you haven't had an opportunity to play with these techniques yet, you have the ability now in code to kind of stitch things together, both in a 1 dimension and even 2 dimensions, to build things like lists and trees. So if we have these building blocks, things like now arrays and lists and trees, what if we start to kind of amalgamate them such that we build things out of multiple data structures? Can we start to get some of the best of both worlds by way of, for instance, something called a hash table? So a hash table is sort of a Swiss Army knife of data structures in that it's so commonly used because it allows you to associate keys with values, so to speak. So for instance, it allows you to associate a username with a password, or a name with a number, or anything where you have to take something as input and get as output a corresponding piece of information. A hash table is often a data structure of choice. And here's what it looks like. It actually looks like an array at first glance, but for discussion's sake, I've drawn this array vertically, which is totally fine. It's still just an array. But it allows you, a hash table, to jump to any of these locations randomly, that is instantly. So for instance, there's actually 26 locations in this array because I want to, for instance, store initially names of people, for instance. And wouldn't it be nice if the person's name starts with A, I have a go-to place for it, maybe the first box. And if it starts with Z, I put them at the bottom, so that I can jump instantly, arithmetically, using a little bit of ASCII or Unicode fanciness, exactly to the location that they need to go. So for instance, here's our array, 0 index, 0 through 25. If I think of this, though, as A through Z, I'm going to think of these 26 locations now in the context of a hash table as what we'll generally call buckets. So buckets into which you can put values. So for instance, suppose that we want to insert a value, one name, into this data structure, and that name is, say, Albus. So Albus starting with A. Albus might go at the very beginning of this list. All right, and then we want to insert another name. This one happens to be Zacharias, starting with Z, so it goes all the way at the end of this data structure in location 25, aka Z. And then maybe a third name like Hermione, and that goes at location H, according to that position in the alphabet. So this is great because in constant time, I can insert and conversely search for any of these names based on the first letter of their name, A or Z or H in this case. Let's fast forward and assume we put a whole bunch of other names, that might look familiar, into this hash table. It's great because every name has its own location. But if you're thinking of names you don't yet see it on the screen, we eventually encounter a problem with this, right? When could something go wrong using a hash table like this if we wanted to insert even more names? What's going to eventually happen? Yeah, there's already someone with the first letter, right? Like I haven't even mentioned Harry, for instance, or Hagrid, and yet Hermione's already using that spot. So that sort of invites the question, well, what happens? Maybe if we want to insert Harry next, do we maybe cheat and put him at location I? But then if there's a location I, where do we put them? And it just feels like the situation could very quickly devolve. But I've deliberately drawn this data structure that I claim is a hash table sort of in two directions. An array vertically here. But what might this be hinting I'm using horizontally, even though I'm drawing the rectangles a little differently from before? Yeah, maybe another array, to be fair. But honestly, arrays are such a pain with the allocating and reallocating and so forth. These kind of look like the beginnings of a linked list, if you will, where the name is where the number used to be, even though I'm drawing it horizontally now just for discussion's sake. And this seems to be like a pointer that isn't pointing anywhere yet. But it looks like the array is 26 pointers. Some of which are null, that is empty, some of which are pointing at the first node in a linked list. So that's really what a hash table might be in your mind, an amalgam of an array whose elements are linked lists. And in theory, this kind of gives you the best of both worlds, right? You get random access with high probability, right? You get to jump immediately to the location you want to put someone. But if you run into this perverse situation where there's someone already there, OK, fine. It starts to devolve into a linked list. But it's at least 26 smaller linked lists, not one massive linked list, which would be big O of n and quite slow to solve. So if Harry gets inserted in Hagrid, yeah, you have to kind of chain them together, so to speak, in this way. But at least you've not painted yourself into a corner. And in fact, if we fast forward and put a whole bunch of familiar names in, the data structure starts to look like this. So the chain's not terribly long. And some of them are actually of size 0 because there's just some unpopular letters of the alphabet among these names. But it seems better than just putting everyone in one big array or one big linked list. We're sort of trying to balance these trade-offs a little bit in the middle here. Well, how might we represent something like this? Here's how we could describe this thing. A node in the context of a linked list could be this. I have an array called word of type char, and it's big enough to fit the longest word in the alphabet plus 1. And the plus 1, why, probably? The null character. So I'm assuming that longest word is like a constant defined elsewhere in the story, and it's something big like 40, 100, whatever the longest word in the Harry Potter universe is, or the English alphabet or English dictionary is. Longest word plus 1 should be sufficient to store any name in the story here. And then what else does each of these nodes have? Well, it has a pointer to another node. So here's how we might implement the notion of a node in the context of storing not integers, but names instead, like this. But how do we decide what the hash table itself is? Well, if we now have a definition of a node, we could have a variable in main or even globally called hash table that itself is an array of node star pointers. That is, an array of pointers to nodes, the beginnings of linked lists. Number of buckets is kind of up to me. I proposed verbally that it be 26. But honestly, if you get a lot of collision, so to speak, a lot of H names trying to go to the same place, well, maybe we need to be smarter and not just look at the first letter of their name, but maybe the first and the second. So it's HA and HE. But wait, no, then Harry and Hagrid still collide. But we start to at least make the problem a little less impactful by tinkering with something like the number of buckets in a hash table like this. But how do we decide where someone goes in a hash table in this way? Well, it's an old school problem of input and output. The input to the problem is going to be something like the name. And the algorithm in the middle, as of today, is going to be something called a hash function. A hash function is generally something that takes as input a string, a number, whatever, and produces as output a location in our context. like a number 0 through 25, or 0 through 16,000, or whatever the number of buckets you want is, it's going to just tell you where to put that input at a specific location. So for instance, Albus, according to the story thus far, gave me back 0 as output. Zacharias gave me 25. So the hash function in the middle of that black box is pretty simplistic in this story. It's just looking at like the ASCII value, it seems, of the first letter in their name, and then subtracting off what capital A is 65. So like doing some math to get back a number between 0 and 25. So that's how we got to this point in the story. And how might we then resolve the problem further and use this notion of hashing more generally? Well, just for demonstration's sake here's actually some buckets, literally. And we've labeled in advance these buckets with the suits from a deck of cards. So we've got some spades, and we've got diamonds here. And we've got, what else here? Clubs and hearts. So we have a deck of cards here, for instance, right? And this is something you yourself might do instinctively if you're sort of getting ready to start playing a game of cards. You're just kind of cleaning up, or you want things in order. Like here is literally a jumbo deck of cards. What would be the easiest way for me to sort these things? Well, we've got a whole bunch of sorting algorithms from the past. So I could go through, like, here's the 3 of diamonds. And I could, here, let me throw this up on the screen just so if you're far and back. So here's, diamonds. I could put this here, 3, 4. I could do this in order here. But a lot of us, honestly, if given a deck of cards and you just want to kind of clean it up and sort it in order, you might do things like this. Well, here's my input, 3 of diamonds. Let's put it in this bucket. 4 of diamonds, this bucket. 5 of diamonds, this bucket. And if you keep going through the cards, here's 7 of hearts, hearts bucket, 8 bucket. Queen of spades over here. And it's still going to take you 52 steps. But at the end of it, you have hashed all of the cards into 4 distinct buckets. And now you have problems of size 13, which is a little more tenable than doing one massive 52 card problem. You can now do 4 13 size problems. And so hashing is something that even you and I might do instinctively, taking as input some card, some name, and producing as output some location, a sort of temporary pile in which you want to stage things, so to speak. But these collisions are kind of inevitable. And honestly, if we kept going through the Harry Potter universe, some of these chains would get longer and longer and longer, which means that instead of getting someone's name quickly by searching for them or inserting them, might start taking a decent amount of time. So what could we do instead to resolve situations like this? If the problem fundamentally is that the first letter is just too darn popular, H, we need to take in more input, not just the first letter, but maybe the first 2 letters. So if we do that, we can go from A through Z to something more extreme, like maybe HA, HB, HC, HD, HE, HF, and so forth, so that now Harry and Hermione end up at different locations. But, darn it, Hagrid still collides with Harry. So it's better than before. The chains aren't quite as long, but the problem isn't fundamentally gone. And in this case here, anyone know how many buckets we just increased to? If we now look at not just A through Z, but AA through ZZ, roughly? Yeah, so, OK, good. So the easy answer, 26 squared, or 676. So that's a lot more buckets. And this is why I only showed a few of them on the screen. So that's a lot more. And it spreads things out in particular. What if we take this one step further? Instead of HA, we do like HAA, HAB, HAC, HZZ, and so forth. Well, now we have an even better situation, because Hermione has her one spot. Harry has his one spot. Hagrid has his one spot. But there's a trade-off here. The upside is now, arithmetically, we can find their locations in constant time. Maybe technically 3 steps, but 3 is constant, no matter how many other names are in here, it would seem. But what's the downside here? Sorry, say again? Memory. So significantly more. We're now up to 17,576 buckets, which itself isn't that big a deal, right? Computers have a lot of memory these days. But as you can kind of infer, I can't really think of someone whose name started with HEQ, for instance, in the Harry Potter universe. And if we keep going, definitely don't know of anyone whose name started with ZZZ or AAA. There's a lot of sort of not useful combinations that have to be there mathematically so that you can do a bit of math and jump to, randomly, so to speak, the precise location. But they're just going to be empty. So it's a very sparsely populated array, so to speak. So what does that really mean for performance ultimately? Well, let's consider again in the context of our big O notation. It turns out that a hash table technically speaking, is still just going to give us big O of n in the worst case. Why? If you have some crazy perverse case where everyone in the universe has a name that starts with A or starts with H or starts with Z, you just get really unlucky and your chain is massively long. Well, then at that point, it's just a linked list. It's not a hash table. It's like the perverse situation with the tree, where if you insert it without any mind for balancing it, keeping it balanced, it just evolves. But there's a difference here between sort of a theoretical performance and an actual performance. If you look back at the tree, the hash table here, this is absolutely in practice going to be faster than a single linked list. You know, mathematically, asymptotically, big O notation, sure, it's all the same, big O of n. But if what we're really caring about is real humans using our software, there's something to be said for crafting a data structure that technically, if this data were uniformly distributed, is 26 times faster than a linked list alone. And so there's this tension, too, in between like systems, types of CS and theoretical CS, where, yeah, theoretically these are all the same. But in practice, for making real-world software, you know, improving the speed by a factor of 26 in this case, let alone 576 or more, might actually make a big difference. But there's going to be a trade-off, and that's typically some other resource like giving up more space. All right, how about another data structure we could build? Let me fast forward to something here called a trie. So a trie, sort of a weird name in pronunciation, short for retrieval, pronounced trie typically. A trie is a tree that actually gives us constant time lookup, even for massive data sets. What do I mean by this? In the world of a trie, you create a tree out of arrays. So we're really getting into like the Frankenstein territory of just building things up with like spare parts of data structures that we have here. But the root of a trie is itself an array, for instance, of size 26, where each element in that trie points to another node, which is to say another array, and each of those locations in the array represents a letter of the alphabet, like A through Z. So for instance, if you wanted to store the names of the Harry Potter universe, not in a hash table, not in a linked list, not in a tree, but in a trie, what you would do is hash on every letter in the person's name one at a time. So a trie is like a multi-tier hash table in a sense, where you first look at the first letter, then the second letter, then the third, and you do the following. For instance, each of these locations represents a letter A through Z. Suppose I wanted to insert someone's name into this that starts with the letter H, like Hagrid, for instance. Well, I go to the location H. I see it's null, which means I need to malloc myself another node or another array. And that's depicted here. Then suppose I want to store the second letter in Hagrid's name, an A. So I go to that location in the second node, and I see, OK, it's currently null. There's nothing below it. So I allocate another node using malloc or the like. And now I have HAG, and I continue this with R, I, D. And then when I get to the bottom of this person's name, I just have to indicate here in color, but probably with a Boolean value or something, like a true value that says a name stops here, so that it's clear that the person's name is not H-A or H-A-G or H-A-R or H-A-G-R. It's H-A-G-R-I-D. And the D is green just to indicate there's like some other Boolean value that just says, yes, this is the node in which the name stops. And if I continue this logic, here's how I might insert someone like Harry. And here's how I might insert someone like Hermione. And what's interesting about the design here is that some of these names share a common prefix, which starts to get compelling because you're reusing space. You're using the same nodes for names like H-A-G and H-A-R because they share H and an A in common, and they all share an H in common. So you have this data structure now that itself is a tree. Each node in the tree is itself an array, and we therefore might implement this thing using code like this. Every node is containing, I'll do it in reverse order, an array. I'll call it children, because that's what it really represents, up to 26 children for each of these nodes, size of the alphabet. So I might have used a constant for number 26 to give myself 26 letters of the alphabet. And each of those arrays stores that many node stars, that many pointers to another node. And here's an example of the bool. This is what I represented in green on the slide a moment ago. I also need another piece of data, just a 0 or 1, a true or false, that says, yes, a name stops in this node, or it's just a path to the rest of the person's name. But the upside of this is that The height of this tree is only as tall as the person's longest name, Hagrid or Hermione. And notice that no matter how many other people are in this data structure, there's 3 at the moment. If there were 3 million, it would still take me how many steps to search for Hermione? Hermione. So 8 steps total. No matter if there's 2 other people, 2 million, 10 million other people, because the path to her name is always on the same path. And if you assume that there's a maximum limit on the length of names in the human world, maybe it's 40, 100, whatever the longest name in the world is, that's constant. Maybe it's 40, 100, but that's constant, which is to say that with a trie, technically speaking, it is the case that your lookup time, big O of n, big O notation would be big O of 1. It's constant time because unlike every other data structure we've looked at, with a trie, the amount of time it takes you to find one person or insert one person is completely independent of how many other pieces of data are already in the data structure. And this holds true even if one name is a prefix of another. I don't think there was a Daniel or Danielle in the Harry Potter universe that I could think of, but Daniel could be one name. And therefore, we have a true there in green. And if there's a longer name like Danielle, then you keep going until you get to the E. So you can still have, with a trie, one name that's a substring of another name. So it's not as though we've created a problem there. That, too, is still possible. But at the end of the day, it only takes a finite number of steps to find any of these people. And again, that's what's particularly compelling, that you effectively have constant time lookup. So that's amazing, right? We've gone through this whole story for weeks now of like linear time, and then it went up to like n squared, and then log n, and now constant time. What's the price paid for a data structure like this so-called trie? What's the downside here? There's got to be a catch. And in fact, tries are not actually used that often, amazing as they might sound on some CS level here. Memory. Why? In what sense? Exactly. If you're storing all of these darn arrays, it's, again, a sparsely populated data structure. And you can kind of see it here. Granted, there's only 3 names, but most of those boxes, most of those pointers are going to remain null. So this is an incredibly wide data structure, if you will. It uses a huge amount of memory to store the names. But again, you got to pick a lane. Either you're going to minimize space or you're going to minimize time. It's not really possible to get truly the best of both worlds. You have to decide where the inflection point is for the device you're writing software for, how much memory it has, how much expensive it is, and again, taking all of these kinds of things into account. So lastly, let's do one further abstraction, so even higher level, to discuss something that are generally known as abstract data structures. It turns out we could spend like all day, all week talking about different things we could build with these data structures. But for the most part, now that we have arrays, now that we have linked lists or their cousins, trees, which are 2-dimensional, and beyond that there's even graphs where the arrows can go in multiple directions, not just down, so to speak. Now that we have this ability to stitch things together, we can solve all different types of problems. So for instance, a very common type of data structure to use in a program or even our human world are things called queues. A queue being a data structure like a line outside of a store, where it has what's called a FIFO property, first in, first out, which is great for fairness, at least in the human world. And if you've ever waited outside of Tasty Burger or Salsa Fresca or some other restaurant nearby, presumably if you're queuing up at the counter, you want the store to maintain a FIFO system, first in, first out, so that whoever's first in line gets their food first and gets out first. So a queue is actually a computer science term too. And even if you're still in the habit of printing things on paper, there are things you might have heard called printer queues, which also do things in order. The first person to send their essay to the printer should ideally be printed before the last person to send their essay to the printer, again, in the interests of fairness. But how can you implement a queue? Well, you typically have to implement like 2 fundamental operations, enqueue and dequeue. So adding something to it and removing something from it. And the interesting thing here is that how do you implement a queue? Well, in the human world, you would just have like literally physical space for humans to line up from left to right or right to left. Same in a computer, like a printer queue. If you send a whole bunch of jobs to be printed, a whole bunch of essays or documents, well, you need a chunk of memory, like an array. All right, well, if you use an array, what's a problem that could happen in the world of printing, for instance, if you use an array to store all of the documents that need to be printed? it could be filled, right? So if the programmer decided, HP or whoever makes the printer decides, oh, you can send like a megabyte worth of documents to this printer at once, at some point you might get an error message which says, sorry, out of memory, wait a few minutes, which is maybe a reasonable solution, but a little annoying. Or HP could write code that maybe dynamically resizes the array or so forth. But at that point, maybe they should just use a linked list. And they could. So there, too, you could implement the notion of a queue using a linked list instead. You're going to spend more memory, but you're not going to run out of space in your array, which might be more compelling. You know, this happens even in the physical world. You go to the store and, you know, you start having to line up outside and down the road. And like for a really busy store, they kind of run out of space, so they make do. But in that case, it tends to be more of an array just because of the physical notion of humans lining up. But there's other data structures too. If you've ever gone to the dining hall and picked up like a Harvard or a Yale tray, right, you're typically picking up the last tray that was just cleaned, not the first tray that was cleaned. Why? Because these cafeteria trays stack up on top of each other. And indeed, a stack is another type of abstract data structure. In the physical world, it's literally something physical like a stack of trays, which have what we would call a LIFO property, last in, first out. So as these things come out of the washer, they're putting the most recent ones on the top, and then you, the human, are probably taking the most recently cleaned one, which means in the extreme, no one on campus might ever use that very first tray, which is probably fine in the world of trays, but would really be bad in the world of like Tasty Burger or lining up for food if LIFO were the property being implemented. But here, too, it could be an array. It could be a linked list. And you see this, honestly, every day. If you're using Gmail and your Gmail inbox, that is actually kind of a stack, at least by default, where your newest message, last in, are the first ones at the top of the screen. That's kind of a LIFO data structure. And it means that you see your most recent emails. But if you have a busy day, you're getting a lot of emails, it might not be a good thing, because now you're kind of ignoring the people who wrote you way earlier in the day or the week. So LIFO and FIFO are just properties that you can achieve with these very specific types of data structures. And the parlance in the world of stacks is to push something onto a stack or pop something out. These are here, for instance, as an example of, like, why might you always wear the same color? Well, if you're storing all of your clothes in a stack, you might not ever get to, like, the different colored clothes at the bottom of the list. And in fact, to paint this picture, we have a couple-minute video here just to paint this here, made by a faculty member elsewhere. Let's go ahead and dim the lights for just a minute or two here so that we can take a look at Jack learning some facts.
Once upon a time, there was a guy named Jack. When it came to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" "Yes," said Jack, "I sure do. Come to my house and I'll show them to you." So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, "I see you have all your clothes in a pile. Why don't you wear some others once in a while?" Jack said, "Well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top." Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose the top book or underwear. Then when he was done, he would put it right back. Back it would go on top of the stack. "I know the solution," said a triumphant Lou. "You need to learn to start using a queue." Lou took Jack's clothes and hung them in a closet, and when he had emptied the box, he just tossed it. Then he said, "Now, Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning, when you see the sun shine, get your clothes from the right, from the end of the line." "Don't you see," said Lou, "it will be so nice. You'll wear everything once before you wear something twice." And with everything in queues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful queue.
So just to help you realize that these things are everywhere in the world, even in our human world. If you've ever lined up at this place, anyone recognize this? Okay, so Sweetgreen, a little salad place in the square, this is if you order online or in advance, your food ends up according to the first letter in your name, which actually sounds awfully reminiscent of something like a hash table. And in fact, no matter whether you implement a hash table like we did with an array and linked lists, or with like 3 shelves like this is actually an abstract data type called a dictionary. And a dictionary, just like in our human world, has keys and values, words and their definitions. This just has letters of the alphabet and salads as their value. But here, too, there's a real-world constraint. In what kind of scenario does this system at Sweetgreen devolve into a problem, for instance? Because they, too, are using only finite space, finite storage. What could go wrong? Yeah. Yeah, if they run out of space on the shelf, and there's a lot of people whose names start with D or E or whatever, and so they just pile up, and then maybe they kind of overflow into the E's or the F's, and they probably don't really care because any human's going to come by and just eyeball it and figure it out anyway. But in the world of a computer, you're the one coding and have to be ever so precise. We thought we would lastly do one final thing here. In advance, we prepared a linked list of sorts in the audience, since this has become a bit of a thing. I am starting to represent the beginning of this linked list insofar as I have a pointer here with seat location G9. Whoever's in G9, would you mind standing up? And what letter is on your seat there? OK, so you have S15 and your letter, say again? F15. So I see you're holding a C in your node. You are pointing to, if you could physically, F15. F15, what do you hold? You have an S, and who should you be pointing at? F5, could you stand up, F5? You're holding a 5, I see. What address? F12, big finale. F12, if you'd like to stand up, holding a 0 and null, which means that was CS50. All right, we'll see you next time. All right, this is CS50, and this is already week 6. And this is the week in which you learn yet another language. But the goal is not just to teach you another language for language's sake. As we transition today and in the coming weeks from C, where we've spent the past several weeks, now to Python, the goal ultimately is to teach you all how to teach yourselves new languages. So that by the end of this course, it's not in your mind the fact that you learned how to program in C or learned some weeks back how to program in Scratch, but really how you learned how to program fundamentally in a paradigm known as procedural programming, as well as with some taste today and in the weeks to come of other aspects of programming languages like object-oriented programming and more. So recall, though, back in week 0, Hello World looked a little something like this, and the world was quite simple. All you had to do was drag and drop these puzzle pieces, but there were still functions and conditionals and loops and variables and all of those kinds of primitives. We then transitioned, of course, to a much more arcane language that looked a little something like this. And even now, some weeks later, you might still be struggling with some of the syntax or getting annoying bugs when you try to compile your code and it just doesn't work. But there, too, the past few weeks, we've been focusing on functions and loops and variables, conditionals, and really all of those same ideas. And so what we begin to do today is to, 1, simplify the language we're using, transitioning from C now to Python, this now being the equivalent program in Python and look at its relative simplicity, but also transitioning to look at how you can implement these same kinds of features just using a different language. So we're going to see a lot of code today, and you won't have nearly as much practice with Python as you did with C, but that's because so many of the ideas are still going to be with us. And really, it's going to be a process of figuring out, all right, I want to do a loop. I know how to do it in C. How do I do this in Python? How do I do the same with conditionals? How do I declare variables and the like? And moving forward, not just in CS50, but in life in general, if you continue programming and learn some other language after the class, if in 5, 10 years there's a new, more popular language that you pick up, it's just going to be a matter of Googling and looking at websites like Stack Overflow and the like to look at just basic building blocks of programming languages, because you already speak, after these past 6+ weeks, you already speak programming itself fundamentally. All right, so let's do a few quick comparisons left and right of what something might have looked like in Scratch and what it then looked like in C, but now as of today, what it's going to look like in Python. Then we'll turn our attention to the command line ultimately in order to implement some actual programs. So in Scratch, we had functions like this: say hello world, a verb or an action. In C, it looked a little something like this, and a bit of a cryptic mess. The first week, you had the printf, you had the double quotes, you had the semicolon, the parentheses. So there's a lot more syntax just to do the same thing. We're not going to get rid of all of that syntax now, but as of today in Python, that same statement is going to look a little something like this. And just to perhaps call out the obvious, what is different or now simpler in Python versus C, even in this simple example here? Yeah? Good. So it's now print instead of printf, and there's also no semicolon, and there's one other subtlety over here. Yeah, so no new line. And that doesn't mean it's not going to be printed. It just turns out that one of the differences we'll see is that with print, you get the new line for free. It automatically gets outputted by default, being sort of a common case, but you can override it, we'll see ultimately too. How about in Scratch? We had multiple functions like this that not only said something on the screen, but also asked a question, thereby being another function that returned a value called answer. In C, we saw code that looked a little something like this, whereby that first line declares a variable called answer, sets it equal to the return value of getString, one of the functions from the CS50 library, and then the same double quotes and parentheses and semicolon. Then we had this format code in C that allowed us with %s to actually print out that same value. In Python, this too is going to look a little bit simpler. Instead, we're going to have answer equals getString, quote unquote, what's your name, and then print with a plus sign and a little bit of new syntax. But let's see if we can't just infer from this example what it is that's going on. Well, first, missing on the left is what? To the left of the equal sign, there's no what this time. Feel free to just call it out. So there's no type. There's no type like the word string, which even though that was a type in CS50, every other variable in C did we use int or string or float or bool or something else. In Python, there's still going to be data types today onward, but you, the programmer, don't have to bother telling the computer what types you're using. The computer is going to be smart enough, the language really is going to be smart enough to just figure it out from context. Meanwhile, on the right-hand side, getString is going to be a function we'll use today and this week, which comes from a Python version of the CS50 library, but we'll also start to take off those training wheels so that you'll see how to do things without any CS50 library moving forward, using a different function instead. As before, no semicolon, but the rest of the syntax is pretty much the same here. This starts, of course, to get a little bit different, though. We're using print instead of printf. But now, even though this looks a little cryptic, perhaps, if you've never programmed before CS50, what might that plus be doing? Just based on inference here. What do you think? Yeah, so adding answer to the string hello, and adding, so to speak, not mathematically, but in the form of joining them together, much like we saw the join block in Scratch, or concatenation was the term of art there. This plus sign appends, if you will, whatever's in answer to whatever is quoted here, and I deliberately left a space there so that grammatically it looks nice after the comma as well. Now, there's another way to do this, and it too is going to look cryptic at first glance, but it just gets easier and more convenient over time. You can also change this second line to be this instead. So what's going on here? This is actually a relatively new feature of Python in the past couple of years, where now what you're seeing is, yes, a string between these same double quotes, but this is what Python would call a format string, or f string. And it literally starts with the letter f, which admittedly looks, I think, a little weird, but that just indicates that Python should assume that anything inside of curly braces inside of the string should be interpolated, so to speak, which is a fancy term saying substitute the value of any variables therein. And it can do some other things as well. So answer is a variable, declared, of course, on this first line. This f string then says to Python, print out hello, comma, space, and then the value of answer. If, by contrast, you omitted the curly braces, just take a guess. What would happen? What would the symptom of that bug be if you accidentally forgot the curly braces, but maybe still had the f there? Yeah, it would literally print hello, comma, answer, because it's going to take you literally. So the curly braces just kind of allow you to plug things in. And again, it looks a little more cryptic, but it's just going to save us time over time. And if any of you programmed in Java in high school, for instance, you saw plus in that context too for concatenation. This just kind of makes your code a little tighter, a little more succinct. So it's a convenient feature now in Python. All right, this was an example in Scratch of a variable, setting a variable like counter equal to 0. In C, it looked like this, where you specify the type, the name, and then the value with a semicolon. In Python, it's going to look like this. And I'll state the obvious here. You don't need to mention the type, just like before with string. And you don't need a semicolon. So it's a little simpler. If you want a variable, just write it and set it equal to some value. But the single equal sign still behaves the same as in C. Suppose we wanted to increment counter by 1. In Scratch, we use this puzzle piece here. In C, we could do this actually in a few different ways. There was this way. If counter already exists, you just say counter equals counter plus 1. There was the slightly less verbose way where you could say, whoops, sorry. Let me do the first sentence first. In Python, that same thing, as you might guess, is actually going to be almost the same. You just throw away the semicolon. And the mathematics are ultimately the same, copying from right to left via the assignment operator. Now recall in C that we had this shorthand notation, which did the same thing. In Python, you can similarly do the same thing, just no need for the semicolon. The only step backwards we're taking, if you were a big fan of counter plus plus, that doesn't exist in Python, nor minus minus. You just can't do it. You have to do the plus equals 1 or plus minus or minus equals 1 to achieve that same result. All right, how about in Python 2? Here in Scratch, recall, was a conditional, asking a silly question like, is x less than y? And if so, just say as much. In C, that looked a little something like this, printf and if with the parentheses, the curly braces, the semicolon, and all of that. In Python, this is going to get a little more pleasant to type too. It's going to be just this. And if someone wants to call out some of the obvious changes here, what has been simplified now in Python for a conditional, it would seem? Yeah, what's missing or changed? So no curly braces. And sorry? And we're using the colon instead. So I got rid of the curly braces in Python, but I'm using a colon instead. And even though this is a single line of code, so long as you indent subsequent lines along with the printf, that's going to imply that everything, if the if condition is true, should be executed below it until you start to unindent and start writing a different line of code altogether. So indentation in Python is important. So this is among the reasons we've emphasized axes like style, just how well styled your code is. And honestly, we've seen certainly in office hours, and you've seen in your own code, sort of a tendency sometimes to be a little lax when it comes to indentation, right? If you're one of those folks who likes to indent everything on the left-hand side of the window, yeah, it might compile and run, but it's not particularly readable by you or anyone else. Python actually addresses this by just requiring indentation when logically needed. So Python is going to force you to start indenting properly now if that's been perhaps a tendency otherwise. What else is missing? Well, we have no semicolon here, of course. It's print instead of printf. But otherwise, those seem to be the primary differences. What about something larger in Scratch? If an if-else block like this, you can perhaps guess what it's going to look like. In C, it looked like this, curly braces, semicolons, and so forth. In Python, it's going to now look like this. Almost the same, but indentation's important, the colons are important, and there's one other difference that's now again visible here, but we didn't call it out a second ago. What else is different in Python versus C for these conditionals? Yeah. Perfect. We don't have any parentheses around the condition, the Boolean expression itself. And why not? Well, it's just simpler to type. It's less to type. You can still use parentheses. And in fact, you might want to or need to if you want to like combine thoughts and do this and that or this or that. But by default, you no longer need or should have those parentheses. Just say what you mean. Lastly, with conditionals, we had something like this, an if, else statement. In C, it looked a little something like this. In Python, it's going to get really tighter now. It's just if, and this is the curiosity, elif. x greater than y. So it's not else if, it's literally one keyword, elif, and the colons remain now on each of the 3 lines. But the indentation is important, and if we did want to do multiple things, we could just indent below each of these conditionals as well. All right, let me pause there first to see if there's any questions on these syntactic differences. Yeah?
Python is a space sensitive language, so it doesn't matter if there's a space between like x and plus and y.
Between what and what?
So like the less than sign is x and y. Doesn't matter if
Good question. Is Python sensitive to spaces and where they go? Sometimes no, sometimes yes is the short answer. Stylistically, though, you should be practicing what we're preaching here, whereby you do have spaces to the left and right of binary operators that they're called. Something like less than or greater than is a binary operator because there's 2 operands to the left and to the right of them. And in fact, in Python, more so than the world of C, there's actually formal style conventions. Not only within CS50 have we had a style guide on the course's website, for instance, that just dictates how you should write your code so that it looks like everyone else's. In the Python community, they take this one step further, and there's an actual standard whereby you don't have to adhere to it, but generally speaking, in the real world, someone would reprimand you, would reject your code if you're trying to contribute it to another project if you don't adhere to these standards. So while you could be lax with some of this white space, do make things readable. And that's Python's theme, for the code to be as readable as possible. All right, so let's take a look at a couple of other constructs before transitioning to some actual code. This, of course, in Scratch was a loop, meowing forever. In C, the closest we could get was doing something while true, because true never changes. So it's sort of a simple way of just saying do this forever. In Python, it's pretty much the same thing, but a couple small differences here. The parentheses are gone. The colon is there. The indentation is there. No semicolon. And there's one other subtle difference. What do you see? True is capitalized just because. Both true and false are Boolean values in Python, but you got to start capitalizing them just because. All right, how about a loop like this, where you repeat something a finite number of times, like meowing 3 times? In C, we could do this a few different ways. There's this very mechanical way where you initialize a variable like I to 0. You then use a while loop and check if I is less than 3, the total number of times you want to meow. Then you print what you want to print. You increment I using this syntax or the longer, more verbose syntax with plus equals or whatnot, and then you do it again and again and again. In Python, you can do it functionally the same way. Same idea, slightly different syntax. You just don't bother saying what type of variable you want. Python will infer from the fact that there's a 0 right there. You don't need the parentheses. You do need the colon. You do need the indentation. You can't do the I++, but you can do this other technique, as we could have done in C as well. How else might we do this, though, too? Well, it turns out in C, we could do something like this, which, again, sort of cryptic at first glance, became perhaps more familiar, where you have an initialization, a conditional, and then an update that you do after each iteration. In Python, there isn't really an analog. There is no analog in Python where you have the parentheses and the multiple semicolons in the same line. Instead, there is a for loop, but it's meant to read a little more like English. For I in 0, 1, and 2. So we'll see in a bit, these square brackets represent an array, now to be called a list in Python. So lists in Python are more like linked lists than they are arrays. More on that soon. So this just means for I in the following list of 3 values. And on each iteration of this loop, Python automatically for you, it first sets I to 0, then it sets I to 1, then it sets I to 2, so that you effectively do things 3 times. But this doesn't necessarily scale, as I've drawn it on the board. Suppose you took this at face value as the way you iterate some number of times in Python using a for loop. At what point does this approach perhaps get bad or bad design? Let me give folks just a moment to think. Yeah, I'm back. Sure, if you don't know how many times you want to loop or iterate, you can't really create a hard-coded list like that of 0, 1, 2. Other thoughts? Yeah, if you're iterating a large number of times, this list is going to get longer and longer, and you're just kind of stupidly going to be typing out like comma 3, comma 4, comma 5, comma dot, 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 comma 99, comma 100. I mean, your code would start to look atrocious eventually, so there is a better way. In Python, there is a function, or technically a type, called range that essentially magically gives you back a range of values from 0 on up to, but not through a value. So the effect of this line of code,
for I in the following range essentially hands you back a list of 3 values, thereby letting you do something 3 times. And if you want to do something 99 times instead, you, of course, just change the 3 to a 99. Question?
Is there a way to start the beginning point of that range at a number or an integer that's higher than 0, or is there never really a point to do so?
A really good question. Can you start counting at a higher number? So not 0, which is the implied default, but something larger than that? Yes. So it turns out the range function takes multiple arguments, not just 1, but maybe 2 or even 3, that allows you to customize this behavior. So you can customize where it begins. You can customize the increment. By default, it's 1. But if you want to do every 2 values for like evens or odds, you could do that as well, and a few other things. And before long, we'll take a look at some Python documentation that will become your authoritative source for answers like that. Like, what can this function do? Other questions on this thus far? Seeing none. So what else might we compare and contrast here? Well, in the world of C, recall that we had a whole bunch of built-in data types like these here, bool and char and double and float and so forth, string, which happened to come from the CS50 library, but the language C itself certainly understood the idea of strings because the \0, the support for %s and printf, that's all native, built into C, not a CS50 simplification. All we did and revealed as of a couple of weeks ago is that string, this data type, is just a synonym for, a type def for char star, which is part of the language natively. In Python now, this list actually gets a little shorter, at least for these common primitive data types. Still going to have bools, we're going to have floats and ints, and we're going to have strings, but we're going to call them strs. And this is not a CS50 thing from the library. Str, is in fact a data type in Python that's going to do a lot more than strings did for us automatically in C. Ints and floats, meanwhile, don't need the corresponding longs and doubles because, in fact, among the problems Python solves for us too, ints can get as big as you want. Integer overflow is no longer going to be an issue per week 1. The language solves that for us. Floating point imprecision, unfortunately, is still a problem that remains. But there are libraries, code that other people have written, as we briefly discussed in weeks past, that allow you to do scientific or financial computing using libraries that build on top of these data types as well. So there's other data types too in Python, which we'll see actually gives us a whole bunch of more power and capability. Things called ranges, like we just saw. Lists, like I called out verbally with the square brackets. Things called tuples for things like x comma y or latitude comma longitude. Dictionaries or dicts, which allow you to store keys and values, much like our hash tables from last time. And then sets in the mathematical sense, where they filter out duplicates for you. And you can just put a whole bunch of numbers, a whole bunch of words or whatnot. And the language, via this data type, will filter out duplicates for you. Now, there's going to be a few functions we give you this week and beyond, training wheels that we're then going to very quickly take off, just because, as we'll see today, they just simplify the process of getting user input correctly without accidentally writing buggy code just when you're trying to get hello world or something similar to work. And we'll give you functions not as long as this list in C, but a subset of these. Get float, get int, and get string. That'll automate the process of getting user input in a way that's more resilient against potential bugs, but we'll see what those bugs might be. And the way we're going to do this is similar in spirit to C. Instead of doing include cs50.h, like we did in C, you're going to now start saying import cs50. Python supports, similar to C, libraries, but there aren't header files anymore. You just use the name of the library in Python. And if you want to import CS50's functions, you just say import CS50. Or if you want to be more precise and not just import the whole thing, which could be slow if you've got a really big library with a lot of functionality in it, you can be more precise and say from CS50 import get float. From CS50 import get int. From CS50 import get string. Or you can just separate them by commas and import 3 and only 3 things from a particular library like ours. But starting today and onward, we're going to start making much more heavy use of libraries, code that other people wrote, so that we're no longer reinventing the wheel. We're not making our own linked lists, our own trees, our own dictionaries. We're going to start standing on the shoulders of others so that you can get real work done, so to speak, faster by building your software on top of others' code as well. All right, so that's it for the syntactic tour of the language and the sort of core features. Soon we'll transition to application thereof. But let me pause here to see if there's any questions on syntax or primitives or otherwise. No? Oh, yes, and back. sorry, say it again. Why doesn't Python have what kind of operators? Sorry, someone coughed when you said something operators. The increment operator? I'd have to check the history, honestly. Python has tended to be a fairly minimalist language. And if you can do something one way, the community arguably has tended to not give you multiple ways to do the same thing syntactically. There's probably a better answer. And I'll see if I can dig in and post something online to follow up on that. All right, so before we transition to now writing some actual code, let me go ahead and consider exactly how we're going to write code. In the world of C, recall that it's generally been a two-step process. We create a file called like hello.c, and then step 1, make hello, step 2, /hello. Or if you think back to week 2, when we sort of peeled back the layer of what what make was doing, you could more verbosely type out the name of the actual compiler, Clang in our case, command line arguments like -o hello to specify what name you want to create. And then you can specify the file name. And then you can specify what libraries you want to link in. So that was a very verbose approach, but it was always a two-step approach. And so even as you've been doing recent problem sets, odds are you've realized that anytime you want to make a change to your code or make a change to your code and try and test your code again, you're constantly doing those two steps. Moving forward in Python, it's going to become simpler, and it's going to be just this. The file name is going to change, but that might go without saying. It's going to be something like hello.py, instead of hello.c, and that's just a convention using a different file extension. But there's no compilation step per se. You jump right to the execution of your code. And so Python, it turns out, is the name not only of the language we're going to start using, it's also the name of a program on a Mac, a PC, assuming it's been pre-installed, that interprets the language for you. This is to say that Python is generally described as being interpreted, not compiled. And by that, I mean you get to skip, from the programmer's perspective, that compilation step. There is no manual step in the world of Python typically of writing your code and then compiling it to zeros and ones and then running the zeros and ones. Instead, these kind of two steps get collapsed into the illusion of one, whereby you instead are able to just run the code and let the computer figure out how to actually convert it to something the computer understands. And the way we do that is via this old process, input and output. But now, when you have source code, it's going to be passed into an interpreter, not a compiler. And the best analog of this is just to perhaps point out that in the human world, if you speak or don't speak multiple human languages, it can be a pretty slow process from going from one language to another. For instance, here are step-by-step instructions for finding someone in a phone book, unfortunately in Spanish. Unfortunately, if you don't speak or read Spanish, you could figure this out. You could run this algorithm, but you're going to have to do some Googling, or you're going to have to open up literal dictionary from Spanish to English and convert this. And the catch with translating any language, human or computer or otherwise, is that you're going to pay a price, typically some time. And so converting this in Spanish to this in English is just going to take you longer than if this were already in your native language. And that's going to be one of the subtleties with the world of Python. Yes, it's a feature that you can just run the code without having to bother compiling it manually first. But we might pay a price, and things might be a little slower. Now, there's ways to chip away at that, but we'll see an example thereof. In fact, let me transition now to just a couple of examples that demonstrate how Python is not only easier for many people to use, perhaps yourselves too, because it throws away a lot of the annoying syntax, it shortens the number of lines you have to write, and also it comes with so many darn libraries. You can just do so much more without having to write the code yourself. So as an example of this, let me switch over here to this image from problem set 4, which is the Weeks Bridge down by the Charles River here in Cambridge. And this is the original photo. Pretty clear, and it's even higher res if we looked at the original version of the photo. But there have been no filters a la Instagram applied to this photo. Recall for problem set 4, you had to implement a few filters, and among them might have been blur. And blur was probably among the more challenging of the ones because you had to iterate over all of the pixels. You had to take into account what's above, what's below, to the left, to the right. I mean, there was a lot of math and arithmetic. And if you ultimately got it, it was probably a great sense of satisfaction, but that was probably several hours later. In a language like Python, where there might be libraries that have been written by others on whose shoulders you can stand, we could perhaps do something like this. Let me go ahead and run a program or write a program called blur.py here. And in blur.py, in VS Code, let me just do this. let me import from a library, not the CS50 library, but the pillow library, so to speak, a keyword called image and another one called image filter. Then let me go ahead and say, let me open the current version of this image, which is called bridge.bmp. So the before version of the image will be the result of calling image.open, quote unquote, bridge.bmp. And then let me create an after version. So you'll see before and after. After equals the before version dot filter of image filter. And there is, if I read the documentation, I'll see that there's something called a box blur that allows you to blur in box format, like 1 pixel above, below, left, and right. So I'll do 1 pixel there. And then after that's done, let me go ahead and save the file as something like out.bmp. That's it. Assuming this library works as described, I am opening the file in Python using line 3. And this is somewhat new syntax. In the world of Python, we're going to start making use of the dot operator more. Because in the world of Python, you have what's called object-oriented programming, or OOP as a term of art. And what this means is that you still have functions, you still have variables, but sometimes those functions are embedded inside of the variables, or more specifically, inside of the data types themselves. Think back to C. When you wanted to convert something to uppercase, there was a toUpper function that takes as input an argument that's a char. And you can pass in any char you want, and it will uppercase it for you and give you back a value. Well, you know what? If that's such a common paradigm where uppercasing chars is a useful thing, what the world of Python does is it embeds into the string data type, or char if you will, the ability just to uppercase any char by treating the char or the string as though it's a struct in C. Recall that structs encapsulate multiple types of values. In object-oriented programming, in a language like Python, you can encapsulate not just values, but also functionality. Functions can now be inside of structs. But we're not going to call them structs anymore. We're going to call them objects. But that's just a different vernacular. So what am I doing here? Inside of the image library, there's a function called open, and it takes an argument, the name of the file, to open. Once I have a variable called before, that is a struct, or technically an object, inside of which is now, because it was returned from this function, a function called filter that takes an argument. The argument here happens to be image.boxblur1, which itself is a function, but it just returns the filter to use. And then after.save does what you might think. It just saves the file. So instead of using fopen and fwrite, you just say .save. And that does all of that messy work for you. So it's just, what, 4 lines of code total? Let me go ahead and go down to my terminal window. Let me go ahead and show you with ls that at the moment, whoops, sorry, let me not bother showing that because I have other examples to come. I'm going to go ahead and do Python of blur.py. Nope, sorry, wrong place. I did need to make a command. There we go. OK, let me go ahead and type ls inside of my filter directory, which is among the sample code online today. There's only one file called bridge.b. Damn it. I'm trying to get these things ready at the same time. Let me rewind. Let me move this code into place. All right, I've gone ahead and moved this file, blur.py, into a folder called filter, inside of which there's another file called bridge.bmp, which we can confer with ls. Let me now go ahead and run Python, which is my interpreter and also the name of the language, and run Python on this file. So much like running the Spanish algorithm through Google Translate or something like that as input to get back the English output, this is going to translate the Python language to something this computer or this cloud-based environment understands, and then run the corresponding code top to bottom, left to right. I'm going to go ahead and enter. No error message is generally a good thing. If I type ls, you'll now see out.bmp. Let me go ahead and open that. And you know what? Just to make clear what's really happening, let me blur it even further. Let's make a box that's not just 1 pixel around, but 10. So let's make that change. And let me just go ahead and rerun it with Python of blur.py. I still have out.bmp. Let me go ahead and open out.bmp and show you first the before, which looks like this. That's the original. And now, crossing my fingers, 4 lines of code later, the result of blurring it as well. So the library is doing all of the same kind of legwork that you all did for the assignment, but it's encapsulated it all into a single library that you can then use instead. Those of you who might have been feeling more comfortable might have done a little something like this. Let me go ahead and open up one other file called edges.py. And in edges.py, I'm again going to import from the pillow library the image keyword and the image filter. Then I'm going to go ahead and create a before image that's a result of calling image.open of the same thing, bridge.bmp. Then I'm going to go ahead and run a filter on that called image filter dot find edges, which is like a constant, if you will, defined inside of this library for us. And then I'm going to do after.save, quote unquote, out.bmp, using the same file name. I'm now going to run Python of edges.py. User error. We'll see what syntax error means soon. Let me go ahead and run the code now, edges.py. Let me now open that new file, out.pmp. And before we had this, and now, especially what will look familiar if you did the more comfortable version of pset4, we now get this after just 4 lines of code. So again, suggesting the power of using a language that's better optimized for the tool at hand. And at the risk of really making folks sad, let's go ahead and re-implement, if we could, problem set 5 real quickly here. Let me go ahead and open another version of this code wherein I have a C version just from problem set 5, wherein you implemented a spell checker loading 100,000 plus words into memory. And then you kept track of just how much time and memory it took. And that probably took a while, implementing all of those functions in dictionary.c. Let me instead now go into a new file called dictionary.py. And let me stipulate for the sake of discussion that we already wrote in advance speller.py, which corresponds to speller.c. You didn't write either of those. Recall for problem set 5, we gave you speller.c. Assume that we're going to give you speller.py. So the onus on us right now is only to implement dictionary.py. All right, so I'm going to go ahead and define a few functions, and we're going to see now the syntax for defining functions in Python. I want to go ahead and define first a hash table, which was the very first thing you defined in dictionary.c. I'm going to go ahead then and say words gets this. Give me a dictionary, otherwise known as a hash table. All right, now let me define a function called check, which was the first function you might have implemented. Check is going to take a word, and you'll see in Python the syntax is a little different. You don't specify the return type. You use the word def instead to define. You still specify the name of the function and any arguments there too, but you omit any mention of types, but you do use a colon and indent. So how do I check if a word is in my dictionary or in my hash table? Well, in Python, I can just say if word in words, go ahead and return true, else go ahead and return false. Done with the check function. All right, now I want to do like load. That was the heavy lift where you had to load the big file into memory. So let me define a function called load. It takes a string, the name of a file, to load. So I'll call that dictionary, just like in C, but no data type. Let me go ahead and open a file by using an open function in Python by opening that dictionary in read mode. So this is a little similar to fopen, a function in C you might recall. Then let me iterate over every line in the file. In Python, this is pretty pleasant. For line in file, colon, indent. How now do I get at the current word and then strip off the new line? Because in this file of words, the 140,000 words, there's word \n, word \n. All right? Well, let me go ahead and get a word from the current line, but strip off from the right end of the string the new line, which the rstrip function in Python does for me. Then let me go ahead and add to my dictionary or hash table that word. Done. Let me go ahead and close the file for good measure. And then let me go ahead and return true because all was well. That's it for the load function in Python. How about the size function? This did not take any arguments. It just returns the size of the hash table or dictionary. In Python, I can do that by returning the length of the dictionary in question. And then lastly, gone from the world of Python is malloc and free. Memory is managed for you. So no matter what I do, there's nothing to unload. The computer will do that for me. So I give you in these functions problem set 5 in Python. So I'm sorry, we made you write it in C first. But the implication now is that what are you getting for free in a language like Python? Well, encapsulated in this one line of code is much of what you wrote for problem set 5, implementing your array for all of your letters of the alphabet or more, all of the linked lists that you implemented to create chains to store all of those words. All of that is happening. It's just someone else in the world wrote that code for you, and you can now use it by way of a dictionary. And actually, I can change this a little bit because add is technically not the right function to use here. I'm actually treating the dictionary as something simpler, a set. So I'm going to make one tweak. Set, recall, was another data type in Python. But set just allows it to handle duplicates, and it allows me to just throw things into it by literally using a function as simple as add. And I'm going to make one other tweak here. Because when I'm checking a word, it's possible it might be given to me in uppercase or capitalized. It's not going to necessarily come in the same lowercase format that my dictionary did. I can force every word to lowercase by using word.lower. And I don't have to do it character for character. I can do the whole darn string at once by just saying word.lower. All right, let me go ahead and open up a terminal window here. And let me go into first my C version on the left. And actually, I'm going to go ahead and split my terminal window into two. And on the right, I'm going to go into a version that I essentially just wrote, but it's also available online if you want to play along afterward. I'm going to go ahead and make speller in C on the left. And note that it takes a moment to compile. Then I'm going to be ready to run speller of dictionaries. Let's do like the Sherlock Holmes text, which is pretty big. And then over here, let me get ready to run Python of speller on texts/holmes.txt2. So the syntax is a little different at the command prompt. I just, on the left, have to compile the code with make and then run it with /speller. On the right, I don't need to compile it, but I do need to use the interpreter. So even though the lines are wrapping a little bit here, let me go ahead and run it on the right. And I'm going to count how long it takes verbally for demonstration's sake. 1 Mississippi, 2 Mississippi, 3 Mississippi. OK, so it's like 3 seconds, give or take. Now running it in Python, keeping in mind, I spent way fewer hours implementing a spell checker in Python than you might have in problem set 5. But what's the trade-off going to be? And what kinds of design decisions do we all now need to be making consciously? Here we go, on the right in Python. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, 8 Mississippi, 9 Mississippi, 10 Mississippi, 11 Mississippi. All right, so 10 or 11 seconds. So which one is better? Let's go to the group here. Which of these programs is the better one? How might you answer that question based on demonstration alone? What do you think?
I think Python is better for the programmer, or more comfortable for the programmer, but C is better for the user.
OK, so Python, to summarize, is better for the programmer because it was way faster to write. But C is maybe better for the computer because it's much faster to run. I think that's a reasonable formulation. Other opinions? Yeah.
I think it depends on the size of the project that you're dealing with. So if it's going to be something that's relatively quick, I might not care that it takes 10 seconds to do it, and it took me way faster to do it in Python. Whereas in C, if I'm dealing with something like a massive data set or something huge that that time is going to really build up on, it might be worth it to put in the upfront effort and just coding it in C so that the process continually runs faster over a longer period of time.
Absolutely. A really good answer. And let me summarize is it depends on the workload, if you will. If you have a very large data set, you might want to optimize your code to be as fast and performant as it can be, especially if you're running that code again and again. Maybe you're a company like Google. People are searching a huge database all the time. You really want to squeeze every bit of performance as you can out of the computer. You might want to have someone smart take a language like C and write it at a very low level. It's going to be painful. They're going to have bugs. They're going to have to deal with memory management and but if and when it works correctly, it's going to be much faster, it would seem. By contrast, if you have a data set that's big, and 140,000 words is not small, but you don't want to spend like 5 hours, 10 hours, a week of your time building a spell checker or a dictionary, you can instead leverage a different language with different libraries and build on top of it in order to prioritize the human time instead. Other thoughts? That perfect segue to exactly the next point we wanted to make, which was, is there something in between? And indeed there is. I'm oversimplifying what this language is actually doing. It's not as stark a difference as saying like, hey, Python is 4 times slower than C. Like that's not the right takeaway. There are absolutely ways that engineers can optimize languages as they have already done for Python. And in fact, I've configured my settings in such a way that I've kind of dramatized just how big the difference is. It is going to be slower Python typically than the equivalent C program, but it doesn't have to be as big of a gap as it is here, because indeed among the features you can turn on in Python is to save some intermediate results. Technically speaking, yes, Python is interpreting dictionary.py and these other files, translating them from one language to another. But that doesn't mean it has to do that every darn time you run the program. As you propose, you can save or cache, C-A-C-H-E, the results of that process so that the second time and the third time are actually notably faster. And in fact, Python itself, the interpreter, the most popular version thereof, itself is actually implemented in C, so you can make sure that your interpreter is as fast as possible. And what then is maybe the high-level takeaway? Yes, if you are going to try to squeeze every bit of performance out of your code, and maybe code is constrained. Maybe you have very small devices. Maybe it's like a watch nowadays, or maybe it's a sensor that's installed in some small format in an appliance or in infrastructure where you don't have much battery life and you don't have much size. You might want to minimize just how much work is being done. And so the faster the code runs, and the better it's going to be if it's implemented something low level. So C is still very commonly used for certain types of applications. But again, if you just want to solve real world problems and get real work done, and your time is just as, if not more valuable than the device you're running it on long term, you know what? Python is among the most popular languages as well. And frankly, if I were implementing a spell checker moving forward, I'm probably starting with Python. And I'm not going to waste time implementing all of that low level stuff, because the whole point of using newer modern languages is to use abstractions that other people have created for you. And by abstraction, I mean something like the dictionary function that just gives you a dictionary or hash table, or the equivalent version that I used, which in this case was a set. All right, any questions then on Python thus far? No? All right, oh yeah, in the middle. Really good question or observation. Could you just compile Python code? Yes, absolutely. This idea of compiling code or interpreting code is not native to the language itself. It tends to be native to the conventions that we humans use. So you could actually write an interpreter for C that would read it top to bottom, left to right, converting it to, on the fly, something the computer understands. But historically, that's not been the case. C is generally a compiled language, but it doesn't have to be. What Python nowadays is actually doing is what you described earlier. It technically is, sort of unbeknownst to us, compiling the code, technically not into zeros and ones, technically into something called bytecode, which is this intermediate step that just doesn't take as much time as it would to recompile the whole thing. And this is an area of research for computer scientists working in programming languages to improve these kinds of paradigms. Why? Well, honestly, for you and I, the programmer, it's just much easier to, one, run the code and not worry about the stupid second step of compiling it all the time. Why? It's literally half as many steps for me, the human, and that's a nice thing to optimize for. And ultimately, two, you might want all of the fancy features that come with these other languages. So you should really just be fine-tuning how you can enable these features as opposed to shying away from them here. And in fact, the only time I personally ever use C is from like September to October of every year during CS50. Almost every other month do I reach for Python or another language called JavaScript to actually get real work done, which is not to impugn C. It's just that those other languages tend to be better fits for the amount of time I have to allocate and the types of problems that I want to solve. All right, let's go ahead and take a 5-minute break here. And when we come back, we'll start writing some programs from scratch. All right, so let's go ahead and start writing some code from the beginning here, whereby we start small with some simple examples, and then we'll build our way up to more sophisticated examples in Python. But what we'll do along the way is first look side by side at what the C code looked like way back in week 1 or 2 or 3 and so forth, and then write the corresponding Python code at right, and then we'll transition just to focusing on Python itself. What I've done in advance today is I've downloaded some of the code from the course's website, my source 6 directory, which contains all of the pre-written C code from weeks past, but it'll also have copies of the Python code we'll write here together and look at. So first, here is hello.c back from week 0. This was version 0 of it. I'm going to go ahead and do this. I'm going to go ahead and split my code window up here. I'm going to go ahead and create a new file called hello.py. And this isn't something you'll typically have to do, laying your code out side by side. But I've just clicked the little icon in VS Code that looks like 2 columns that splits my code editor into 2 places so that we can, in fact, see things for now side by side with my terminal window down below. All right, now I'm going to go ahead and write the corresponding Python program on the right, which, recall, was just print, quote unquote, hello world, and that's it. Now down in my terminal window, I'm going to go ahead and run Python of hello.py, enter, and voila, we've got hello.py working. So again, I'm not going to play any further with the C code. It's there just to jog your memory left and right. So let's now look at a second version of hello world from that first week, whereby if I go and get hello1.c, I'm going to drag that over to the right. Whoops. I'm going to go ahead and drag that over to the left here. And now on the right, let's modify hello.py to look a little more like this second version in C. All right, I want to get a answer from the user as a return value, but I also want to get some input from them. So from CS50, I'm going to import the function called getString for now. We're going to get rid of that eventually, but for now it's a helpful training wheel. And then down here, I'm going to say answer equals getString, quote unquote, what's your name, question mark, space, but no semicolon, no data type. And then I'm going to go ahead and print, just like the first example on the slide, hello, comma, space, plus answer. And now let me go ahead and run this. Python of hello.py. All right, it's asking me what's my name, David, hello, comma, David. But it's worth calling attention to the fact that I've also simplified further. It's not just that the individual functions are simpler. What is also now glaringly omitted from my Python code at write, both in this version and the previous version? What did I not bother implementing? Yeah, so I didn't even need to implement main. We'll revisit the main function because having a main function actually does solve problems sometimes, but it's no longer required. In C, you have to have that to kickstart the entire process of actually running your code. And in fact, if you were missing main, as you might have experienced if you accidentally compiled helpers.c instead of the file that contained main, you would have seen a compiler error. In Python, it's not necessary. Python, you can just jump right in, start programming, and boom, you're good to go. Especially if it's a small program like this, you don't need the added overhead or complexity of a main function. So that's one other difference here. All right, there were a few other ways we could say hello world. Recall that I could use a format string. So I could put this whole thing in quotes. I could use this f prefix. And then let me go ahead and run python of hello.py again. You can perhaps see where we're going with this. Let me type my name, David, and here we go. OK, that's the mistake that someone identified earlier. You need the curly braces. Otherwise, no variables are interpolated, that is, substituted with their actual values. So if I go back in and add those curly braces to the f string, now let me run python of hello.py, type in my name, and there we go. We're back in business. Which one's better? I mean, it depends. But generally speaking, making shorter, more concise code tends to be a good thing. So stylistically, the f string is probably a reasonable instinct to have. All right, well, what more can we do besides this? Well, let me go ahead here and let's get rid of the training wheel altogether, actually. So same C code at left. Let me get rid of the CS50 library, which we will ultimately in a couple of weeks anyway. I can't use getString, but I can use a function that comes with Python called input. And in fact, this is actually a one-for-one substitution pretty much. There's really no downside to using input instead of getString. We implement getString just for consistency with what you saw in C. Python of hello.py, what's your name, David, still actually works the same. So gone are the CS50 specific training wheels, but we're going to bring them back shortly just to deal with integers or floats or other values too, because it's going to make our lives a little simpler with error checking. All right, any questions before we now pivot to revisiting other examples from week 1, but now in Python? All right, let me go ahead and open up now, let's say calculator0.c, which was one of the first examples we did involving math and operators like that, as well as functions like getInt. Let me go ahead and create a new file now called calculator.py at write, so that I have my C code at left still and my Python code at right. All right, let me go dive into a translation of this code into Python. I am going to use getInt from the CS50 library, so let me import that. I'm going to go ahead now and get an int from the user. So int x equals getInt, and I'll ask them for an x value, just like we did weeks ago. No need to specify a semicolon, though, or a int for the x. It will just figure it out. Y is going to get another int via y colon. And then down here, I'm going to go ahead and say print of x plus y. So this is already a bit new. Recall the C version required that I use this format string as well as printf itself. Python's just a little more user-friendly. If all you want to do is print out a value like x plus y, just print it. Don't futz with any percent signs or format codes. It's not printf. It's indeed just print now. All right, let me go ahead and run python of calculator.py. Enter. And just do a quick sample. 1 plus 2 indeed equals 3. As an aside, suppose I had taken a different approach to importing the whole CS50 library. Functionally, it's the same. You're not going to notice any performance impact here. It's a small library. But notice what does not work now, whereas it did work in C. Python of calculator.py, enter. we see our first traceback deliberately here. So a traceback is just a term of art that says here is a trace back through all of the functions that just got executed. In the world of C, you might call this a stack trace, stack being the operative word. Recall that when we talked about the stack and the heap, the stack, like a stack of trays, was all of the functions that might get called one after the other. We had main, we had swap, then swap went away, and then main finished. Recall? So here's a traceback of all of the functions or code that got executed. There's not really any functions other than my file itself. Otherwise, there'd be more detail. But even though it's a little cryptic, we can perhaps infer from the output here. Name error, so something related to the name of something. Name getInt is not defined. And this, of course, happens on line 3 over there. All right, so why is that? Well, Python essentially allows us to namespace our functions that come from libraries. There was a problem in C. If you were using the CS50 library and thus had access to getInt, getString, and so forth, you could not use another library that had the same function names. They would collide, and the compiler would not know how to link them together correctly. In Python and other languages like JavaScript and in Java, you have support for effectively what would be called namespaces. You can isolate variables and function names to like their own namespace, like their own container in memory. And what this means is if you import all of CS50, you have to say that the getInt you want is inside the CS50 library. So just like with the image blurring and the image edges before, where I had to specify image dot and image filter dot, similarly here, am I specifying with a dot operator, albeit a little differently, that I want CS50.getInt in both places. And now if I rerun Python of calculator.py, 1 and 2, now we're back in business. Which one is better? Generally speaking, it depends on just how many functions you're using from the library. If you're using a whole bunch of functions, just import the whole thing. If you're only using maybe 1 or 2, import them line by line. All right, so let's go ahead and make a little tweak here. Let's get rid of this library and take this training wheel off too, as quickly as we introduced it. Though for the problem set 6, you'll be able to use all of these same functions. Suppose I get rid of this and I just use the input function, just like I did by replacing getString earlier. Let me go ahead now and run this version of the code, Python of calculator.py. OK, how about 1 plus 2 equals 3? Huh. All right, obviously wrong, incorrect. Can anyone explain what just happened based on instincts? What just happened here? Yeah. Sure, yeah. Exactly. Python is interpreting or treating both x and y as strings, which is actually what the input function returns by default. And so plus is now being interpreted as concatenation as we defined it earlier. So x plus y isn't x plus y mathematically, but in terms of string joining, just like in Scratch. So that's why we're getting 12, or really 1, 2, which isn't itself a number. It too is another string. So we somehow need to convert things. And we didn't have this ability quite as easily in C. We did have like the a to I function, ASCII to integer, which did allow you to do this. The analog in Python is actually just to do a cast, a typecast using int. So just like in C, you can use the keyword int, but use it a little differently. Notice that I'm not doing parenthesis, int, close parenthesis before the value. I'm using int as a function. So indeed, in Python, int is a function. Float is a function that you can pass values into to do this kind of conversion. So now if I run Python of calculator.py, 1 and 2, now we're back in business and getting the answer of 3. But there's kind of a catch here. There's always going to be a trade-off. Like, that sounds amazing that it just works in this way. We can throw away the CS50 library already. But what if the user accidentally types or maliciously types in like a cat instead of a number? Damn, well, there's one of these tracebacks. Like, now my program has crashed. This is similar in spirit to the kinds of seg faults that you might have had in C. But they're not seg faults per se. It doesn't necessarily relate to memory. This time it relates to actual runtime values not being as expected. So this time it's not a name error. It's a value error. Invalid literal for int with base 10, quote unquote, cat. So again, it's written for sort of a programmer more than sort of a typical person, because it's pretty arcane, the language here. But let's try to interpret it. Invalid literal. A literal is just something someone typed. For int, which is the function name with base 10, it's defaulting to decimal numbers. CAT is apparently not a decimal number. It doesn't look like it, therefore can't be treated like it. Therefore, there's a value error. So what can we do? Unfortunately, you would have to somehow catch this error. And the only way to do that in Python really is by way of another feature that C did not have, namely what are called exceptions. An exception is exactly what just happened. Name error, value error. They are things that can go wrong when your Python code is running that aren't necessarily going to be detected until you run your code. So in Python and in JavaScript and in Java and other more modern languages, there's this ability to actually try to do something except if something goes wrong. And in fact, I'm going to introduce a bit of syntax here, even though we won't have to use this much just yet. Instead of just blindly converting x to an int, let me go ahead and try to do that. And if there's an exception, go ahead and say something like print that is not an int. And then I'm going to do something like exit right there. And let me go ahead and do this here. Let me try to get y, except if there's an exception. Then let me go ahead and say, again, that is not an int, exclamation point. And then I'm going to exit from there too. Otherwise, I'll go ahead and print x plus y. If I run Python of calculator.py now, whoops. Forgot my close quote. Sorry. All right, so close quote. Python of calculator.py, 1 and 2 still work. But if I try to type in something wrong like cat, now it actually detects the error. So what is the CS50 library in Python doing? It's actually doing that try and except for you. Because suffice it to say, otherwise your programs for something simple like a calculator start to get longer and longer. So we factored that kind of logic out to the CS50 getInt function and getFloat function. But underneath the hood, they're essentially doing this, try, except, but they're being a little more precise. They're detecting a specific error. And they are doing it in a loop so that these functions will get executed again and again. In fact, the best way to do this is to say, except if there's a value error, then print that error message out to the user. And again, let's not get too into the weeds here with this feature. We've already put it into the CS50 library. But that's why, for instance, we bootstrap things by just using these functions out of the box. All right, let's do something more with our calculator here. How about this? In the world of C, we had another version of this code which actually did some division by way of, which actually did division of numbers, not just the addition herein. So let me go ahead and close the C version. And let's focus only on Python now, doing some of these same lines of codes. But I'm going to go ahead and just assume that the user is going to cooperate and use proper input. So from CS50, import getInt. That'll deal with any errors for me. X gets getInt, ask the user for an int x. Y equals getInt, ask the user for an int y. And then let's go ahead and do this. Let's declare a variable called z, set it equal to x divided by y. Then let's go ahead and print z. Still no need for a format string. I can just print out the variable's value. Let me go ahead and run Python of calculator.py. Let me do 1, 10, and I get 0.1. What did I get in C, though? If you think back, what would we have happened in C? Yeah, we would have gotten 0 in C, but why in C? When you divide one int by another, and those ints are like 1 and 10, respectively. It will give you what? It will give you an integer back, and unfortunately, 0.1, the integer part of it is indeed 0. So this was an example of truncation. So truncation was an issue in C, but it would seem as though this is no longer a problem in Python insofar as the division operator actually handles that for us. As an aside, if you want the old behavior, because it actually is sometimes useful for rounding or flooring values, you can actually use 2 slashes, and now you get the C behavior so that now 1 divided by 10 is 0. So you don't give up that capability, but at least it does a more sensible default. Most people, especially new programmers, when dividing one value by another, would want to get 0.1, not 0, for reasons that indeed we had to explain weeks ago. But what about another problem we had with the world of floats before, whereby there was imprecision? Let me go ahead and somewhat cryptically print out the value of z as follows. I'm going to format it using an f string, and I'm going to go ahead and format not just z, because this is essentially the same thing. Notice this. If I do Python of calculator.py, 1 and 10, I get by default just 1 significant digit. But if I use this syntax in Python, which you won't have to use often, I can actually do in C, like I did before, 50 significant digits after the decimal point. So now let me rerun Python of calculator.py, 1, and 10. And let's see if floating point imprecision is still with us. Unfortunately, it is. And you can see as much here. The F string, the format string, is just showing us now 50 digits instead of the default 1. So we've not solved all problems, but we have solved at least some. All right, before we pivot away from a mere calculator, any questions now on syntax or concepts or the like? Yeah?
So you use like the double slash to get the there. How do you comment?
How do you what? Oh, how do you comment? Really good question. If you're using double slash for division with flooring or truncation, like I described, how do you do a comment in Python? This is a comment. And the convention is actually to use a complete sentence, like with a capital T here. You don't need a period unless there's multiple sentences. And technically, it should be above the line of code by convention. So you would use a hash symbol instead. Good question. Haven't seen those yet. All right, let's go ahead and make something else here. How about? Let me go ahead and open up, for instance, an example called points1.c, which we saw a few weeks back. And let me go ahead on the other side and create a file called points.py. This was a program, recall, that asked the user how many points they lost on the first assignment, and then it went ahead and just printed out whether they lost fewer points than me, because I lost 2 if you recall the photo, more points than me, or the same points as me. Let me go ahead and zoom out so we can see a bit more of this. And let me now, on the top right here, go about implementing this in Python. So I want to first prompt the user for some number of points. So from CS50, let's import getInt, so it handles the error checking. Let's then do points equals getInt and ask the user, how many points did you lose? Question mark. Then let's go ahead and say if points less than 2, which was my value, print you lost fewer points than me. Otherwise, if it's else if points greater than 2, go ahead and print you lost more points than me. Else, let's go ahead and handle the final scenario, which is you lost the same number of points as me. Before I run this, does anyone want to point out a mistake I've already made? Yeah. Yeah, so else if in C is actually now elif in Python. It's a single word. So let me change this to elif and now cross my fingers. Python of points.py. Suppose you lost 3 points on some assignment. You lost more points than my 2. If you only lost 1 point, you lost fewer points than me. So the logic is the same, but notice the code is much tighter. In 10 total lines, we did in what was 24 lines because we've thrown away a lot of the syntax. The curly braces are no longer necessary. The parentheses are gone, the semicolons. So this is why it just tends to be more pleasant pretty quickly using a language like this. All right, let's do one other example here. In C, recall that we were able to determine the parity of some number, if something is even or odd. Well, in Python, let me go ahead and create a file called parity.py. And let's look for a moment at the C version at left. Here was the code in C that we used to determine the parity of a number. And really, the key takeaway from all these lines was just the remainder operator. And that one is still with us. So this is a simple demonstration just to make that point. If in Python, I want to determine whether a number is even or odd, well, let's go ahead and from CS50 import getInt. Then let's go ahead and get a number like n from the user using getInt. And ask them for n. And then let's go ahead and say if n %2 equals 0, then let's go ahead and print, quote unquote, even. Else, let's go ahead and print out odd. But before I run this, anyone want to instinctively, even though we've not talked about this, point out a mistake here? What did I do wrong? Yeah, so double equals. Again, so even though some of the stuff is changing, some of the same ideas are the same. So this too should be a double equal sign because I'm comparing for equality here. And why is this the right math? Well, if you divide a number by 2, it's either going to have 0 or 1 as a remainder. And that's going to determine if it's even or odd for us. So let's run Python of parity.py, type in a number like 50, and hopefully we get indeed even. So again, same idea, but now we're down to 8 lines of code instead of the 20. Well, let's now do something a little more interactive and a little representative of tools that actually ask the user questions. In C, recall that we had this agreement program, agree.c. And then let's go ahead and implement a corresponding version in Python in a file called agree.py. And let's look at the C version first. On the left, we used getChar here. And then we use the double vertical bars to check if C is equal to capital Y or lowercase y. And then we did the same thing for n for no. And so let's go over here And let's do from CS50 import get. OK, get char is not a thing. And this here is another difference with Python. There is no data type for individual characters. You have strings, strs, and honestly, those are fine. Because if you have a str that's just one character, for all intents and purposes, it is just a single character. So it's just a simplification. You don't have to think as much. You don't have to worry about double quotes, single quotes. In fact, in Python, you can use double quotes or single quotes so long as you're consistent. So long as you're consistent, the single quotes do not mean something different like they do in C. So I'm going to go ahead and use getString here. Although strictly speaking, I could just use the input function, as we saw before. I'm going to get a string from the user that asks them this. GetString, quote unquote, do you agree? Like a little checkbox or interactive prompt where you have to say yes or no, you want to agree to the following terms or whatnot. And then let's translate the conditionals to Python now too. So if s equals equals quote unquote y, or s equals equals lowercase y, let's go ahead and print out agreed, just like in C. If s equals equals n, or s equals equals little n, let's go ahead then and print out not agreed. And you can already see perhaps one of the differences here too is Python a little more English-like in that you just literally use the English word or instead of the two vertical bars, but it's ultimately doing the same thing. Can we simplify this code a bit, though? This would be a little annoying if we wanted to add support, not just for big Y and little y, but yes, or big yes, or little yes, or big Y, lowercase e, capital S, right? There's a lot of permutations of Y, E, S, or just Y that we ideally should tolerate. Otherwise, the user is going to have to type exactly what we want, which isn't very user-friendly. Any intuition for how we could logically, even if you don't know how to do it in code, make this better? Yeah. Nice. Yeah, we saw an example of a list before, just 0, 1, 2. Why don't we take that same idea and ask a similar question? If s is in the following list of values, y, or little y, or heck, let me add to the list now, yes, or maybe all capital yes. And it's going to get a little annoying, admittedly, but this is still better than the alternative with all the ors. I could do things like this and so forth. There's a whole bunch more permutations, but let's leave this alone. And let me just go into here and change this to if s is in the following list of n, or little n, or no. And I won't do as, let's just not worry about the weird capitalizations there for now. Let's go ahead and run this. Python of agree.py. Do I agree? Y. OK, how about yes? All right, how about big yes? OK, that does not seem to work. Notice it did not say agreed, and it did not say not agreed. It didn't detect it. So how can I do this? Well, you know what I could do? I don't really need the uppercase and lowercase. Let me tighten this list up a little bit. And why don't I just force s to be lowercase? S.lower, recall, whether it's one character or more, is a function built into strs now, strings in Python, that forces the whole thing to lowercase. So now watch what I can do. Python of agree.py, little y, that works. Big Y, that works. Big yes, that works. Big Y, little e, big S, that also works. So we've now handled in one fell swoop a whole bunch more logic. And you know what? We can tighten this up a bit. Here's an opportunity in Python for slightly better design. What have I done in here that's a little redundant? Does anyone see an opportunity to eliminate a redundancy? Doing something more than times than you need is a stretch or no? Yep. We could move the s.lower above. Notice that I'm using s.lower twice, but it's going to give me the same answer both times. So I could do a couple of things here. I could, first of all, get rid of this lower and get rid of this lower. And then above this, maybe I could do something like this. S equal, I can't just do this because that throws the value away. It does the math, but it doesn't convert the string itself. It's going to return a value. So I have to say s equals s.lower. I could do that. Or honestly, I can chain these things together. And this is not something we saw in C. If getString returns a string, and strings have functions like lower in them, you can chain these functions together like this and do dot this, dot that, dot this other thing. And eventually you want to stop because it's going to become crazy long. But this is reasonable. Still fits on the screen. It's pretty tight. It does in one place what I was doing in two. So I think that's OK. Let me go ahead and do Python of agree.py one last time. Let's try it one last time. And it's still working as intended. Also, if I tried those other inputs as well. Yeah, question? Let me summarize. Could we handle uppercase and lowercase together in some form? I'm actually doing that already. I just have to pick a lane. I have to either be all lowercase in my logic or all uppercase and not worry about what the human types in, because no matter what the human types in, I'm forcing their input to lowercase. And then I am using a lowercase list of values. If I want to flip that, fine. I just have to be self-consistent. But I'm handling that already. Yeah? A really good loaded question. Are strings no longer an array of characters? Conceptually, yes. Underneath the hood, no. They're a little more sophisticated than that. Because with strings, you have a few changes. Not only do they have functions built into them, because strings are now what we call objects in what's called object-oriented programming. And we're going to keep seeing examples of this dot operator. They are also immutable, so to speak. I-M-M-U-T-A-B-L-E. Immutable means they cannot be changed, which means unlike C, you can't go into a string and change its individual characters. You can make a copy of the string that makes a change, but you can't change the original string itself. This is both a little annoying maybe sometimes, but it's also pretty protective because you can't do screw ups like I did weeks ago when I was trying to copy S and call it T and then one affected the other. Python underneath the hood is handling all of the memory management and the pointers and all of that. There are no pointers in Python. So if that wasn't clear, all of that pain, if you will, all of that power is now handled by the language itself, not by us, the programmers. All right, so let's introduce maybe some loops like we've been in the habit of doing. Let me open up meow.c, which was an example in C, just meowing a bunch of times textually. Let me create a file called meow.py here on the right. And notice on the left, this was correct code in C, but it was kind of poorly designed. Why? Because it was a missed opportunity for a loop. Why say something 3 times when you can say it just once? So in Python, let me do it the poorly designed way first. Let me print out meow. And like I generally should not, let me copy paste it 3 times, run python of meow.py, and it works. OK, but not good practice. So let me go ahead and improve this a little bit. And there's a few ways to do this. If I wanted to do this 3 times, I could instead do something like this. For I in range of 3, recall that that was the better version rather than arbitrarily enumerate numbers yourself. Let me go ahead and print out, quote unquote, meow. Now if I run python of meow, still seems to work. So it's a little tighter. And my God, like programs can't really get much shorter than this. We're down to 2 lines of code, no main function, no gratuitous syntax. Let's now improve the design further like we did in C by introducing a function called meow that actually does the meowing. So this was our first abstraction, recall, both in Scratch and in C. Let me focus now entirely on the Python version here. Let me go ahead and first define a function. Let me first go ahead and do this. For I in range of 3, let's assume for the moment that there's a meow function that I'm just going to call. Let's now go ahead and define, using the def keyword, which we saw briefly with the speller demonstration, a function called meow that takes no arguments, and all it does for now is print meow. Let me now go ahead and run python of meow.py, enter. One of those tracebacks. So this is another name error. And again, name meow is not defined. What's your instinct here, even though we've not tripped over this yet in Python? Where does your mind go here? Yeah.
Because it reads top, bottom, left, and right, and it hasn't yet seen anything defined in the new
Perfect. As smarter as Python seems to be, it still makes certain assumptions. And if it hasn't seen a keyword yet, it just doesn't exist. So if you want it to exist, we have to be a little clever here. I could just flip it around like this. But this honestly isn't particularly good design. Why? Because now if you, the reader of your code, whether you wrote it or someone else, you kind of have to go fishing now. Like, where does this program begin? And even though, yes, it's obviously that it begins on line 4, logically, like if the file were longer, you're going to be annoyed and fishing visually for the right lines of code. So let's reintroduce main. And indeed, this would be a common paradigm when you want to start having abstractions and your own functions. Just put your own code in main so that 1, you can leave it up top, and 2, you can solve the problem we just encountered. So let me define a function called main that has that same loop meowing 3 times. But now watch what happens. Let me go into my terminal and run python of meow.py, enter. Nothing. All right. Investigate this. What could explain this symptom? I have not told you the answer yet. So all you have is your instinct, assuming you've never touched Python before. What might explain this symptom where nothing is meowing? Yeah. Yeah, I didn't run the main function. So in C, this is functionality you get for free. You have to have a main function, but heck, so long as you make it, it will be called for you. In Python, this is just a convention to create a main function, borrowing a very common name for it. But if you want to call that main function, you have to do it. So this looks a little weird, admittedly, that you have to call your own main function now. And it has to be at the bottom of the file, because only once the interpreter gets to the bottom of the file have all of your functions been defined higher up. But this solves both problems. It keeps your code, that's the main part of your code, at the very top of the file. So it's just obvious to you and a TF or any reader in the future where the program logically starts. But it also ensures that main is not called until everything else, main included, has been defined. So this is another perfect example of we're learning a new language for the first time. You're not going to have heard all of the answers before. Just apply some logic as to like, all right, what could explain this symptom? Start to infer how the language does or doesn't work. If I now go and run this, Python of meow.py, now we're back in business. And just so you have seen it, there is a quote unquote better way of doing this that solves different problems that we are not going to encounter, certainly in these initial days. Typically, you would see in online tutorials or books something that looks like this, where you actually have a weird conditional with multiple underscores. That's functionally the same thing, but it solves problems with libraries if we ourselves were implementing a library or something similar in spirit. But we're going to keep things simpler and just write main at the bottom, because we're not going to encounter that problem just yet. All right, let's make one change to this just to show how it's done. In C, the last version of meow also took arguments to the function meow. So suppose that I want to factor this out, and I want to just call meow as a better abstraction, where I just say meow this number of times. And I figure out how many times by just like putting in number 3 or using getInt or something like that to figure out how many times to say meow. Well, now I have to define inside my meow function in input, let's call it n, and then use that as by doing this. For I in range of n, let me go ahead and print out meow that many times. So again, the only thing that's different in C is we don't bother specifying return types for any of these functions, and we don't bother specifying the type of our arguments or our variables. So same ideas, simpler in some sense. We're just throwing away keystrokes. All right, let me run this one final time, Python of meow.py, and we still have the same program. All right, let me pause here. Any questions? And I know this is going fast, but hopefully the C code is still somewhat familiar. Yeah?
Are there any differences between global and local variables?
Good. Good question. Is there any difference between global and local variables? Short answer, yes. And we would run into that same problem. If we declare a variable in one function, another function is not going to have access to it. We can solve that by putting variables globally, but we don't have all of the features we had in C. Like there's no such thing as a constant in Python. The mentality in the Python community is if you don't want some value to change, don't touch it. Like just don't screw up. So there's trade-offs here too. Some languages are stronger or more defensive than that, but that too is part of the mindset with this particular language. Yeah. Oh, sorry. Say it louder. That is an amazing segue. Let's come to that in just a moment, because we're going to recreate also that Mario example where we had like the question marks for the coins and the vertical bars. So let's come back to that in a second. And your question? Correct. Strings are immutable. Anytime you seem to be modifying it, as with the lower function, you're getting back a copy. So it's taking a little more memory somewhere, but you don't have to deal with it. Python's doing that for you. Say it again. You don't need what? You don't free anything. So if you weren't a big fan over the past couple of weeks of malloc or free or memory or addresses or all of those low-level implementation details, Python is the language for you, because all of that is handled for you automatically. Java does the same. JavaScript does the same. Yeah? How do you define a global variable if there's no main function in Python? Global variables, by definition, always need to be outside of main as well. So that's not a problem. If I wanted to have a function that's outside of and therefore global to all of these, like global, actually don't use the word global, that's a special word in Python, variable equals foo. FOO, just as an arbitrary string value that a computer scientist would typically use, that is now global. There are some caveats, though, as to how you access that, but let's come back to that another time. But that problem is solvable, too. All right, so let's go ahead and do this to come back to the question about the print command. Let me go ahead and create a file now called mario.py. Won't bother showing the C code anymore. We'll focus just on the new language here. But recall that in Mario, we wanted to first do something like this. This was a random screen from the side scroller version 1 of Super Mario Brothers. And we just want to print like 3 hashes to represent those 3 blocks. Well, in Python, we could do something like this. Print, for I in the range of 3, go ahead and print out, quote unquote, hash. And I think this is pretty straightforward. Python of mario.py, we get our 3 hashes. You could imagine parameterizing this now, though, and getting actual user input. So let's do that. Let me go up here, and let me go and say from CS50 import getInt. And then let's get the input from the user. So it actually is a value n. Like, all right, getInt the height of the column of bricks that you want to do. And then let's go ahead and print out n hashes instead of 3. So let me run this. Let's print out like 5 hashes. OK, 1, 2, 3, 4, 5. That seems to work, too. And it's going to work for any positive value. But it's not going to work for, how about -1? That just doesn't do anything. But that seems OK. But also recall that it's not going to work if the user types in something weird like it is going to work if the user types in something weird like cat. Why? We're using CS50's getInt function, which is handling all of those headaches for us. But what if the user indeed types a negative number? We're tolerating that. So that was the bug I wanted to highlight. It would be nice to reprompt them and reprompt them. And in C, what was the programming construct we used when we wanted to ask the user a question, and then if they didn't cooperate, prompt them again, prompt them again? What was that? Yeah, do while loop, right? That was useful because it's almost the same as a while loop. But instead of checking a condition and then doing something, you do something and then check a condition, which makes sense with user input because what are you even going to check if the user hasn't done anything yet? You need that inverted logic. Unfortunately, in Python, there is no do while loop. There is a for loop. There is a while loop. And frankly, those are enough to recreate this idea. And the way to do this in Python, the Pythonic way, which is another term of art in the community, is to say this. Deliberately induce an infinite loop while true, with capital T for true, and then do what you got to do, like get an int from a user, asking them for the height of this thing. And then if that is what you want, like a number greater than 0, go ahead and break out of the loop. So this is how, in Python, you could recreate the idea of a do-while loop. You deliberately induce an infinite loop, so something's going to happen at least once. Then, if you get the answer you want, you break out of it, effectively achieving the same logic. So this is the Pythonic way of doing a do-while loop. Let me go ahead and run Python of mario.py, type in 3 this time, and now I get back just the 3 hashes as well. What if, though, I wanted to get rid of how about ultimately that CS50 library function and also encapsulate this in a function? Well, let's go ahead and tweak this a little bit. Let me go ahead and remove this temporarily, give myself a main function so I don't make the same mistake as I did initially earlier. And let me give myself a function called getHeight that takes no arguments. And inside of that function is going to be that same code. But I don't want to break in this case. I want to return n. So recall that if you return from a function, you're done. You're going to exit from right that point. So this would be fine. You can just say return n inside of the loop. Or if you would prefer to break out, you could do something like this instead. Break. And then down here, you could return n as well. And let me make one point here before we go back up to main. This is a little different from C. And this one's subtle. What have I done here that in C would have been a bug, but is apparently not, I claim, in Python? It's super subtle, this one. Yeah? So similar. It's not quite that we're using it first. So it's OK not to declare a variable with like the data type. We've addressed that before. But on line 9, we're assigning n a value, it seems. And then we return n on line 12. But notice the indentation. In the world of C, if we had declared a variable inside of a loop on line 9, it would have been scoped to that loop, which means as soon as you get out of that loop, like further down in the program, n would not exist. It would be local to the curly braces therein. Here, logically, curly braces are gone, but the indentation makes clear that n is still inside of this loop between lines 8 through 11. But n is actually still in scope in Python. The moment you create a variable in Python, for better or for worse, it is available everywhere within that function, even outside of the loop in which you defined it. So this logic is actually OK in Python. In C, recall, to solve this same problem, we would have had to do something a little hackish like this, like define n up here on line 8 so that it exists now on line 10 and so that it exists on line 13. That is no longer an issue or need in Python. Once you create a variable, even if it's nested, nested, nested inside of some loops or conditionals, it still exists within the function itself. All right. Any questions then on this before we now run this and then get rid of the CS50 library again? OK, so let me go ahead and get the height from the user. Let's go ahead and create a variable in main called height. Let's call this getHeight function. And then let's use that height value instead of something hard-coded there. And let me see if this all works now. Python of Mario.py. Hopefully I haven't messed up, but I did. But this is an easy fix now. Yeah. I got to call main. So again, I deleted that earlier, but let me bring it back. So I'm actually calling main. Let me rerun Python of Mario.py. There we go. Height 3. Now it seems to be working. So let's do one last thing with Mario just to tie together that idea now of exceptions from before. Again, exceptions are a feature of Python whereby you can try to do something. And if there's a problem, you can handle it in any way you see fit. Previously, I handled it by just yelling at the user that that's not an int. But let's actually use this to re-implement CS50's own getInt function. Let me throw away CS50's getInt function. And now let me go ahead and replace getInt with input, but it's not sufficient to just use input. What do I have to add to this line of code on line 8? If I want to get back an int? Yeah, I have to cast it to an int by calling the int function around that value. Or I could do it on a separate line, just to be clear. I could also do n equals int of n. That would work too, but it's sort of an unnecessary extra line. This is not sufficient because that does not change the value. It creates the value, but then it throws it away. You need to assign it. So the conventional way to do this would probably be in one line just to keep things nice and tight. So that works fine now. If I run Python of Mario.py, I can still type in 3 and all is well. I can still type in -1 because that is an int that I am handling. What I'm not yet handling is weird input like cat or some string that is not a base 10 number. So here again is my traceback. And notice that here, let me scroll up a little bit. Here we can actually see more detail in the traceback. Notice that just like in C, or just like in the debugger in VS Code, you can see a few things. You can see mention of module. That just means your file. Main, which is my main function, and getHeight. So notice it's kind of backwards. It's top to bottom instead of bottom up as we drew it on the board the other day and as we envisioned stacks of trays in the cafeteria. But this is your stack of functions that have been called from top to bottom. GetHeight is the most recent. Main is the very first. Value error is the problem. So let's try to do this literally, except if there's an error. So what do I want to do? I'm going to go in here and I'm going to say try to do the following. Whoops. Try to do the following, except if there's a value error, then go ahead and say something like, well, like before, print that's not an integer, exclamation point. But the difference this time is because I'm in a loop, the user's going to have a chance to recover from this issue. So if I run Mario.py, 3 still works as before. If I run Mario.py and type in cat, I detect it now. And because I'm still in that loop, and because the program hasn't crashed, because I've caught, so to speak, the value error using this line of code here, that's the way in Python to detect these kinds of errors that would otherwise end up being on the user's own screen. If I type in cat, dog, that doesn't work. If I type in, though, 2, I get my 2 hashes, because that's indeed an int. All right, any questions on this? And we're not going to spend too much time on exceptions, but just wanted to show you what's involved with getting rid of those training wheels. Yeah? OK, so let's do this. That actually comes to the earlier question about printing the hashes on the same line, or maybe something like this, where we have little bricks in the sky or little question marks. Let's recreate this idea, because the problem with print, as was noted earlier, is you're automatically printing out new lines. But what if we don't want that? Well, let's change this program entirely. Let me throw away all the functions. Let's just go to a simpler world where we're just doing this. So let me start fresh in Mario.py. I'm not going to bother with exceptions or functions. Let's just do a very simple program to create this idea. For I in range of 4 this time, because there are 4 of these things in the sky. Let's go ahead and just print out a question mark to represent each of those bricks. Odds are, you know this is not going to end well, because these are, unfortunately, as you predicted, on separate lines. So it turns out that the print function actually takes in multiple arguments, not just the thing you want to print, but also some additional arguments that allow you to specify what the default line ending should be. But what's interesting about this is that if you want to change the line ending to be something like quote unquote, that is nothing, instead of \n, this is not sufficient, because in Python you can have 2 types of arguments or parameters. Some arguments are positional, which is the fancy way of saying it's a comma-separated list of arguments. And that's what we did all the time in C. Something, comma, something, comma, something. We did it in printf all the time and in other functions that took multiple arguments. In Python, you have not only positional arguments, where you just separate them by commas to give 1 or 2 or 3 or more arguments. There are also named arguments, which looks weird but is helpful for reasons like this. If you read the documentation, you will see that there is a named argument that Python accepts called end. And if you set that equal to something, that will be used as the end of every line instead of the default, which the documentation will also say is quote unquote \n. So this line here has no effect on my logic at the moment. But if I change it to just quote unquote, essentially overriding the default new line character and now run Mario again, now I get all 4 on the same line. There's a bit of a bug, though. My prompt is not meant to be on the same line. So I can fix that by just printing nothing. But really, it's not nothing, because you get the new line for free. So let me run Python of Mario.py again. And now we have what I intended in the first place, which was a little something that looked like this. And this is just one example of an argument that has a name. But this is a common paradigm in Python 2 to not just separate things by commas, but to be very specific, because the print function might take 5, 10, even 20 different arguments. And my God, if you had to enumerate like 10 or 20 commas, you're going to screw up. You're going to get things in the wrong order. Named arguments allow you to be resilient against that. So you only specify arguments by name, and it doesn't matter what order they are in. All right, any questions then on this and the overriding of new line? And to be clear, you can do something like very weird but logically expected like this by just changing the line ending too. But the right way to solve the Mario problem would be just to override it to be nothing like this. All right, how about this for cool? And this is why a lot of people like Python. Suppose you don't really like loops. You don't really like 3-line programs, because that was kind of 3 times longer than it needs to be. What if you just printed out a question mark 4 times? Python of Mario.py, that also works. So it turns out that just like the plus operator in Python can join things together, the multiply operator is not arithmetic in this case. It actually means take this and concatenate it 4 times over. So that's a way of just distilling into one line what would have otherwise taken multiple lines in C, fewer but still multiple lines in Python, but is really now rather succinct in Python by doing that instead. Let's do one last Mario example, which looked a little something like this. If this is another part of the Mario interface, this is like a grid of like 3 by 3 bricks, for instance. So 2 dimensions now, not just vertical, not horizontal, but now both. Let's print out something like that using hashes. Well, how do I do this? So how about for I in range of 3? Then I could do for j in range of 3, just because j comes after I, and that's reasonable for counting. I could now print out a hash symbol. Well, let's see what this does. Python of Mario.py. OK, that's just one crazy long column. What do I need to fix and where here to make this look like this? So 3 by 3 bricks instead of one long column. Any instincts? OK, so after printing 3, we want to skip a line. So maybe like print out a blank line here. OK, let's try that. I like that instinct, right? Print 3, new line. Print 3, new line. Let's go ahead and run Python of Mario.py. OK, it's more visible what I'm doing, but still wrong. What's the remaining fix, though? Yeah. Yeah, I'm getting an extra new line here, which I don't want while I'm on this row. So let me do end equals quote unquote. And now together, your solutions might take us the whole way there. Python of Mario.py. Voila, now we've got it in 2 dimensions. And even this, we can tighten up. Like, we could just use the little trick we learned. So we could just say print a hash times 3 times. And we can get rid of one of those loops altogether. All it's doing is automating that process. But no, I don't want to do that. How do I fix this here? Oh, I don't think I want this anymore, right? Because that's giving me an extra new line. So now this program is really tightened up. Same thing, 2 lines of code, but we're now implementing this same 2-dimensional structure here. All right, any questions here on these? Yeah? If print n, any spaces. Say that once more.
Whenever you write n, for example, the print function, in order to stop it from going to a new line, you didn't put any spaces in between it, like n equals and then 2 quotes. There were no spaces. Did you do that on purpose?
Oh, yes. Good question. I see what you're saying. So in a previous version, let me rewind in time. When we had this, I did not put spaces. The convention in Python is not to do that. Why? It just starts to add too much space. And this is a little inconsistent because earlier when we talked about like pluses or spaces around the less than or equal signs, I did say added. Here, it's actually clearer and recommended to keep them tighter together. Otherwise, it just becomes harder to read where the gaps are. Good observation. All right, let's do, how about another 5-minute break. Let's do that. And then we're going to dive into some more sophisticated problems and then ultimately build with some audio and visual examples as well. See you in 5. All right. So almost all of the examples we just did were recreations of what we did in week 1. And recall that week 1 was like our most syntax-heavy week. It was when we were first learning how to program in C. But after week 1, we began to focus a bit more on ideas like arrays and other higher-level constructs. And we'll do that again here, condensing some of those first early weeks into a fewer set of examples in Python. And we'll culminate by actually taking Python out for a spin and doing things that would be way harder to do and way more time-consuming to do in C, even more so than the speller example. But how do you go about figuring out like what functions exist? If you didn't hear it in class, you don't see it online, but you want to see it officially, you can go to the Python documentation, docs.python.org here. And I will disclaim that, honestly, the Python documentation is not terribly user-friendly. Google will often be your friend, so Googling something you're interested in to find your way to the appropriate page on python.org or stackoverflow.com is another popular website. As always, though, the line should be Googling things like, how do I convert a string to lowercase? Like, that's reasonable to Google. Or how to convert to uppercase. Or how implement function in Python. But Googling, of course, things like how to implement problem set 6 in CS50, of course, crosses the line. But moving forward, and really with programming in general, like Google and Stack Overflow are your friends, but the line is between the reasonable and the unreasonable. So let me officially use the Python documentation search, just to search for something like the lowercase function. Like, I know I can lowercase things in Python. I don't quite remember how. So let me just search for the word lower. You're going to get often an overwhelming number of results because Python's a pretty big language with lots of functionality. And you're going to want to look for familiar patterns. For whatever reason, string.lower, which is probably more popular or more commonly used than these other ones, is third on the list. But it's purple because I clicked it a moment ago when looking for it. So str.lower is probably what I want because I am interested at the moment in lowercasing strings. When I click on that, this is an example of what Python's documentation tends to look like. It's in this general format. Here's my str.lower function. This returns a copy of the string with all of the cased characters converted to lowercase and the lowercasing algorithm, ... So that doesn't give me much. It doesn't give me sample code, but it does say what the function does. And if we keep looking, you'll see mention of lstrip, which is left strip. I used its analog rstrip before. Right strip, which allows you to remove, that is, strip from the end of a string, something like white space, like a new line, or even something else. And if you scroll through string, this web page here, and we're halfway down the page already. If you see my scroll bar tiny on the right, there's a huge amount of functionality built into string objects here. And this is just testament to just how rich the language itself is. But it's also reason to assure that the goal when playing around with some new language and learning it is not to learn it exhaustively. Just like in English or any human language, there's always going to be vocab words you don't know, ways of presenting the same information in some language. That's going to be the case with Python. And what we'll do today and this week in problem set 6 is really get your footing with this language. But you won't know all of Python, just like you won't know all of C. And honestly, you won't know all of any of these languages on your own unless you're perhaps using them full-time professionally. And even then, there's more libraries than one might even retain themselves. So let's actually now pivot to a few other ideas that we'll implement in Python. In a moment, let me switch back over to VS Code here. And let me whip up, say, a recreation of our scores example from week 2, where we averaged like 3 scores together. And that was an opportunity in week 2 to play with arrays, to realize how constrained arrays are. They can't grow or shrink. You have to decide in advance. But let's see what's different here in Python. So let me do scores.py. And let me give myself an array in Python called scores. Sorry, let me give myself a variable in Python called scores. Set it equal to a list of 3 scores, which are the same ones we've used before, 72, 73, 33. In this context, meant to be scores, not ASCII values. And then let's just do the average of these. So average will be another variable. And it turns out I can do, well, how did I sum these before? I probably had a for loop to add 1. Then I knew how long there were. Turns out in Python, you can just say sum of scores divided by the length of scores. That's going to give me my average. So sum is a function that takes a list, in this case, as input, and it just does the sum for you with a for loop or whatever underneath the hood. Lang gives you the length of the list, how many things are in it, so I can dynamically figure that out. Now let me go ahead and print out, using print, the word average, and then in curly braces, the actual average, close quote. All right, so let's run this code, python of scores.py. And there's my average, in this case, 59.33333, and so forth, based on the math. Well, let's actually now change this a little bit and make it a little more interesting and actually get input from the user rather than hard coding this. Let me go back up here and use from CS50 import get int, because I don't want to deal with all the exceptions and the loops. Like, I just want to use someone else's function here. Let me give myself an empty list called scores. And this is not something we were able to do in C, right? Because in C, if you tried to make an empty array, well, that's pretty stupid because you can't add things to it. It's a fixed size. So it wouldn't even let you do that. But I can just create an empty list in Python, because lists, unlike arrays, are really linked lists. They'll grow and shrink. But you and I are not dealing with all the pointers underneath the hood. Python's doing that for us. So now let's go ahead and get a whole bunch of scores from the user. How about 3 of them in total? So for I in range of 3, let's go ahead and grab a score from the user using getInt, asking them for score. And then let's go ahead and append to the scores list that particular score. So it turns out that a list, and I could read the Python documentation to confirm as much, lists have a function built into them. And functions built into objects are generally known as methods, if you've heard that term before. Same idea, but whereas a function kind of stands on its own, a method is a function built into an object, like a list here. That's going to achieve the same result. Strictly speaking, I don't need the variable. Just like in C, I could tighten this up and do something like this as well. But I don't know. I kind of like it this way. It's more clear, to me at least, that what I'm doing here, getting the score and then appending it to the list. Now the rest of the code can stay the same. Python of scores.py, score will be 72, 73, 33, and I get back the math. But now the program's a little more dynamic, which is nice. But there's other syntax I could use here, just so you've seen it. Python does have some neat syntactic tricks whereby if you don't want to do scores.append, you can actually say scores plus equals this score. So you can actually concatenate lists together in Python too. Just as we used plus to join 2 strings together, you can use plus to join 2 lists together. The catch is you need to put the one score I'm adding here in a list of its own, which is kind of silly, but it's necessary so that this thing and this thing are both lists. To do this more verbosely, which most programmers wouldn't do, but just for clarity, this is the same thing as saying scores plus this score. So now maybe it's a little more clear that scores and bracket score, plural, sorry, singular, are both lists themselves, being concatenated or joined together. So 2 different ways. I'm not sure one is better than the other. This way is pretty common, but .append is also quite reasonable as well. All right. How about another example from week 2? This one was called uppercase. So let me do this in uppercase.py, though, this time. And let me import from CS50 getString again. And let me go ahead and say before will be my first variable. Let me get a string from the user asking them for a before string. And then let me go ahead and say after, just to demonstrate some changes, uppercasing to this string. Let me change my line ending to be that using our new trick. And this is where things get cool in Python, relatively speaking. If I want to iterate over all of the characters in a string and print them out in uppercase, one way to do that would be this. For C in the before string, go ahead and print out C.upper, but don't end the line yet because I want to keep these all on the same line until I'm all done. So what am I doing? Python of uppercase.py. Let me type in hello in all lowercase. I've just uppercased the whole string. How? I first get string, calling it before. I then just print out some fluffy text that says after colon, and I get rid of the line ending just so I can kind of line these up. Notice I hit the spacebar a couple times just so letters line up to be pretty. For C and before. This is new. This is powerful in in Python, whereby you don't have to do like int I equals 0 and I less than this. You could just say for C in the string in question, for C and before. And then here is just uppercasing that specific character and making sure we don't output a new line too soon. But this is actually more work than I need to do. Based on what we've seen thus far, like from our agreement example, can I tighten this up further? Can I collapse lines 5 and 6, maybe even 7 altogether? The goal of this program is just to uppercase the before string. How might I do this? Yeah, and back? Stir.upper, yeah. So I could do something like this. After gets before dot upper. So it's not stir literally dot upper. Stir just represents the string in question. So it would be before dot upper, but right idea otherwise. And so let me go ahead and just tweak my print statement a little bit. Let me just go ahead and print out the after variable here after creating it. So this line is the same. I'm getting a string called before. I'm creating another variable called after. And as you propose, I'm calling upper on the whole string, not one character at a time. Why? Because it's allowed. And again, in Python, there aren't technically characters individually. There's only strings anyway, so I might as well do them all at once. So if I rerun the code now, Python of uppercase.py, now I'll type in hello in all lowercase. And oh, so close. I think I can get rid of this override because I'm printing the whole thing out at once, not character by character. So now if I type in hello before, now I have an even tighter version of the program here. All right, any questions then on lists or on strings and what this kind of function upper represents with its docs? No? All right, so a couple other building blocks before we start. Oh, where was that? Then to the right. The right, right. Yes, thank you. Yes, do I have to create this variable upper? No, I don't. I could actually tighten this up. And if you really want to see something neat, inside of the curly braces, you don't have to just put the names of variables. You can put a small amount of logic, so long as it doesn't start to look stupid and kind of overwhelmingly complex, such that it's sort of bad design at that point. I can tighten this up like this and now run Python of uppercase.py, writing hello again, and that too worked. But I would be careful about this. You want to resist the temptation of having like a long line of code that's inside the curly braces, because it's just going to be harder to read. But absolutely, you could indeed do that too. All right, how about command line arguments, which was one thing we introduced in week 2 also, so that we could actually have the ability to take input from the user. So we could actually take input from the user at the command line so as to take literally command line arguments. These are a little different, but it follows the same paradigm. There's no main by default, and there's no def main int argc char, or we called it string argv by default. There's none of this. So if you want access to the argument vector, argv, you import it. And it turns out there's another module in Python, or library in Python, called sys. And you can import from the system this thing called argv. So same idea, different place. Now I'm going to go ahead and do this. Let's write a program that just requires that the user types in a word after the program's name or none at all. So if the length of argv equals 2, let's go ahead and print out, how about hello, comma, argv bracket 1, close quote. Else, if they don't type 2 words total at the prompt, let's just say the default, like we did weeks ago, hello world. So the only thing that's new here is we're importing argv from sys, and we're using this fancy f-string format, which kind of, to your point too, it's putting more complex logic in the curly braces, but that's OK. In this case, it's a list called argv, and we're getting bracket 1 from it. Let's do Python of argv.py, enter, hello world. What if I do argv.py David at the command line? Now I get hello David. So there's one curiosity here. Python is not included in argv, whereas in C, /whatever was the first thing. The analog in Python is that the name of your Python program is the first thing. In bracket 0, which is why David is in bracket 1, the word Python does not appear in the argv list, just to be clear. But otherwise, the idea of these arguments is exactly the same as before. And in fact, what you can do, which is kind of cool, is because argv is a list, you can do things like this. For arg in argv, go ahead and print out each argument. So instead of using a for loop and I and all of this, if I do Python of argv enter, it just writes the program's name. If I do Python of argv foo, it puts argv.py and foo. If I do foo and bar, those words all print out. If I do foo bar baz, those print out too. And foo and bar or baz are like a mathematician's x and y and z for a computer scientist when you just need some placeholder words. So this is just nice. It reads a little more like English, and a for loop is just much more concise. Allows you to iterate very quickly when you want something like that. Suppose I only wanted the real words that the human typed after the program's name. Like suppose I want to ignore argv.py. I mean, I could do something hackish like this. If arg equals argv.py, I could just ignore, let's invert the logic. I could do this, for instance. So if the arg does not equal the program name, then go ahead and print out the word. So I get foo, bar, and baz only. Or, this is what's kind of neat about Python too. Let me undo that. And let me just take a slice of the array of the list instead. So it turns out if argv is a list, I can actually say, you know what, go into that list, start at element 1 instead of 0, and then go all the way to the end. And we have not seen the syntax in C, but this is a way of slicing a list in Python. So now watch what happens. If I run Python of argv.py, foo, bar, baz, enter, I get only a subset of the list starting at position 1, going all the way to the end. And you can even do kind of the opposite. If for whatever reason you want to ignore the last element, you can say colon, we could say colon -1 and use a negative number, which we've not seen before, which slices off the end of the list as well. So there's some syntactic tricks that tend to be powerful in Python too, even if at first glance you might not need them for typical things. All right, let's do one other example with exit, and then we'll start actually applying some algorithms to make things interesting. So in one last program here, let's do exit.py just to do one more mechanic before we introduce some algorithms. And let's do this. Let's import from sys import argv. Let's now do this. Let's make sure the user gives me one command line argument. So if the length of argv does not equal 2 in total, then let's go ahead and print out something like missing command line argument, just to explain what the problem is. And then let's do this. We can exit. But I'm going to use a better version of exit here. Let me import 2 functions from sys. Turns out the better way to do this is with sys.exit, because I can then exit specifically 2 with this exit code. Otherwise, down here, I'm going to go ahead and print out something like hello, comma, argv bracket 1, same as before, and then I'm going to exit with 0. So again, this was a subtle thing we introduced in week 2, where you could actually have your programs exit with some number where 0 signifies success and anything else signifies error. This is just the same idea in Python. So if I, for instance, just run the program like this, oops, I screwed up. I meant to say exit here and exit here. Let me do that again. If I run this like this, I'm missing a command line argument. So let me rerun it with like my name at the prompt. So I have exactly 2 command line arguments, the file name and my name, hello, comma, David. And if I do David Malin, it's not going to work either, because now argv does not equal 2. But the difference here is that we're exiting with 1, so that special programs can detect an error, or 0, in the event of success. And now there's one other way to do this too. Suppose that you're importing a lot of functions and you don't really want to make a mess of things and just have all of these function names available without it being clear where they came from. Let's just import all of sys. And let's just change our syntax, kind of like I proposed for CS50, where we just prepend to all of these library functions sys, just to be super explicit where they came from. And if there's another exit or argv value that we want to import from a library, this is one way to avoid collision. So if I do it one last time here, missing command line argument, but David still actually worked. All right, only to demonstrate how we can implement that same idea. Let's now do something more powerful like a search algorithm like binary search. I'm going to go ahead and open up a file called numbers.py, and let's just do some searching, or linear search, rather, on a list of numbers. Let's go ahead and do this. How about import sys as before? Let me give myself a list of numbers like 4, 6, 8, 2, 7, 5, 0. So just a bunch of integers. And then let's do this. If you recall from week 3, we searched for the number 0 at the end of the lockers on stage. So let's just ask that question in Python. No need for a loop or anything like that. If 0 is in the numbers, go ahead and print out found. And then let's just exit successfully with 0. Else, if we get down here, let's just say print not found. And then we'll sys exit with 1. So this is where Python starts to get powerful again. Here's your list. Here is your loop that's doing all of the checking for you. Underneath the hood, Python's going to use linear search. You don't have to implement it yourself. No while loop, no for loop. You just ask a question. If 0 is in numbers, then do the following. So that's one feature we now get with Python and get to throw away a lot of that code. We can do it with strings too. Let me open a file called names.py instead and do something that was even more involved in C because we needed strcomp and the for loop and so forth. Let me import sys for this file. Let's give myself a bunch of names like we did in C. And those were Bill and Charlie and Fred and George and Ginny and 2 more, Percy. And lastly, Ron. And recall at the time we looked for Ron, and so we had to iterate through the whole thing, doing strcomp and I++ and all of that. Now just ask the question. If Ron is in names, then let's go ahead and, whoops, let me hide that. I hit the command too soon. Let me go ahead and say print found as before, sys exit 1 just to indicate success. And then down here, if we get to this point, we can say not found. And then we'll just sys exit 1 instead. So again, this just does linear search for us by default. Python of names.py, we found Ron, because indeed he's there and at the end of the list, but we don't need to deal with all of the mechanics of it. All right, let's take things one step further. In week 3, we also implemented the idea of a phone book that actually associated keys with values. But remember, the phone book in C was kind of a hack, right? Because we first had 2 arrays, one with names, one with numbers. Then we introduced structs, and so we gave you a person structure. And then we had an array of persons. You can do this in Python using objects and things called classes, but we can also just use a general purpose dictionary, because just like in pset5, you can associate keys with values using a hash table, using a trie. Well, similarly, can Python just do this for us? From CS50, let's import getString. And now let's give myself a dictionary of people. DICT, open paren, close paren, gives you a dictionary. Or you can simplify the syntax, actually. And a dictionary, again, is just keys and values, words and definitions. You can also just use curly braces instead. That gives me an empty dictionary. But if I know what I want to put in it by default, let's put Carter in there with a number of +1, 617, 495, 1000, just like last time. And put myself, David, with +1, 949, 468. 2750. And it came to my attention tragically after class that day that we had a bug in our little Easter egg. If today you would like to call me or text me at that number, we have fixed the code that underlies that little Easter egg. Spoiler ahead. All right, so this now gives me a variable called people that's associating keys with values. There is some new syntax here in Python. Not just the curly braces, but the colons and the quotes on the left and the right. This is a way in Python of associating keys with values, words with definitions, anything with anything else. And it's going to be a super common paradigm, including in week 7, when we look at CSS and HTML and web programming. Keys and values are like this omnipresent idea in computer science and programming, because it's just a really useful way of associating one thing with another. So at this point in the story, we have a dictionary, a hash table, if you will, of people, associating names with phone numbers, just like a real-world phone book. Let's write a program that gets a string from the user and asks them whose number they would like to look up. Then let's go ahead and say, if that name is in the people dictionary, go ahead and print out that person's number by going into the people dictionary and going to that specific name within there, using an F string for the whole thing. So this is similar to, in spirit to before. Linear search and dictionary lookups will just happen automatically for you in Python by just asking the question, if name and people. And this line's just going to print out whoever is in the people dictionary at that name. So I'm using square brackets because here's the interesting thing in Python. Just like you can index into an array or a list in Python using numbers, 0, 1, 2, you can very conveniently index into a dictionary in Python using square brackets as well. And just to make clear what's going on here, let me go and create a temporary variable, person equals people bracket name. And then let's say number equals people bracket name. And let's just print out the number in question. In C and previously in Python, anything with square brackets like this would have been go to a location in a list or an array using a number. But that can actually be a string, like a word the human has typed. And this is what's amazing about dictionaries. It's not like a big line of a big linear thing. It's this table that you can look up in one column the name and get back in the other column the number. So let's go ahead and run Python of phonebook.py. Found, not that, oh wait, that's not what's supposed to happen at all. I think I'm in the wrong play. Phonebook.py. What's going on? Print found. I am confused. OK. Let's run this again. Python of phonebook.py. What the? OK, stand by. What the hell? What am I not understanding here? OK, Rongshin, Carter, do you see what I'm doing wrong? What the? Say again? Oh, what? Yeah. Found. OK, we're going to do this. One sec. Whoa. OK. All this is coming out of the video. Thanks. All right. I will try to figure out what was going wrong. The best I can tell, it was running the wrong program. I don't quite understand why, so we will diagnose this later. I just put the file into a temporary directory for now to run it. So let me go ahead and just run this, Python of phonebook.py. Type in, for instance, my name, and there's my corresponding number. I have no idea what was just happening, but I will get to the bottom of it and update you if we can put our finger on it. So this was just an example now of implementing a phone book. Let's now consider what we can do that's a little more powerful in these examples, like a phone book that actually keeps this information around. Thus far, these simple phone book examples throw the information away, but using CSV files, comma-separated values, maybe we could actually keep around the names and numbers so that, like on your phone, you can actually keep your contacts around long term. So I'm going to go ahead now and do a slightly different example. And let me just hide this detail so it's not confusing. Whoops. I'm going to change my prompt temporarily. So let me go ahead now and refine this example as follows. I'm going to go into phonebook.py, and I'm going to import a whole library called CSV. And this is a powerful one because Python comes with a library that just handles CSV files for you. A CSV file is just a file with comma separated values. And in fact, to demonstrate this, let me check on one thing here just to make this a little more real. To demonstrate this, let's go ahead and do this. Let me import the CSV library. From CS50, let me import getString. Let me then open a file using the open function. Open a file called phonebook.csv in append format, in contrast with read format and write format. Write just blows it away. If it exists, append adds to the bottom of it. So I keep this phone book around, just like you might keep adding contacts to your phone. Now let me go ahead and get a couple values from the user. Let me say getString and ask the user for a name. Then let me get string again and ask the user for their number. And now let me go ahead and do this. And this is new, and this is Python specific, and you would only know this by following a tutorial or reading the documentation. Let me give myself a variable called writer and ask the CSV library for a writer to that file. Then let me go ahead and use that writer variable, use a function or a method inside of it called writeRow to write out a list containing that person's name and number. Notice the square brackets inside the parentheses because I'm just printing a list to that particular row in the file. And then I'm just going to close the file. So what is the effect of all of this? Well, let me go ahead and run this version of phonebook.py, and I'm prompted for a name. Let's do Carter's first. +1 617 495 1000. And then let's go ahead and ls. Notice in my current directory, there's two files now, phonebook.py, which I wrote, and apparently phonebook.csv. CSV just stands for comma separated values, and it's like a very simple way of storing data in a spreadsheet, if you will, where the comma represents the separation between your columns. There's only two columns here, name and number. But because I'm writing to this file in append mode, let me run it one more time. Python of phonebook.py. And let me go ahead and do David and +1 949 468 2750, enter. And notice what happened in the CSV file. It automatically updated because I'm now persisting this data to the file in question. So if I wanted to now read this file in, I could actually go ahead and do linear search on the data using a read function to actually read from the CSV. But for now, we'll just leave it a little simply as write. And let me make one refinement here. It turns out that if you're in the habit of opening a file, you don't have to even close it explicitly. You can instead do this. You can instead say, with the opening of a file called phonebook.csv in append mode, calling the thing file, go ahead and do all of these lines here. So the with keyword is a new thing in Python, and it's used in a few different ways. But one of the ways it's used is to tighten up code here. And I'm going to move my variables to the outside because they don't need to be inside of the with statement where the file is open. This just has the effect of ensuring that you, the programmer, don't screw up and accidentally don't close your file. In fact, you might recall from C, Valgrind might have complained at you if you had a file that you didn't close a file. You might have had a memory leak as a result. The with keyword takes care of all of that for you as well. How about, do we want to do this? How about, let's do one other thing. Let's do this. Let me go ahead and propose that on your phone or laptop here or online, go to this URL here, where you'll find a Google form. And just to show that these CSVs are actually kind of omnipresent. And if you've ever used a Google form or managed a student group or something where you've collected data via Google Forms, you can actually export all of that data via CSV files. So go ahead to this URL here. And those of you watching on demand later will find that the form is no longer working since we're only doing this live. But that will lead to a Google form that's going to let everyone input their answer to a question like, what house do you want to end up into? Sort of an approximation of the sorting hat in Harry Potter. And via this form, will we then have the ability to export, we'll see, a CSV file. So let's give you a moment to do that. In just a moment, I'll share my version of the screen, which is going to let me actually open the file, the form itself. And in just a moment, I'll switch over. OK, so this is now my version of the form here, where we have 200 plus responses to a simple question of the form, what house do you belong in? Gryffindor, Hufflepuff, Ravenclaw, or Slytherin? If I go over to responses, I'll see all of the responses in the GUI form here. So graphical user interface. And we could flip through this, and it looks like, interestingly, 40% of Harvard students want to be in Gryffindor. 22% in Slytherin, and everyone else in between the others. But you might have noticed, if ever using a Google form, this Google Spreadsheets link. So I'm going to go ahead and click that, and that's going to automatically open, in this case, Google Spreadsheets. But you can do the same thing with Office 365 as well. And now you see the raw data as a spreadsheet. But in Google Spreadsheets, if I go to File and then I go to Download, notice I can download this as an Excel file, a PDF, and also a CSV, comma separated values. So let me go ahead and do that. That gives me a file in my Downloads folder on my computer. I'm going to now go back to my code editor here. And what I'm going to go ahead and do is upload this file from my Downloads folder to VS Code so that we can actually see it within here. And now you can see this open file. And I'm going to shorten its name just so it's a little easier to read. I'm going to rename this using the mv command to just hogwarts.csv. And then we can see in the file that there's two columns, timestamp column house, where you have a whole bunch of timestamps when people filled out the form, someone very early in class, and then everyone else just a moment ago. And the second value after each comma is the name of the house. Well, let me go ahead here and implement a program in a file called hogwarts.py that processes this data. So in hogwarts.py, let's just write a program that now reads a CSV, in this case not a phone book, but everyone's sorting hat information. And I'm going to go ahead and import CSV. And suppose I want to answer a reasonable question, ignoring the fact that Google's GUI, or graphical user interface, can do this for me. I just want to count up who's going to be in which house. So let me give myself a dictionary called houses that's initially empty with curly braces. And let me pre-create a few keys. Let me say Indoor is going to be initialized to 0. Hufflepuff will be initialized to 0 as well. Ravenclaw will be initialized to 0. And finally, Slytherin will be initialized to 0. So here's another example of a dictionary or a hash table just being a very general purpose piece of data. You can have keys and values. The keys in this case are the houses. The values are initially 0, but I'm going to use this instead of like 4 separate variables to keep track of everyone's answer to this form. So I'm going to do this with opening hogwarts.csv in read mode, not append. I don't want to change it. I just want to read it. As file, as my variable name. Let's go ahead and create a reader this time that is using the reader function in the CSV library by opening that file. I'm going to go ahead and ignore the first line of the file, because recall that the first line is just timestamp and house. I want to get the real data. So this next function is just a little trick for ignoring the first line of the file. Then let's do this. For every other row in the reader, that is line by line, get the current person's house, which is in row bracket 1. This is what the CSV reader library is doing for us. It's handling all of the reading of this file. It figures out where the comma is. And for every row in the file, it hands you back a list of size 2. In bracket 0 is the timestamp. In bracket 1 is the house name. So in my code, I can say house equals row bracket 1. I don't care about the timestamp for this program. And then let's go into my dictionary called houses, plural, index into it at the house location by its name, and increment that 0 to 1. And now, at the end of this block of code, that has the effect of iterating over every line of the file, updating my dictionary in 4 different places based on whether someone typed Gryffindor or Slytherin or anything else. And notice that I'm using the name of the house to index into my dictionary to essentially go up to this little cheat sheet and change the 0 to a 1, the 1 to a 2, the 2 to a 3, instead of having like 4 separate variables, which would just be much more annoying to maintain. Down at the bottom, let's just print out the results. For each house in those houses, iterating over the keys they're in by default in Python, let's go ahead and print out an f string that says the current house has the current count, and count will be the result of indexing into houses for that given house. And let me close my quote. So let's run this to summarize the data. Hogwarts.py 140 of you answered Gryffindor, 54 Hufflepuff, 72 Ravenclaw, and 80 of you Slytherin. And that's just my now way of code. And this is, oh my God, so much easier than C to actually analyze data in this way. And one of the reasons that Python's so popular for data science and analytics more generally is that it's actually really easy to manipulate data and run analytics like this. And let me clean this up slightly. It's a little annoying that I just have to know and trust that the house name is in bracket 1 and timestamp is in bracket 0. Let's clean this up. There's something called a dictionary reader in the CSV library that I can use instead. Capital D, capital R. This means I can throw away this next thing, because what a dictionary reader does is it still returns to me every row from the file, one after the other, but it doesn't just give me a list of size 2 representing each row. It gives me a dictionary. And it uses as the keys in that dictionary timestamp and house for every row in the file, which is just to say it makes my code a little more readable, because instead of doing this little trickery, bracket 1, I can say, quote unquote, bracket house with a capital H because it's capitalized in the Google form itself. So the code now is just minorly different, but it's way more resilient, especially if I'm using Google Spreadsheets and I'm moving the columns around or doing something like that where the numbers might get messed up. Now I can run this on Hogwarts.py again, and I get the same answers, but I now don't have to worry about where those individual columns are. All right. Any questions on those capabilities there? That's a teaser of sorts for what some of the manipulation we'll do in PSET 6. All right, so some final examples and flair to intrigue with what you can do with Python. I'm going to actually switch over to a terminal window on my own Mac so that I can actually use audio a little more effectively. So here's just a terminal window on Mac OS. I, before class, have pre-installed some additional Python libraries that won't really work in VS Code in the cloud because they require audio that the browser won't necessarily support. But I'm going to go ahead and write an example here that involves writing a speech-based program that actually does something with speech. And I'm going to go ahead and import a library that, again, I pre-installed called Python text-to-speech. And I'm going to go ahead and, per its documentation, give myself a speech engine by using that library's init function for initialize. I'm then going to use this engine's say function to do something fun like hello world. And then I'm going to go ahead and tell this engine to run and wait while it says those words. All right, I'm going to save this file. I'm not using VS Code at the moment. I'm using another popular program that we used in CS50 back in my day called Vim, which is a command line program that's just in this black and white window. Let me go ahead now and run Python of speech.py and
hello world.
All right, so it's a little computerized, but it is speech that has been synthesized from this example. Let's change it a little bit to be more interesting. Let's do something like this. Let's ask the user for their name, like what's your name, question mark. And then let's use a little f string and say not hello world, but hello to that person's name. Let me save my file, run Python of speech.py, enter. David.
Hello, David.
All right, so we pronounce my name OK. Might struggle with different names depending on the phonetics, but that one seemed to be OK. Let's do something else with Python using similarly just a few lines of code. Let me go into today's examples. And I'm going to go into a folder called a folder called faces.py. Faces. And in this folder that I've written in advance are a few files. detect.py, recognize.py, and two photos, office.jpg and toby.jpg, if you're familiar with the show. Here, for instance, is the cast photo from the office here. So here's a photo as input. Suppose I want to do something very Facebook style where I want to analyze all of the faces or detect all of the faces in there. Well, let me go ahead and show you a program I wrote in advance. That's not terribly long. Much of it is actually comments, but let's see what I'm doing. I'm importing the pillow library, again, to get access to images. I'm importing a library called face recognition, which I downloaded and installed in advance, but it does what it says. According to its documentation, you go into that library and you call a function called load image file to load something like office.jpg. And then you can use a line of code like this. Call a function called face locations, passing the images input, and you get back a list of all of the faces in the image. And then down here, a for loop that iterates over all of those face locations. And inside of this loop, I just do a bit of trickery. I figure out the top, right, bottom, and left corners of those locations. And then using these lines of code here, I'm using that image library to just draw a box, essentially. And the code looks cryptic. Honestly, I would have to look this up to write it again. But per the documentation, this just draws a nice little box around the image. So let me go ahead and zoom out here and run this now on office.jpg. All right. It's analyzing, and you can see in the sidebar here, here's the original, and here is every face that my, 10 lines of Python code found within that file. What's a face? Presumably the library is looking for something maybe without a mask that has 2 eyes, a nose, and a mouth in some kind of arrangement, some kind of pattern. So it would seem pretty reliable, at least on these fairly easy to read faces here. But what if we want to look for someone specific, for instance, someone that's always getting picked on? Well, we could do something like this. Recognize.py, which is taking 2 files as input. That image and the image of one person in particular. And if you're trying to find Toby in a crowd, here I conflated the program. Sorry, this is the version that draws a box around the given face. Here we have Toby as identified. Why? Because that program, recognize.py, has a few more lines of code. But long story short, it additionally loads as input Toby.jpg in order to recognize that specific face. And that specific face is a completely different photo, but it looks similar enough to the person that it all worked out OK. Let's do one other that's a little sensitive to microphones. Let me go into, how about my listen folder here, which is available online too. And let's just run Python of listen0.py. I'm going to type in like David. Oh, sorry. No, I'm going to hello world. Oh, no, that's the wrong version. OK, I look like an idiot. OK, hello. There we go. Hello to you too. And if I say goodbye, I'm talking to my laptop like an idiot. OK. Now it's detecting what I'm saying here. So this first version of the program is just using some relatively simple if, elif, and it's just asking for input, forcing it to lowercase, and that was my mistake with the first example. And then I'm just checking, is hello in the user's words? Is how are you in the user's words? Didn't see that, but it's there. Is goodbye in the user's words? Now let's do a cooler version using a library, just by looking at the effect. Python of listen1.py. Hello world. Let's do version 2 of this that uses a speech-to-text library. Hello world. OK, so now it's artificial intelligence. Now let's do something a little more interesting, the third version of this program that actually analyzes the words that are said. Hello world. My name is David. How are you? OK, so that time it not only analyzed what I said, but it plucked my name out of it. Let's do 2 final examples. This one will generate a QR code. Let me go ahead and write a program called qr.py that very simply does this. Let me import a library called OS. Let me import a library called QR code. Let me grab an image here that's qrcode.make. And let me give you like the URL of like a lecture video on YouTube or something like that. With this ID, let me just type this so I don't get it wrong. OK, so if I now use this URL here of a video on YouTube, making sure I haven't made any typos, I'm now going to go ahead and do 2 lines of code in Python. I'm going to first save that as a file called qr.png, which is a 2-dimensional barcode, a QR code. And indeed, I'm going to use this format. And I'm going to use the os.system library to open qr.png automatically. And if you'd like to take out your phone at this point, you can see the result of my barcode that's just been dynamically generated. Hopefully from afar that will scan. And I think that's an appropriate line to end on. So that's it for CS50. We will see you next time. This is CS50, and this is week 7, the week here of Halloween. Indeed, special thanks to CS50's own Valerie and her mom for having created this very festive scenery, and all past ones as well. Today, we pick up where we left off last time, which, recall, we introduced Python. And that was our big transition from C, where suddenly things started to look new again, probably, syntactically, but also probably things hopefully started to feel easier. Well, with that said, like problem set 6 certainly added some challenges and you did some new things, but hopefully you've begun to appreciate that with Python, just a lot more stuff is easier to do. You get more out of the box with the language itself, and that's going to be so useful over the coming weeks as we transition further to introducing something called databases today, web programming next week and the week after, so that by term's end, and perhaps even for your final project, you really are building something from scratch using all of these various tools somehow together. So before we do that, though, today, let's consider what we weren't really able to do last week, which was actually create and store data ourselves. Right? In Python, we've played around with the CSV, comma, separated values library. And you've been able to read in CSVs from disk, so to speak, that is, from files in your programming environment. But we haven't necessarily started saving data, persisting data ourselves. And that's a huge limitation because pretty much all of the examples we've done thus far, with a couple of exceptions, have involved my providing input at the keyboard or even vocally, but then nothing happens to it. It disappears the moment the program quits because it was only being stored in memory. But today, we'll start to focus all the more on storing things on disk, that is, storing things in files and folders so that you can actually write programs that remember what it is the human did last time, and ultimately you can actually make mobile or web apps that actually begin to grow and grow and grow their data sets, as might happen if you get more and more users, for instance, on a website. To play then with this new capability of being able to write files, let's go ahead and just collect some data. In fact, those of you here in person, if you want to pull up this URL on your phone or laptop, that's going to lead you to a Google form. And that Google form is going to ask you in just a moment for really just your favorite TV show. And it's going to ask you to categorize it according to its genre, like comedy or drama or action or musical or something like that. And this is useful because if you've ever used a Google form before, or Microsoft's equivalent with Office 365, it's a really useful mechanism of just collecting data from users and then ultimately putting it into a spreadsheet form. So this is a screenshot of the form that those of you here in person or tuning in on Zoom are currently filling out. It's asking only 2 questions. What's the title of your favorite TV show? And what are one or more genres into which your TV show falls? And I'll go ahead and pivot now to the view that I'll be able to see as the person who created this form, which is quite simply a Google spreadsheet. Google Forms has this nice feature, if you've ever noticed, that allows you to export your data to a Google spreadsheet. And then from there, we can actually grab the file and download it to my own Mac or your own PC so that we can actually play around with the data that's come in. So in fact, let me go ahead and slide over to the live Google spreadsheet. And you'll see probably a whole bunch of familiar TV shows here, all coming in. And if we keep scrolling and scrolling and scrolling, only 46, 47, there we go, up to 50 plus already. If you need that URL again here, if you're just tuning in, you can go to this URL here. And in just a moment, we'll have a bunch of data with which we can start to experiment. I'll give you a moment or so there. All right. Let me hang in there a little longer. OK, we've got over 100 submissions. Good. Good. Even more coming in now. And we can see them coming in live here. Let me switch back to the spreadsheet. The list is growing and growing and growing. And in just a moment, let me give Carter a moment to help me export it in real time. Carter, just give me a heads up when it's reasonable for me to download this file. All right, and I'll begin to do this very slowly. So I'm going to go up to the File menu. If you've never done this before, download. You can download a whole bunch of formats, one in Excel. But more simply, and the one we'll start to play with here, is comma-separated values. So CSV files, we used this past week. Why are they useful? Now that you've played with them or used them in past real world, like what's the utility of a CSV file versus something like Excel, for instance? Why CSV in the first place? Any instincts? Yeah. OK, so storage is compelling. A simple text file with ASCII or Unicode text is probably pretty small. I like that. Other thoughts? Yeah, well said. It's just a simple text format, but using conventions like commas, you can represent the idea of columns. Using new lines, \n's, invisibly at the end of your lines, you can create the idea of rows. So it's a very simple way of implementing what we might call a flat file database. It's a way of storing data in a flat, that is very simple file that's just pure ASCII or Unicode text. And more compellingly, I dare say, is that with a CSV file, it's completely portable. Something's portable in the world of computing if it means you can use it on a Mac or a PC running this operating system or this other one. And portability is nice because if I were to download an Excel file, there'd be a whole bunch of people in this room and online who couldn't download it because they haven't bought Microsoft Excel or installed it. Or if they have a Mac, they might not, or if it's a .numbers file in the Mac world, a PC user might not be able to download it. So a CSV is indeed very portable. So I'm going to go ahead and download, quite simply, the CSV version of this file. That's going to put it onto my own Mac's downloads folder. And let me go ahead here, and in just a moment, let me just simplify the name because it actually downloads it at a pretty large name. And give me just one moment here. And you'll see that indeed on my Mac, I have a file called favorites.csv. I shortened the name real quick. And now what I'm going to do is go over to VS Code. And in VS Code, I'm going to open my File Explorer. And if I minimize my window here for a moment, a handy feature of VS Code is that you can just drag and drop a file, for instance, into your Explorer. And voila, it's going to automatically upload it for you. So let me go ahead and full screen here, close my Explorer, temporarily close my terminal window. And you'll see here a CSV file, favorites.csv, and the first row, by convention, has whatever the columns were in Google Spreadsheets or Office 365, in Excel Online, timestamp, comma, title, comma, genres. Then we have timestamps, which indicates when people started submitting. Looks like a couple of people were super eager to get started an hour or two ago. And then you have the title next, after a comma. But there's kind of a curiosity after that. Sometimes I see the genre like comedy, 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 but sometimes it's like crime, comma, drama, or action, comma, crime, comma, drama. And those things are quoted. And yet I didn't do any quotes. You probably didn't type any quotes. Where are those quotes coming from in this CSV file? Why are they there if we infer? Yeah. Yeah, so you have a kind of a corner case, if you will, because if you're using commas, as you described, to separate your data into what are effectively columns, well, you've kind of painted yourself into a corner if your actual data has commas in it itself. So what Google has done, what Microsoft does, what Apple does, is they quote any strings of text that themselves have commas, so that these are now sort of English grammatical commas, not CSV-specific commas. So it's a way of escaping your data, if you will, and escaping just means to call out a symbol in a special way so it's not misinterpreted as something else. All right, so this is all to say that we now have all of this data with which we can play in the form of what we'll start calling a flat file database. So suppose I wanted to now start manipulating this data, and I want to store it ultimately indeed in this CSV format. How can I actually start to read this data, maybe clean it up, maybe do some analytics on it, and actually figure out what's the most popular show among those who submitted here over the past few minutes? Well, let me go ahead and close this. Let me go ahead then and open up, for instance, just my terminal window. And let's code up a file called favorites.py. And let's go ahead and iteratively start simple by just opening up this file and printing out what's inside of it. So you might recall that we can do this by doing something like import CSV to give myself some CSV reading functionality. Then I can go ahead and do something like with open, the name of the file that I want to open, in read mode, quote unquote, R means to read it, and then I can say as file or whatever other name for a variable to say that I want to open this file and essentially store some kind of reference to it in that variable called file. Then I can give myself a reader, and I can say csv.reader, passing in that file as input. And this is the magic of that library. It deals with the process of opening it, reading it, and giving you back something that you can just iterate over, like with a for loop. I do want to skip the first row. And recall that I can do this. Next reader is this little trick that just says ignore the first row, because the first one's special. It said timestamp, title, genres. That's not your data. That was mine. But this means now that I've skipped that first row, everything hereafter is going to be the title of a show that you all like. So let me do this. For row in the reader, let's go ahead and print out the title of the show each of you typed in. How do I get at the title of the show each of you typed in? It's somewhere inside of row. Row, recall, is a list. So what do I want to type next in order to get at the title of the current row? Just as a quick check here. What do I want to type to get at the title of the row? Keeping in mind, again, that it was timestamp, title, genres. Yeah. So row bracket 1 would give me the second column, 0 index. That is the one in the middle with the title. So this program isn't that interesting yet, but it's a quick and dirty way to figure out, all right, what's my data look like? Let me actually just do a little bit of a check here and see if it contains the data I think it does. Let me maximize my terminal window here. Let me run Python of favorites.py, hitting enter. And you'll see now a purely textual list of all of the shows you all seem to like here. But what's noteworthy about it? Specific shows aside, judgment aside as to people's TV tastes, like what's interesting or noteworthy about the data that might create some problems for us if we start to analyze this data and figure out what's the most popular, how many people like this or that? What do you think? Yeah? Yeah, there might be user errors or just sort of stylistic differences that give the appearance that one show is different from the other. For instance, here, let's see if I can see an example on the screen here. Yeah, so Friends here is in all lowercase. Friends here is capitalized. No big deal. We can sort of mitigate that. But this is just a tiny example of where data in the real world can get messy fast. And that probably wasn't even a typo. It was just sort of just someone not caring as much to capitalize it. And that's fine. Your users are going to type what they're going to type. So let's see if we can't now begin to get at more specific data and maybe even clean some of this data up. Let me go back into my file called favorites.py here. And let's actually do something a little more user-friendly for me. Instead of a reader, recall that there was this dictionary reader that's just a little more user-friendly. And it means I can type in dictionary reader here, passing in the same file. But now when I iterate over this reader variable, what is each row? When using a dict reader instead of a reader, recall, and this is just a peculiarity of the CSV library, this gives me back not a list of cells, but what instead, which is marginally more user-friendly for me. Yeah? Yeah, I can now use open bracket, quotes, and the title, because what's coming back now is a dict object. That is a dictionary which has keys and values, the keys of which are the column headings, the values of which are the data I actually care about. So this is just marginally better because, one, it's just way more obvious to me, the author of this code, what it is I'm getting at. I mean, I don't remember what column the title was. Was it 0? Was it 1? Was it 2? That's something you're going to forget over time. And God forbid someone changes the data by just dragging and dropping the columns in Excel or Apple Numbers or Google Spreadsheets. That's going to break all of your numeric indices. And so a dictionary reader is arguably just better designed because it's more robust against changes and potential errors like that. Now, the effect of this change isn't going to be really any different. If I run Python of favorites.py, voila, I get all of the same results. But I've now not made any assumptions as to where each of the columns actually is numerically. All right, well, let's go ahead and now filter out some duplicates, because there's a lot of commonality among some of the shows here. So let's see if we can't filter out duplicates. If I'm reading a CSV file top to bottom, what intuitively might be the logic I want to implement to filter out duplicates? It's not going to be quite as simple as a simple function that does it for me. I'm going to have to build this. But logically, if you're reading a file from top to bottom, how might you go about, in Python or just any context, getting rid of duplicate values? Yeah, what do you think? Sure, I could use a list, and I could add each title to the list, but first check if I've put this into the list before. So let's try a little something like that. Let me go ahead and create a variable at the top of my program here. I'll call it titles, for instance, initialized to an empty list, open bracket, close bracket. And then inside of my loop here, instead of printing it out, let's start to make a decision. So if the current row's title is in the titles array, I don't want to, the titles list, I don't want to put it there. And actually, let me invert the logic so I'm doing something proactively. So if it's not the case that row bracket title is in titles, then go ahead and do something like titles dot append the current row's title. And recall that we saw dot append a week or so ago, where it just allows you to append to the current list. And then what can I do at the very end after I'm all done reading the whole file? Why don't I go ahead and say for title in titles, go ahead and print out the current title. So it's 2 loops now, and we can come back to the quality of that design. But let me go ahead here and rerun Python of favorites.py. Let me increase the size of my terminal window so we can focus just on this and hit enter. And now I'm just skimming. I don't think I'm seeing duplicates, although I am seeing some near duplicates. For instance, there's friends again. And if we keep going and going and going and going, there's friends again. Oh, interesting. So that's curious that I seem to have multiple friends, and I have this one here too. So how might we clean this up further? I like your instincts, and it's a step closer to it. What are we going to have to do to really filter out those near duplicates? Any thoughts? Yeah, what are the common mistakes to summarize? We could ignore the capitalization altogether and maybe just force everything to lowercase or everything to uppercase. Doesn't matter which, but let's just be consistent. And for those of you who might have accidentally or instinctively hit like the space bar at the beginning of your input or even at the end, we can strip that off too. Stripping white space is a common thing just to clean up user input. So let me go back into my code here and let me go ahead and tweak the title a little bit. Let me say that the current title inside of this loop is not going to be just the current row's title, but let me go ahead and strip off from the left and the right implicitly any white space. If you read the documentation for the strip function, it does just that. It gets rid of white space to the left, white space to the right. And then if I want to force everything to maybe uppercase, I can just uppercase the entire string. And remember, what's handy about Python is you can chain some of these function calls together by just using dots again and again. And that just takes whatever just happened, like the white space got stripped off, then it additionally uppercases the whole thing as well. So now I'm going to check whether this specific title is in titles. And if not, I'm going to go ahead and append that title, massaged into this different format, if you will. So I'm throwing away some information, like I'm sacrificing all of the nuances of your grammar and input to the form itself, but at least I'm trying to canonicalize, that is, standardize what the data actually looks like. So let me go ahead and run Python of favorites.py again and hit enter. Oh, and this is just user error. Maybe you haven't seen this before. This just looks like a mistake on my part. I meant to say not even uppercase. That's completely wrong. The function is called upper, now that I think of it. All right, let's go and increase the size of the terminal window again, run Python of favorites.py. And now, it's a little more overwhelming to look at because it's not sorted yet and it's all capitalized. But I don't think I'm seeing multiple friends, so to speak. There's one friends up here. And that's it. I'm back up at my prompt already. So we seem now to be filtering out duplicates. Now, before we dive in further and clean this up further than this, what else could we have done? Well, it turns out that in Python 2, you often do get a lot of functionality built into the language. And I'm kind of implementing myself the idea of a set. If you think back to mathematics, a set is typically something with a bunch of values that has duplicates filtered out. Recall that Python already has this for us. And we saw it really briefly when I whipped up the dictionary implementation a couple of weeks back. So I could actually define my titles to be a set instead of a list. And this would just modestly allow me to refine my code here such that I don't have to bother checking for duplicates anyway. I can instead just say something like titles.add the current title like this. Marginally better design if you know that a set exists, or you're just getting more functionality out of this. All right, so let's clean the data up further. We've now gone ahead and fixed the problem of case sensitivity. We threw away white space in case someone had hit the space bar with some of the input. Let's go ahead now and sort these things by the titles themselves. So instead of just printing out the titles in the same order you all inputted them, but in filtering out duplicates as we go, let me go ahead and use another function in Python you might not have seen, which is literally called sorted, and will take care of the process of actually sorting titles for you. Let me go ahead and increase the font size of my terminal, run Python of favorites.py, and hit enter. And now you can really see how many of these shows start with the word the or do not. Now it's a little easier to wrap our minds around just because it's at least sorted alphabetically. But now you can really see some of the differences in people's inputs. So far, so good, but a few of you decided to stylize avatar in 3 different ways here.
Brooklyn 99, a couple of different ways here. And I think if we keep going, we'll see further and further variances that we did not fix by focusing on white space and capitalization alone. So already here, this is only, what, 100 plus, 200 rows? Already real-world data starts to get messy quickly, and that might not bode well when we actually want to keep around real data from real users. You can imagine an actual website or a mobile application dealing with this kind of thing on scale. Well, let's go ahead and do this. Let's actually figure out the popularity of these various shows by now iterating over my data and keeping track of how many of you inputted a given title. We're going to ignore the problems like Brooklyn Nine-Nine and the Avatar, Avatar, where there was things that were different beyond just white space and capitalization. But let's go ahead and keep track of now how many of you inputted each of these titles. So how can I do this? I'm still going to take this approach of iterating over the CSV file from top to bottom. We've used a couple of data structures thus far, a list to keep track of titles or a set to keep track of titles. But what if I now want to keep around a little more information? For each title, I want to keep around how many times I've seen it before. I'm not doing that yet. I'm throwing away the total number of times I see these shows. How could I start to keep that around? We could use a dictionary. And how? Elaborate on that. Perfect. Really good instincts. Using a dictionary, insofar as it lets us store keys and values, that is, associate something with something else. This is why a dictionary, or hash tables more generally, are such a useful, practical data structure, because they just let you remember stuff in some kind of structured way. So if the keys are going to be the titles I've seen, the values could be the number of times I've seen each of those titles. And so it's kind of like just having a two-column table on paper. For instance, if I were going to do this on a piece of paper, I might just have two columns here, where maybe this is the title that I've seen, and this is the count over here. This is, in effect, a dictionary in Python. It's two columns, keys on the left, values on the right. And this, if I can implement in code, will actually allow me to store this data and then maybe do some simple arithmetic to figure out which is the most popular. So let's do this. Let me go ahead and change my titles to not be a list, not be a set. Let's have it be a dictionary instead, either doing this or, more succinctly, two curly braces that are empty gives me an empty dictionary automatically. What do I now want to do? I think most of my code can stay the same. But down here, I don't want to just blindly add titles to the data structure. I somehow need to keep track of the count. And unfortunately, if I just do this, let's do titles, bracket title, plus equals 1. This is a reasonable first attempt at this, because what am I doing? If titles is a dictionary, and I want to look up the current title therein, the syntax for that, like before, is titles bracket and then the key you want to use to index into the dictionary. It's not a number in this case. It's an actual word, a title. And you're just going to increment it by 1. And then eventually I'll come back and finish my second loop and do things in terms of the order. But for now, let's just keep track of the total counts. Let me go ahead and increase my terminal window. Let me do python of favorites.py and hit enter. And How I Met Your Mother is giving me a key error. What does that mean? And why am I seeing this? And in fact, just to give a little bit of a breadcrumb here, let me zoom out here. Let me open up the CSV file again real quickly. And wow, we didn't even get past the second row in the file or the first show in the file. Notice that How I Met Your Mother, somewhat lowercase, is the very first show in therein. What's your instinct for why this is happening? I don't have a starting point, right? I'm adding 1 to what? Like I'm blindly indexing into the dictionary using a key, How I Met Your Mother, that doesn't yet exist in the dictionary. And so Python throws what's called a key error because the key you're trying to use just doesn't exist yet. So logically, how could we fix this? We're close. We got like half of the problem solved, but I'm not handling the obvious now case of nothing being there. Yeah. Creating the counter itself. So maybe I could do something like this. Let me close my terminal window and let me ask a question first. If the current title is in the dictionary already, if title in titles, that's going to give me a true-false answer, it turns out. Then I can safely say titles bracket title plus equals 1. And recall, this is just shorthand notation for the same
thing is in C, title plus 1. Whoops, typo, don't do that. That's the same thing as this, but it's a little more succinct just to say plus equals 1. Else, if it's logically not the case that the current title is in the titles dictionary, then I probably want to say titles bracket title equals, feel free to just shout it out, 0. I just have to put some value there so that the key itself is also there. All right, so now that I've got this going on, let me go ahead and undo my sorting temporarily. And now let me go ahead and do this. I can, as a quick check, let me go ahead and just run the code as is, Python of favorites.py. I'm back in business. It's printing correctly, no key errors, but it's not sorted. And I'm not seeing any of the counts. Let me just quickly add the counts. And there's a couple of ways I could do this. I could say print out the title, and then maybe let's do something like, how about just comma, titles, bracket, title. So I'm going to print two things at once, both the current title in the dictionary and whatever its value is by indexing into it. Let me increase my terminal window. Let me run Python of favorites.py, enter. And OK, None of you said a whole lot of TV shows, it seems. What's the logical error here? What did I do wrong if I look back at my code here? Yeah, why so many zeros? Exactly. To summarize, I initialized the count to 0 the first time I saw it, but I should have initialized it at least to 1 because I just saw it, or I should change my code a bit. So for instance, if I go back in here, the simplest fix is probably to initialize to 1, because on this iteration of the loop, obviously I'm seeing this title for the very first time. Or I could change my logic a little bit. I could do something like this instead. If the current title is not in titles, then I could initialize it to 0. And then I could get rid of the else and now blindly index into the titles dictionary, because now on line 11, I can trust that lines 9 and 10 took care of the initialization for me if need be. Which one is better? I don't know. This one's a little nicer maybe because it's one line fewer, but I think both approaches are perfectly reasonable and well designed. But the key thing, no pun intended, is that we have to make sure the key exists before we presume to actually increment. Oh, this is wrong. This is incorrect code. What did I do wrong? OK, yes, there we go. So otherwise, everyone would have liked this show once, and no matter how many people said the same thing, now the code is as it should be. So let me go ahead and open up my terminal window again. Let me run Python of favorites.py. And now we see more reasonable counts. Some of the shows weren't that popular. There's just 1s and maybe 2s. But I bet if we sort these things, we can start to see a little more detail. So how else can we do this? Well, it turns out when dealing with a dictionary like this, let's go ahead and just sort the titles themselves. So let's reintroduce the sorted function as I did before, but no other changes. Let me go ahead now and run Python of favorites.py. Now it's just a little easier to wrap your mind around it because at least it's alphabetical, but it's not sorted by value. It's sorted by key. But sure enough, if we scroll down, there's something down here, for instance, like, let's see, The Office. That's definitely going to be a contender for most popular, 15 responses. But let's see, what's actually going to bubble up to the top? Unfortunately, the sorted function only sorts dictionaries by keys by default, not by values. But it turns out in Python, if you read the documentation for the sorted function, you can actually pass in other arguments that tell it how to sort things. For instance, if I want to do things in reverse order, I can add a second parameter to the sorted function called reverse, and it's a named parameter. You literally say reverse equals true so that the position of it in the comma-separated list doesn't matter. If I now rerun this after increasing my terminal window, you'll see now that it's in the opposite order. Now adventure and with an E is at the bottom of the output instead of the top. How can I tell it to sort by a different part by values instead of by key? Well, let's go ahead and do this. Let me go ahead and define a function. I'm just going to call it f to keep things simple. And this f function is going to take a title as input. And given a given title, it's going to return the value of that title. So actually, maybe a better name for this would be getValue. Or we could come up with something else as well. The purpose of the getValue function, to be clear, is to take as input a title and then return the corresponding value. Why is this useful? Well, it turns out that the sorted function in Python, according to its documentation, also takes a key parameter where you can pass in, crazy enough, the name of a function that it will use in order to determine what it should sort by the key or by the value, or in other cases, even other types of data as well. So there's a curiosity here, though, that's very deliberate. Key is the name of the parameter, just like reverse was the name of this other parameter. The value of it, though, is not a function call. It's a function name. Notice I am not doing this, no parentheses. I'm instead passing in getValue, the function I wrote, by its name. And this is a feature of Python and certain other languages. Just like variables, you can actually pass whole functions around so that they can be called for you later on by someone else. So what this means is that the sorted function written by Python, they didn't know what you're going to want to sort by today. But if you provide them with a function called getValue or anything else, now their sorted function will use that function to determine, OK, if you don't want to sort by the key of the dictionary, what do you want to sort by? This is going to tell it to sort by the value, by returning the specific value we care about. So let me go ahead now and rerun this after increasing my terminal. Python of favorites.py, enter. Here we have now an example of all of the titles you all typed in, albeit forced to uppercase and with any white space thrown out. And now The Office is an easy win over Friends versus Community versus Game of Thrones, Breaking Bad, and then a lot of variants thereafter. So there's a lot of steps to go through. Like this, isn't that bad once you've done it once and you know what these functions are and you know that these parameters exist. But it's a lot of work. I mean, that's 17 lines of code just to analyze a CSV file that you all created by way of those Google Forms submissions. But it took me a lot of work just to get simple answers out of it. And indeed, that's going to be among the goals for today ultimately is how can we just make this easier? Right? It's one thing to learn new things in Python, but if we can avoid writing code or this much code, that's going to be a good thing. And so one other technique we can introduce here that does allow us to write a little less code is we can actually get rid of this function. It turns out in Python, if you just need to make a function, but it's going to be used and then essentially thrown away. It's not something you're going to be reusing in multiple places. It's not like a library function that you want to keep around. You can actually just do this. You can change the value of this key parameter to be what's called a lambda function, which is a fancy way of saying a function that technically has no name. It's an anonymous function. Why does it have no name? Well, it's kind of stupid that I invented this name on line 13. I used it on line 16, and then I never again used it. Right? If there's only being used in one place, why bother giving it a name at all? So if you instead in Python say lambda and then type out the name of the parameter you want this anonymous function to take, you can then say, go ahead and return this value. Now, notice the inconsistencies here. When you use this special lambda keyword that says, hey, Python, give me an anonymous function, a function with no name. It then says, Python, this anonymous function will take one parameter. Notice there's no parentheses, and that's deliberate if confusing. It just tightens things up a little bit. Notice that there's no return keyword, which similarly tightens things up a bit, albeit inconsistently. But this line of code I've just highlighted is actually identical in functionality to this. But it throws away the word def, it throws away the word getValue, it throws away the parentheses, and it throws away the return keyword just to tighten things up. And it's well suited for a problem like this, where I just want to pass in a tiny little function that does something useful, but it's not something I'm going to reuse. It doesn't need multiple lines to take up space. It's just a nice, elegant one-liner. That's all a lambda function does. It allows you to create an anonymous function right then and there, and then the function you're passing it to, like sorted, will use it as before. Indeed, if I run Python of favorites.py after growing my terminal window, the result is exactly the same. And we see at the bottom here all of those small results. Are any questions then on this syntax, on these ideas? The goal here has been to write a Python program that just starts to analyze or clean up data like this. Yeah? Could you use the lambda if it's just returning immediately? It's really meant for one line of code generally. So you don't use the return keyword. You just say what it is you want to return.
Good question. Could you do more in that one line if it's got to be a more involved algorithm? Yes, but you would just ultimately return the value in question. In short, if it's getting it all sophisticated, you don't use the lambda function in Python. You go ahead and actually just define a name for it, even if it's a one-off name. JavaScript, another language we'll look at in a few weeks, makes heavier use, I dare say, of lambda functions. And those can actually be multiple lines. But Python does not support that instinct. All right, so let's go ahead and do one other thing. Office was clearly popping out of the code here quite a bit. Let's go ahead and write a slightly different program that maybe just focuses on the office for the moment. Just focuses on the office. So let me go ahead and throw most of this code away up until this point when I'm inside of my inner loop. And let me go ahead and I don't even want the global variable here. All I want to do is focus on the current title. How could I detect if someone likes the office? Well, I could say something like, how about this? So counter equals 0. We'll just focus on the office. If title equals the office, I could then go ahead and say counter plus equals 1. I don't need a key. There's no dictionary involved now. It's just a simple integer variable. And then down here, I'll say something like number of people who like the office is whatever this value is, and I'll put in counter in curly braces, and then I'll turn this whole thing into an F string. All right, let me go ahead and run this. Python of favorites.py, enter. Number of people who like the office is 15. All right, so that's great, but let's go ahead now and deliberately muddy the data a bit. All of you were very nice in that you typed in the office. But you could imagine someone just typing office, for instance, maybe there, and many people might just write office. You could imagine, didn't happen here, but suppose it did, and probably would have if we had even more submissions over time. Now let's go ahead and rerun this program. No changes to the code. Now only 13 people like the office. So let's fix this. The data is now, as I mutated it, to have a couple of offices and many the offices. How could I change my Python code to now count both of those situations? What could I change up here in order to improve this situation? Any thoughts? Yeah. Yeah, so I could just ask two questions like that. If title equals the office or title equals just office, for instance, and I'm still don't have to worry about capitalization. I don't have to worry about spaces because I at least threw that all away. Now I can go ahead and rerun this code. Let me go run it a third time. OK, so we're back up to 15. So I like that. But you can imagine this not scaling very well, right? Like Avatar had 3 different permutations, and there were some others, if we dug deeper, that there might have been more variants. Could we do something a little more general purpose? Well, we could do something like this. If office in the title, this is kind of a cool thing you can do with Python. It's very English-like. Just ask the question, albeit tersely. This, interesting, just got me into trouble. Now all of a sudden we're up to 16. Does anyone know what the other one is? What office? Oh, interesting. Yes, so they hit V. OK. OK, someone did that. Sure. So the V office. OK, this one's actually going to be hard to correct for. Like, I can't really think of a general. Well, this is actually a good example of like data gets messy fast. And you could imagine doing something where, OK, we could have like 26 conditions. If someone said the A office or the B office, or right, you could imagine doing that. But then there's surely going to be other typos that are possible. So that's actually a hard one to fix. But it turns out we got lucky, and now this is actually the accurate count. But the data is itself messy. Let me show another way that just as another tool to our toolkit. It turns out that there's this feature in many programming languages, Python among them, called regular expressions. And this is actually a really powerful technique that we'll just scratch the surface of here, but it's going to be really useful actually maybe toward final projects, in web programming, anytime you want to clean up data or validate data. And actually, just to make this clear, give me a moment before I switch screens here. And let me open up a Google form from scratch. Give me just a moment to create something real quick. If you've never noticed this before when creating a Google form, you can do like a
question. And if you want the user to type in something very specific as a short text answer like this, you might know that there's toggles like this in Google's world, like you can require it. Or you can do response validation, like you could say, what's your email? And then you could say something like text is an email. So here's an example in Google Forms how you can validate users' input. But a feature most of you have probably never noticed or cared about or used is this thing called a regular expression, where you can actually define a pattern. And I could actually re-implement that same idea by doing something like this. I can say, let the user type in anything, represented by dot star, then an @ sign, then something else, then a literal period, then, for instance, something else. So it's very cryptic, admittedly, at first glance, but this means any character 0 more times. This means any character 0 more times. This means a literal period, because apparently dot means any character in the context of these patterns. Then this thing means any character 0 more times. So I should actually be a little more nitpicky. You don't want 0 or more times. You want 1 or more times. So this with a plus means any character 1 or more times. So there has to be something there. And I think I want the same thing here, 1 or more times, 1 or more times. Or heck, if I want to restrict this form in some sense to edu addresses, I could change that last thing to literally .edu. And so long story short, even though this looks, I'm sure, pretty cryptic, there is this sort of mini language built into Python and JavaScript and Java and other languages that allows you to express patterns in a standardized way. And this pattern is actually something we can implement in code too. And let me switch back to Python for a second just to do the same kind of idea. Let me toggle back to my code here. Let me put up, for instance, a summary of what it is you can do. And here's just a quick summary of all of the available, some of the available symbols. A period represents any character. Dot star or dot asterisk means 0 or more characters. So the dot means anything. So it can be A or nothing. It can be B or nothing. It can be AB, ABC. It can be any combination of 0 or more characters. Change that to a plus, and you now express 1 or more characters. Question mark means something is optional. Caret symbol means start matching at the beginning of the user's input. $sign means start matching at the end of the user, or stop matching at the end of the user's input. So we won't play with all of these just now, but let me go over here and actually tackle this office problem. Let me go ahead and import a new library called the regular expression library, import RE. And then down here, let me say this. If re.search, this pattern, let's just search for office, quote unquote, in the current title. Then we're going to go ahead and increase the counter. So it turns out that the regular expression library has a function called search that takes as its first argument a pattern, and then as its second argument, the string you want to analyze for that pattern. So it's sort of look for a needle in this haystack from left to right. Let me go ahead now and run this version of the program. Enter. And now I screwed up because I forgot my colon. But that's old stuff. Enter. Number of people who like The Office is now 0. So this seems like a big, thank you, big step backwards. What did I do wrong? Yeah. Yeah, so I forced all my input to uppercase, so I probably need to do this. So we'll come back to other approaches there. Let me rerun it now. OK, now we're back up to 16. But I could even, let's say, I could tolerate just The Office. How about this? Or how about something like or The Office? Let me do this instead. And let me use these other special characters. This caret sign means the beginning of the string. This $sign weirdly represents the end of the string. I'm adding in some parentheses, just like in math, just to add another symbol here, the or symbol here. And this is saying start matching at the beginning of the user string. Check if the beginning of the string is office or the beginning of the string is the office. And then you better be at the end of the string. So they can't keep typing words before or after that input. Let me go ahead and rerun the program. And now we're down to 15. Which used to be our correct answer, but then we noticed the office. How can we deal with that? It's going to be messier to deal with that. But I could. How about if I tolerate any character represented by dot in between the and office? Now if I rerun it,
Now I really have this expressive capability. So this is only to say there are so many ways in languages in general to solve problems, and some of these tools are more sophisticated than others. This is one that you've actually probably glanced at but never used in the context of Google Forms for years if you're in the habit of creating these for student groups or other activities. But it's now something you can start to leverage, and we're just scratching the surface of what's actually possible with this. But let's now do one final example just using some Python code here. And let's actually write a program that's a little more general purpose that allows me to search for any given title and figure out its popularity. So let me go ahead and simplify this. Let's get rid of our regular expressions. Let's go ahead and continue capitalizing the title. And let's go ahead to, at the beginning of this program, and first ask the user for the title they want to search for. So title equals, let's ask the user for input, which is essentially the same thing as our CS50 getString function. Ask them for the title. And then whatever they type in, let's go ahead and strip white space and uppercase the thing again. And now inside of my loop, I could say something like this. If the current row's title, after stripping white space and forcing it to uppercase 2, equals the user's title, then go ahead and maybe increment a counter. So I still need that counter back. So let me go ahead and define this maybe in here. Counter equals 0. And then at the very end of this program, let me go ahead and print out just the popularity of whatever the human typed in. So again, the only difference is I'm asking the human for some input this time. I'm initializing my counter to 0. Then I'm searching for their title in the CSV file by doing the same massaging of the data by forcing it to uppercase and getting rid of the white space. So now when I run python of favorites.py, enter, I could type in the office, all lowercase even, and now we're down to 13. Why? Oh, that's correct, because I'm the one that went in and removed those the keywords a bit ago. If we fix those, we would be back up to 15. If we hadn't support for the office, we would be up to 16 as well. All right, any questions then on these various manipulations? And if you're feeling like, oh my God, this is so much Python code just to do simple things, that's the point. And indeed, even though it's a powerful language and can solve these kinds of problems, we had to write almost 20 lines of code just to ask a single question like this. But any questions on how we did this? Or on any of these building blocks along the way? Anything here? No? All right, that was a lot. Let's take a 5-minute break here. When we come back, we'll do it better. So we are back. And the rest of today is ultimately about how can we store and manipulate and change and retrieve data more efficiently than we might by just writing raw code. This isn't to say that you shouldn't use Python to do the kinds of things that we just did. And in fact, it might be super common if you're getting a lot of messy input from users that you might want to clean it up. And maybe the best way to do that is to write a program so that step by step you can make all of the requisite changes and fixes like we did with the Office, for instance, again and again, and reuse that code, especially if more and more submissions are coming through. But another theme of today, ultimately, is that sometimes there are different, if not better, tools for the same job. And in fact, now, at this point in the term, as we begin to introduce not just Python, but in a moment, a language called SQL, and next week, a language called JavaScript, and the week after that, synthesizing a whole lot of these languages together, is to just kind of paint a picture of how you might decide what the trade-offs are between using this tool or this other tool, because undoubtedly you can solve problems moving forward in many different ways with many different tools. So let's give you another tool, one with which you can implement a proper relational database. What we just saw in the form of CSV files are what we might call flat file databases. Again, just a very simple file, flat in that there's no hierarchy to it. It's just like rows and columns. And that is all ultimately storing ASCII or Unicode text. A relational database, though, is something that's actually closer to a proper spreadsheet program, right? Like a CSV is an individual sheet, if you will, from a spreadsheet when you export it. If you had multiple sheets in a spreadsheet, you would have to export multiple CSVs. And that gets annoying quickly in code if you have to open up this CSV, all of which represent different sheets or tabs in a proper spreadsheet. A relational database is more like a spreadsheet program that you, a programmer now, can interact with. You can write data to it, you can read data from it, and you can have multiple sheets, aka tables, storing all of your data. So whereas Excel and numbers and Google Spreadsheet are meant to be used really by humans with their mouse and their keyboard, clicking and pointing and manipulating things graphically, a relational database using a language called SQL is one in which the programmer has similar capabilities, but doing so in code, specifically using a language called SQL, and at a scale that's much grander than spreadsheets alone. In fact, if you try on your Mac or PC to open a spreadsheet that's got tens of thousands of rows, it'll probably work fine. Hundreds of thousands of rows, millions of rows, no way. Like at some point, your Mac or PC is going to struggle to open particularly large data sets, and that too is where proper databases come into play and proper languages for databases come into play when it's all about scale. And indeed, most any mobile app or web app today that you or someone else might write should probably plan on lots of data if it's successful, so we need the right tools for that problem. So fortunately, even though we're about to learn yet another language, it only does 4 things fundamentally, known by this silly acronym, CRUD. SQL, this language for databases, supports the ability to create data, read data, update data, and delete data. Like, that's it. There's a few more keywords that exist in this language called SQL that we'll soon see. But at the end of the day, even if you're starting to feel like this is a lot very quickly, it all boils down to these 4 basic operations. And the 4 commands in SQL, if you will, functions in a sense, that implement those 4 ideas happen to be these. They're almost the same, but with some slight variance. The ability to create or insert data is the C. The ability to select data is the R, or read. Update is the same, delete is the same, but drop is also a keyword as well. So we'll see these and a few other keywords in SQL that at the end of the day just allow you to create, read, and update data using verbs, if you will, like these. So to do that, what's the syntax going to be? Well, we won't get into the weeds too quickly on this, but here's a representative syntax of how you can create, using this language called SQL, in your very own database, a brand new table. Right? This is so easy in Excel and Google Spreadsheets and Apple Numbers. You want a new sheet, you click the plus button, you get a new tab, you give it a name, and boom, you're done. In the world of programming, though, if you want to create the analog of that spreadsheet in the computer's memory, you create something called a table, like a sheet that has a name, and then in parentheses has 1 or more columns. But unlike Google Spreadsheets and Apple Numbers and Excel, you have to decide as the programmer what types of data you're going to be storing in each of these columns. Now, even though Excel and Google Spreadsheets and Numbers does allow you to format or present data in different ways, it's not strongly typed data like it is, for instance, when we were using C. And heck, even in Python, there's underlying data types, even if you don't have to type them explicitly. Databases are going to want to know, are you storing integers? Are you storing real numbers or floats? Are you storing text? Why? Because especially as your data scales, the more hints you give the database about your data, the more performant it can be, the faster it can help you get at and store that data. So types are about to be important again, but there's not going to be that many of them, fortunately. Now, how can I go about converting, for instance, some real data, like that from you, my favorites.csv file, into a proper relational database? Well, it turns out that using SQL, I can do this in VS Code on my own Mac or PC or in the cloud here by just importing the CSV into a database. We'll see eventually how to do this manually. For now, I'm going to use more of an automated process. So let me go over to VS Code here. Let me type ls to see where we left off before. I had 2 files, favorites.csv, which I downloaded from Google Spreadsheets. Recall that I made a couple changes. We deleted a couple of thes from the file for the office, but this is the same file as before. And then we have favorites.py, which we'll set aside for now. I'm going to go ahead now and run a command, SQLite 3. So in the world of relational databases, there's many different products out there, many different software that implements the SQL language. Microsoft has their own. There's something called MySQL that's been very popular for years. Facebook, for instance, used it early on. PostgreSQL, Microsoft Access Server, Oracle, and maybe a whole bunch of other product names you might have encountered over time. Which is to say, there's many different types of tools and servers and software in which you can use SQL. We're going to use a very lightweight version of the SQL language today called SQLite. This is the version of SQL that's generally used on iPhones and Android devices these days. If you download an app that stores data like your own contacts, typically is stored using SQLite because it's fairly lightweight, but you can still store hundreds, thousands, even tens of thousands of pieces of data even using this lightweight version thereof. SQLite 3 is like version 3 of this tool. We're going to go ahead and run SQLite 3 with a file called favorites.db. It's conventional in the world of SQLite to name your file something.db. I'm going to create a database called favorites.db. Once I'm inside of the program now, I'm going to go ahead and enter CSV mode. Again, not something you have to memorize, just something you can look up as needed. And then I'm going to import favorites.csv into a table that is a sheet, if you will, called favorites as well. Now I'm going to hit enter, and I'm going to go ahead and exit the program altogether and type ls. Now I have 3 files in my current directory, the CSV file, the Python file from before, and now favorites.db. But if I did this right, all of the data you all typed into the CSV file has now been loaded into a proper database where I can now use this SQL language to access it instead. So let's go ahead again and run SQLite 3 of favorites.db, which now exists. And now, at the SQLite prompt, I can start to play around and see what this data is. For instance, I can look by typing .schema at what the schema is of my data. What's the design? Now, no thought was put into the design of this data at the moment because I automated the whole process. Once we start creating our own databases, we'll give more thought to the data types and the columns that we have. But we can see what SQLite presumed I wanted just by importing the data by default. What the import command did for me a moment ago is essentially this syntax. It automated the process of creating a table, if it doesn't exist, called favorites. And then notice in parentheses, it gave me 3 columns: timestamp, title, and genres, which were inferred obviously from the CSV, all 3 of which have been decreed to be text. Again, once we're more comfortable, we'll create our own tables, choose our own types and column names. But for now, I just automated the whole process just to get us started by using this built-in import command as well. All right. So what now can I begin to do? Well, if I wanted to, for instance, start playing around with data therein, I might execute a couple of different commands, one of which, let me find the right one here, one of which would be select. Select being one of our most versatile tools to select data from this database. So if I have these 3 columns here, timestamp, title, and genres, suppose I want to select all of the titles. Doing that earlier in Python required importing the CSV library, opening the file, creating a reader or a dict reader, iterating over every row, adding every title to a dictionary or just printing it out, and ... right? There was like a dozen or so lines of code when we first began. Now, how about this? Select title from favorites, semicolon, done. So now, with this particular language, the output is very textual, and it's simulating what it looks like if it were more graphical by creating this table, so to speak. Select title from favorites is a distillation in a different language called SQL of all the lines of code I wrote early on when we first started playing with favorites.py. SQL is therefore optimized for reading and creating and updating and ultimately deleting data. So here's perhaps a better tool for the job once you have the data. Tossing it into a more powerful, versatile format might allow you now to get more work done more quickly without having to reinvent the wheel. Someone else has figured out how to select data like this. What more can I do here? Well, let me go ahead and pull up in a moment just a little bit of a cheat sheet here. Give me 1 second to find this. So suppose I want to now select data a little more powerfully. So here's what I just did in a canonical way. So select typically works like this. You select columns from a specific table, semicolon. Unfortunately, stupid semicolons are back. Select columns from table, then, is the sort of generic form of what I just did more specifically. I selected 1 column called title from favorites. Favorites is the name of the table. Semicolon ends my thought. Suppose I wanted to get 2 things, like the genres that each of you inputted. I could instead do select title, comma, genres from favorites, and then a semicolon, and enter. It's going to look a little ugly on my screen because some of these titles and some, OK, one of you really went all out with community. You can see that it's just wrapping in an ugly way, but it's just now showing me 2 columns. If we scroll up to the very top again, the leftmost of one, Black Mirror went all out too, thank you. And now, OK, we're going to have to clean some of these up. Game of Thrones, good comedy, yes. Keep going, keep going, keep going. So now we've selected 2 of the columns that we care about. There it is. OK, so it's crazy wide because of all of those genres, but it allows me to select exactly the data I want. Let's go back to the titles, though, and perhaps start playing around with some modifiers here. For instance, it turns out, using SQL, there's a lot of functionality built into the language. You've got a lot of functions, similar to Excel or Google Spreadsheets where you can have formulas. SQL provides you with some of the same heuristics that allow you to apply operations like these on entire columns. For instance, you can take averages, count the total, get the distinct values, force things to lowercase, uppercase, min and max, and so forth. So let's try distinct, for instance. Let me go back to my terminal, and let's say select, how about the distinct titles from the favorites table? Enter. I didn't bother selecting the genres because I want it to be a little prettier. And you can see here that we have just the distinct titles, except for issues of formatting, right? So white space is going to be an issue again. Capitalization is going to be a thing again. So there's a trade-off. I mean, one of the things I was doing in Python was forcing everything to uppercase and then getting rid of white space. But we could combine some of these. I could do something like force every title to uppercase, then get the distinct value. And that's actually going to get rid of some of those values as well. And again, I did it all in one simple line. That was fast. So let me pull up at the bottom of the screen again. I selected distinct upper titles from favorites. And that did everything for me at once in just one breath. Suppose I want to get the total number of counts of titles. How about select count of all of those titles from favorites, semicolon, enter. And now you get back sort of a mini table that contains just your answer, 158 in this case. So that's the total number of not distinct, but total titles that we had in the file. And we can continue to manipulate the data further using, again, functions like these here. But there's also additional filtration we can do. We can also qualify our selections by saying where some condition is true. So just as in Scratch, in C, and Python, you have Boolean expressions, you can have the same in SQL as well, where I can filter my data where something is true or false. Like allows me to do approximations. If I want to get something that's like the office, but not necessarily THE space office, I could do pattern matching using like here. Order by, limit, and group by are other commands I can execute too. So let me go back and do a couple of these here. How about, let me just get, I don't know, all of the titles from favorites, but limit it to 10 results. That might be one thing that's helpful to see if you just care about some of the data at the top there instead. How about select all of the titles from favorites where the title itself is like, quote unquote, office. And this will give me only 2 answers. Those are the 2 rows, recall, that I mutated by getting rid of the word the. Notice that like allows me to tolerate uppercase and lowercase, because if I instead just use the equal sign, and in SQL, in single equal sign does, in fact, mean equality. It's not, for comparison's sake, it's not doing assignment. This is not how you assign data in SQL. I got back no answers there. So indeed, the equal sign is giving me literal answers that searches just for what I typed in. How could I get all of these? Well, similar in spirit to regular expressions, but not quite as powerful in SQL. I could do something like this. I can select the title from favorites where the title is like, quote unquote, office, but I can add, a bit weirdly, % signs to the left and the right. So the language SQL supports the same notion of pattern matching, but much more limited out of the box. If we want more powerful regular expressions, we probably do want to use Python instead. But the % sign here means 0 or more characters on the left, 0 or more characters on the right. So this will just grab any title that contains OFFICE in it in that order. And now I get all 16, it would seem, of those results again. How do I know it's 16? Well, I can just get the count of those titles and get back that answer instead as well. So again, it takes some getting used to the vocabulary and sort of the syntax that you can use. There's these building blocks and others, but SQL is really designed, again, for creating, reading, updating, and deleting data. For instance, I've never really been a fan of friends, for instance. So right now, if I do select, how about title from favorites, where title
like quote unquote friends with the percent signs, we can see that there's a whole bunch of them. That's how many exactly? Let's just do a quick count. So that's 9 of them. Well, delete from favorites. OK, you and me, you delete from favorites where title like friends, enter. Nothing seems to happen, but bye-bye friends. So now we've actually, thank you. So now we've actually changed the data. And this is what's compelling about a database, a proper database. Yes, you could technically write Python code that not only reads the CSV file, but also writes it. Like you can change using quote unquote A for append or quote unquote W for write instead of quote unquote R for read alone. But it's definitely a little more involved to do that in Python. But with SQL, you can update the data in real time. And if I were actually running like a web application here or a database for a mobile app, that change theoretically would be reflected everywhere on your own devices if you're somehow talking to this application. So that's sort of the direction we're headed. This other thing has been bothering me. So select, how about title from favorites, where title equals, what was it? The office, was it? Yeah, it was that one. How about we update favorites by setting title equal to the office, where title equals, quote unquote, the office, semicolon. And now if I select the same thing again, I can go up and down with my arrow keys quickly. Now there is no the office. We've actually changed that value. How about genres? Select genres from favorites where the title is title equals Game of Thrones, semicolon. These were kind of long, and I don't really agree with all of that. So how about we update favorites, set genres equal to, sure, action, adventure, sure, drama. OK, so it's a decent list. Fantasy, sure, thriller, war. OK, anything really but comedy, I would say. Let's go ahead and hit enter now. And now if I select genres again, same query, now we've sort of canonicalized that. We've thrown data away. So whether or not that is right is probably a bit subjective and argumentative. But I have at least cleaned up my data, which is, again, the U in CRUD. Create, read, update, delete. You can do it that easily. Beware using delete. Beware worse using drop, whereby you can drop an entire table. But via these kinds of commands, can we actually now manipulate our data much more rapidly and with single thoughts. And in fact, if you're an aspiring statistician or data scientist or analyst in the real world, SQL is such a commonly used language because it allows you to really dive into data quickly and ask questions of the data and get back answers quite quickly. And this is a simple data set. You can do this with much larger data sets, as we soon will too. Are any questions on what we've seen of SQL thus far? Only scratch the surface, but again, it boils down to creating, reading, updating, and deleting data. Questions here? All right, well, let's consider the design of this data. Recall that if I do .schema, that shows me the design of my table, the so-called schema of my data. This is OK. It gets the job done. And frankly, everything the user typed in was arguably text, including the timestamp, which is the date and time. So the data set itself is somewhat simple. But if we look at the data set itself, especially genres, let's do this. Select genres from favorites. And let me point out one other thing stylistically, too. I am very deliberately capitalizing all of these special SQL keywords, and I'm lowercasing all of the column names and the table names. This is a convention. And honestly, it just helps you read, I think, the code when you're commingling your names for columns and tables with proper SQL keywords. But I could just as easily do select genres from favorites. But again, the SQL-specific keywords don't quite jump out as much. So stylistically, we would recommend this, selecting genres from favorites, semicolon. So here is where, OK, that was not intended. I accidentally made every show, including The Office, about action, adventure, drama, fantasy, thriller, and war. How did I do that accidentally? What did I do wrong? Yeah, so beware. It's funny, I think I did say beware around this time. So the SQL database took me literally. I updated favorites, setting genres equal to that, semicolon, end of thought. I really wanted to say where title equals, quote unquote, Game of Thrones,
Unfortunately, there isn't an undo command or time machine with a SQL database. So the best we can do here is let's actually get rid of favorites.db. Let's run SQLite of favorites.db again, which now will be recreated. Let me change myself into CSV mode. Let me import into my favorites table, the CSV file. And now friends is back for better or for worse, but so are all of our genres. So if I now do select, if I now reload the file and do select genres from favorites, that was the result I was getting. It's much messier, but that's because some of these are quite long. But now we're back to the original data. Lesson here, be sure to back up your work. All right, so what more can we now do with this data? Well, I don't love the design of the genres table for a couple of reasons. One, I mean, we didn't have any sort of validation, but user input's going to be messy. There's just a lot of redundancy in here, right? Like, let's go ahead and do this. Let me select all the comedies you all typed in. So select title from favorites where genres equals quote unquote comedy. OK, so there's all of the shows that are explicitly comedies. But I think there might actually be others. Let me scroll back up here. Comedy drama. What was a comedy and a drama? How about? Let's search for the, whoops. Let me copy paste comedy, comma, drama. OK, so The Office, in this case, was considered comedy and drama. Billions, It's Always Sunny in Philadelphia, and Gilmore Girls as well. But notice that I get many more when I just search for comedy. So the catch here is that because I have all of these genres implemented the way Google did as a comma-separated list, it's actually really hard and messy to get at any show, all of the shows that are somewhere described as comedy, right? Because if I search for quote-unquote comedy, the only answers I'm going to get are this one, whatever that show is, this one, whatever that show is, this one, but I'm not going to get this one. I'm not going to get this one. Why? If I'm searching for where genres equals quote-unquote comedy, why am I missing those other shows? Why am I missing? Yeah. Exactly. It's not just a comedy. It's a comedy and a drama and a comedy or a news show and so forth. So I have to search for these commas. So this gets messy quickly, right? Like, let me copy this so I can do this. Let me search for where genres equals comedy. How about or genres equals comedy drama, or genres equals this whole thing, comedy, news, talk show. I'm going to get more and more results, but that's not going to scale well. What could I do instead of enumerating with ors all of the different permutations of genres, do you think? Yeah, so I could use the keyword, similar in Python to the word in. I could use the like keyword so that so long as the genres is like comedy somewhere in there, that's going to give me all of them, so long as the word comedy is in there. But let me go ahead and just open the form from earlier. The form had, let me see if I can open this real quick before I toggle over. If we look back at the form, recall that there were all of those radio buttons asking for the specific genres into which something fell. And if I open this, let me full screen here and now open the original form, you'll see all of the genres here, none of which are that worrisome except for a corner case is jumping out at me. Where might the like keyword alone get me into trouble? It's not with comedy. I'm OK with comedy, but yeah, music and musical are deliberately on the list here because, one, there are separate genres. But if I just search for something that's like music, I'm going to accidentally suck in all of the musicals, which might not be what I intend. If music is like a music video or whatever, and musical is actually a different type of show, I don't want to just do that. So it seems just very messy. Like I could probably hack something together with maybe add some commas in there or something like this. But this is just not a good design for the data. Google has done it this way because it's just simple to actually keep the user's data all in a single column and, just as they did, separate it by commas. But this is a real messy way to use CSVs by putting comma-separated values in your comma-separated values. Arguably, the folks at Google probably just did this because it's just simpler. And they didn't want to give people multiple sheets or complicate things using some other weirder character than commas alone. But I bet there's a better way for us to do this. And let me go ahead and do this.
Let me go back into my code here. And in just a moment, I'm going to grab a program that I wrote in advance that's going to use Python to open up the CSV file, iterate over all of the rows, and load the data into 2 tables this time. 2 tables, one called shows and one called genres, so as to actually separate these 2 things out. Give me just a moment to grab the code. And when I run this, I'll only have to run it once. Let me go ahead and run Python in a moment, and I'll reveal the results in a sec. This is going to be version 8 of the code online. When I do this, let me go ahead and open up this file. Give me a second to move it into this directory. Version 8. OK. So here we have version 8 of this that's available online that's going to do the following. And I'll gloss over some of the details just so that we don't get stuck in the weeds of some of this code. I'm going to be using at the top of this program, as we'll soon see, a CS50 library, not for the sake of getString or getInt or getFloat, but because there's some built-in SQL functionality that we didn't discuss a couple of weeks back with the CS50 library itself. But inside of the CS50 library, we'll see, there is a special function called SQL that gives you the ability, using this weird URL-like looking thing, technically called a URI, that allows me to open a file called favorites.db. And long story short, all of the subsequent code is going to iterate over this favorites.csv file that we downloaded, and it's going to import it into the SQLite database, but it's going to use 2 tables instead of just 1. So give me just a moment to run this, and then I'll reveal the actual results. This is going to be run on favorites.csv. And taking a look here, give me just a moment. Give me a sec. Come on. Come on. This program should not be taking this long. Sorry. Let's open this real fast. Whoops, not that file. OK, let me just skim this code real quick to see where we've gone wrong with favorites.csv, reader, title, show ID, insert into shows. Row and genre split, execute. All right, this is me debugging in real time. All those times we encourage you to use print. This is me actually using print. We'll see how quickly I can recover from this. Python of favorites version 8. OK, so here's me debugging in real time. It's printing out. Oh, maybe I just didn't wait long enough. OK, so here we go. What I'm doing is printing out the dictionary that represents each row that you all typed in. And we're actually making progress. All right, I was too impatient and didn't wait long enough. So in a moment, there we go. All right, so all you have to do sometimes is wait. Let me go ahead now and open this file using SQLite 3. So in SQLite 3, I now have a different version of favorites.db. I named it number 8 for consistency. Once I've run the program, I can do .schema to look inside of it. And here's what the 2 tables in this database are going to look like. I've created a table called shows, this time to represent all of the TV shows that are favorites, that has 2 columns. One is called ID. One is called title. But now I'm going to start taking out for a spin some of the other features of SQL. And besides there being text, it turns out there's a data type called integer. Besides there being a data type called text, there's also a special key phrase that you can specify that the title can never be null. Think back to our use of null in C. Think back to the keyword none in Python. This is a database constraint that allows you to ensure that none of you can't have a favorite TV show. Like if you submit the form, you have to have typed in a title for it to end up in our database here. And you'll notice one other new feature. It turns out on this table, I'm defining what's called a primary key, specifically to be the ID column. More on that in just a moment. Meanwhile, the second table my code has created for me, as we'll soon see, gives me a column called show ID, and then a genre, the value of which is text, that can also not be null. And then more on this in a moment. This table has what we're going to call a foreign key, specifically the show ID column that references shows ID. So before we get into the weeds of this, this is now a way of creating the relation in relational database. If I have 2 tables now, not just one, they can somehow be linked together by a common column. In other words, the shows column, shows table, is going to give me a table with 2 columns, an ID and a title. Every
title you gave me, I'm going to assign a unique value. The genres table, meanwhile, is going to associate individual genres, singular, with that same ID. And the result of this, to pop back to the terminal here, is let's do this. Select star from shows of this new database. And you'll see that I've given, indeed, all of the shows you all typed in unique identifiers. I didn't filter out duplicates or do anything beyond just forcing everything to uppercase. So there's going to be some duplicates here because I didn't want to get rid of anyone's data. But you'll see that, indeed, I've given everyone a unique identifier, from the very first person who typed How I Met Your Mother all the way down to input number 158. Meanwhile, if I do select star from genres, which is now a table, not just a column in the original data, now you'll see a much better design for this data. Notice what I've done here. Let me go all the way to the top, and you'll see two columns, one of which is called show ID, the other of which is called genre. And again, I wrote some code to do this because I had to take Google's messy output where everything was separated by commas. I had to tear away the commas and then put each genre into this table by itself. Even though we haven't introduced the syntax via which we can reconstitute the data and reassociate your genres with your titles, why at a glance might this be a better design now? Even though I've doubled the number of tables from 1 to 2, why is this probably on the direction toward a better design? What might your instincts be? Why is this cleaner? Again, first time with SQL. Why is it better, perhaps, that we've done this with our genres table? Can I come to you? Why might this be better? Yeah, oh, just because we had the conversation before about the commas. Exactly. It's as simple as that. We've cleaned up the data by giving every genre, every word in the genres column in the original Google spreadsheet its own cell in this table, if you will. And now notice show ID might appear multiple times. Whoever typed in How I Met Your Mother, they only associated one genre with it. And so we see that show ID 1 is a comedy. But whoever typed in, I forget the name of the second show offhand, but that person, whoever was assigned show ID 2, checked off a whole bunch of the genres boxes. That happened again with show ID 3, 4, persons 5, 6, 7, only checked one box. And so you can see now that we've associated the data with what we might call a one-to-many relationship, a one-to-many relationship, whereby for every one show in the shows table, it can now have many genres associated with it, each of which is represented by a separate row here. So again, if I go ahead and select star from shows, let's limit it to the first 10 just to focus on a subset of the data. How I Met Your Mother, The Sopranos was the second input there. It would seem that now that I've created the data in this way, I could ideally somehow search the data, but a little more correctly. I don't have to worry about the commas. I don't have to worry about the hackish approach of music being a substring of musical. But how can I actually get back at this data? Well, let's go ahead and do this. Suppose I did want to get back maybe all of the comedies. All of the comedies, no matter whether the person checked just the comedy box or multiple boxes instead. How now, given that I have two tables, could I go about selecting only the titles of comedies? Like, I've actually made the problem a little harder, but again, SQL is going to give me a solution for this. The problem is that if I want to search for comedies, I have to check the genres table first, and then what's that going to give me? Like, if I search the genres table for comedies, what's that going to give me back? Potentially, yeah. Maybe show ID. So let me try that. Let me do select show ID from genres, where the genre in a given row equals quote unquote comedy. No commas, no like, no percent signs, because literally that column now is singular words like comedy or drama or the like. Let me go ahead and hit enter here. OK, so I got back a whole bunch of ID numbers. Now this could very quickly get annoying. It looks like show ID 1, 2,